Nonetheless, faith that the universe is knowable, faith that the patterns we have detected close to home extend outward, faithfully, to the farthest shores of space and time. Faith that the story we have pieced together from starlight and radio waves and gravitational whispers is the true story, or close enough to true that the difference barely matters. Webb did not merely outdate that story. It threatened to rewrite it from the opening line. The model we had constructed was called the lambda-CDM model, cold dark matter, seasoned with the cosmological constant, a mathematical term Einstein had once inserted into his equations and then famously regretted, a kind of fudge factor that turned out not to be a fudge at all, but a description of something real and deeply strange, a repulsive energy woven into the fabric of space itself, pushing everything apart, accelerating the expansion of the universe at a rate that defies intuitive comprehension. This model, this lambda-CDM, had been one of the great triumphs of late 20th and early 21st century physics. It described the large-scale structure of the cosmos with extraordinary precision. It predicted the patterns in the cosmic microwave background radiation, the faint afterglow of the Big Bang, still detectable today as a kind of thermal hum pervading all of space, with a fidelity that was almost uncanny. It told us when the first stars should have formed, how they should have clustered into galaxies, how those galaxies should have grown and merged and evolved over the 13.8 billion years since the universe began its great expansion. It was beautiful. It was elegant. And if Webb's early findings are to be believed, it may be incomplete in ways that will take decades to fully understand. What Webb found, staring into the ancient light of the universe's first billion years, were galaxies. That sounds unremarkable until you understand what kind of galaxies they were. They were large. They were massive. They were structured and mature and luminous in ways that the standard model said they simply should not yet be. Galaxies of that size, with that many stars, arranged with that degree of order, they require time to build. They require the slow gravitational accumulation of matter, the collapse of clouds of hydrogen and helium into the first stellar nurseries, the birth and death of generations of stars, the progressive enrichment of the interstellar medium with heavier elements forged in stellar cores and scattered by supernovae, the mergers of smaller galaxies into larger ones, the patient, unhurried process of cosmic construction that unfolds over hundreds of millions and then billions of years. Or so we thought. Webb looked back to within the first few 100 million years after the Big Bang and found galaxies that looked like they had already been through all of that. Galaxies that looked old when the universe was still an infant. And that contradiction, that impossible, haunting contradiction, is what scientists had feared they might find but hoped they wouldn't. In the first year of Webb's scientific operations, a series of papers appeared in the astronomical literature that caused something close to a collective intake of breath among cosmologists. Researchers analyzing Webb's deep field images that captured thousands of galaxies and a patch of sky no larger than a grain of sand held at arm's length, found objects at redshifts of 8, 10, 12, 14, and beyond. A redshift is a measure of how much the universe has stretched the light from a distant object during the billions of years that light has spent traveling toward us. A redshift of 8 corresponds to a time when the universe was only about 650 million years old. A redshift of 14 corresponds to a time when the universe was barely 230 million years old, a sliver of cosmic time, a geological moment compared to the full sweep of cosmic history. And at these redshifts, Webb found galaxies, bright, massive, seemingly well-formed galaxies, that the standard model had not predicted. The discrepancy was not small. Some of the objects Webb detected appeared to be 10, to 100 times more massive than models allowed for that epoch. The question that immediately arose, the question that made careful scientists pause and less careful ones reach immediately for revolutionary proclamations, was not whether these objects were real. They were real. Webb's instruments are not in the business of manufacturing phantoms. The question was what their existence meant. It is worth pausing here to consider the nature of scientific fear. When a scientist says they feared a result, they do not mean it in the ordinary emotional sense, the quickening of the pulse, the cold sweat, the impulse to look away. Scientific fear is more nuanced than that. It is the anxiety that comes from having built something beautiful and then discovering evidence that it might need to be torn apart. It is the recognition that a beloved model, tested and refined over decades, might be insufficient. But it is also, if you listen carefully, tinged with something else, with excitement, because a result that breaks a model is not a defeat. It is an invitation. It is the universe whispering, patiently and without judgment, that there is more to understand. The scientists who built the standard cosmological model did not build it in the hope that it would be the last word. They built it in the hope that it would be a good enough word to get them to the next question. And Webb, it seems, has delivered the next question with extraordinary clarity. The machinery of Webb's vision is worth understanding, because it is extraordinary in itself, a feat of engineering so ambitious, so technically demanding that its successful deployment was, to those who had spent their careers waiting for it, something close to a miracle. The telescope had been in development for over 20 years, the subject of budget overruns and schedule delays and political battles that threatened more than once to kill it entirely. It had been launched on Christmas morning of 2021, carried into space by an Ariane 5 rocket from the Guiana Space Center on the northeastern coast of South America, and then had spent nearly 6 months unfolding itself, cooling itself, aligning itself, calibrating its instruments in the cold dark of the second Lagrange point, a gravitational equilibrium located 1.5 million kilometers from Earth on the side opposite the Sun. And then, in July of 2022, it began to see. What Webb can see that Hubble could not is, in the most literal sense, time itself. Because Webb observes primarily in the infrared, in wavelengths of light longer than what the human eye can detect, longer than the red end of the visible spectrum, it can see through the dust that obscures so many of the universe's most interesting regions. Stellar nurseries hidden behind vast clouds of interstellar gas and dust reveal themselves to Webb's instruments in stunning detail. But more than that, Webb can detect the infrared light that carries the signature of the universe's most ancient objects. When light travels through an expanding universe, it stretches. The expansion of space itself tugs at the wavelengths of light, pulling them apart, shifting them toward longer and longer wavelengths. By the time light from a galaxy at redshift 14 reaches us, it has been shifted so far toward the infrared that Hubble, a primarily optical telescope, could barely detect it. For Webb, it is, if not exactly visible, then at least accessible. And in that accessibility lies the ability to see things that have never before been seen by human eyes or human instruments. The mirror at Webb's heart is a marvel. 18 hexagonal segments of beryllium coated with a thin layer of gold. Gold, because gold is an extraordinary reflector of infrared light, each one adjustable to nanometer precision by tiny actuators that bend the mirror surface to the exact curvature needed to bring distant starlight to a perfect focus. The total mirror area is 6.5 square meters, more than 6 times the light-collecting area of Hubble. Behind the mirror sits the sun shield, a 5-layered structure the size of a tennis court, each layer coated with a reflective material that bounces sunlight away from the telescope. The sun shield reduces the temperature on the sun-facing side from roughly 85 degrees Celsius to minus 233 degrees Celsius on the telescope side, cold enough that the instruments can detect the faint infrared glow of objects billions of light years away without being blinded by the warmth of their own surroundings. Every aspect of Webb's design is a response to the extraordinary difficulty of seeing ancient, cold, redshifted light across unimaginable distances. And when you understand how hard it was to build, you begin to understand why what it found was so unexpected and so confronting. Let us speak of what the universe was expected to look like in those first few 100 million years. In the beginning, and that phrase carries a weight that no amount of scientific familiarity can entirely strip from it, the universe was an almost featureless sea of matter and energy, hot and dense and nearly uniform. Nearly, but not quite. There were tiny fluctuations in density, regions where the matter was infinitesimally more concentrated than elsewhere, seeds of future structure planted by the quantum fluctuations of the inflationary epoch that preceded the conventional Big Bang, stretched to cosmological scales by the explosive expansion of spacetime. Over the first few 100 million years, gravity amplified these fluctuations. Matter fell into the denser regions. The denser regions grew denser still. Eventually, in pockets of accumulating hydrogen and helium, the first stars were born, massive, violet, short-lived objects very different from our own sun, burning hot and bright and dying young, seeding the universe with the first heavy elements and the first photons energetic enough to ionize the surrounding intergalactic medium in a process called reionization, which gradually transformed the early universe from a fog of neutral hydrogen into the transparent, structured cosmos we inhabit today. In this picture, the first galaxies were expected to be small. They were expected to be irregular, lumpy, chaotic, the raw material of structure rather than structure itself. They were expected to be deficient in heavy elements, because heavy elements require generations of stellar evolution to produce, and the first generation of stars had barely begun its work. They were not expected to be the kinds of massive, luminous, chemically enriched objects that Webb was finding. They were not expected to look, in some cases, almost like the galaxies we see in the local universe today, the grand spirals and ellipticals that took billions of years to assemble. And yet there they were, bright and massive and seemingly composed, hanging in the oldest light Webb could reach, like a quiet challenge to everything the models had predicted. The reaction of the scientific community to Webb's early galaxy findings was fascinating to observe, because it illustrates something important about how science actually works, not the sanitized, linear narrative of textbooks, but the messy, contentious, exhilarating process of real inquiry. There were those who immediately reached for the most dramatic interpretation. The standard model is broken, Lambda-CDM is wrong, the Big Bang is in question. This interpretation made excellent headlines, but was immediately disputed by the majority of working cosmologists, who pointed out, quite correctly, that extraordinary claims require extraordinary evidence, and that there were several possible explanations for Webb's findings that did not require abandoning the entire edifice of modern cosmology. One possibility was that the galaxies Webb was seeing were intrinsically brighter than average, not necessarily more massive than models predicted, by containing more luminous objects per unit of mass, perhaps because star formation in the early universe was more efficient than assumed, concentrated into brief intense bursts that produced enormous amounts of light in short periods. Star formation efficiency, the fraction of a gas cloud's mass that actually ends up in stars before stellar feedback disperses the remaining gas, is one of the parameters in galaxy formation models that is most uncertain, because it depends on complex, small-scale physics that is difficult to simulate accurately. If early galaxies formed stars more efficiently than assumed, they would be brighter than models predicted without necessarily being more massive. This explanation is plausible. It is also, crucially, testable. Another possibility was that the mass estimates themselves were uncertain. Estimating the stellar mass of a distant galaxy from its observed light is not a simple calculation. It requires assumptions about the age distribution of the stars in the galaxy, the initial mass function, the statistical distribution of star masses, and the history of star formation, all of which affect how much light a given mass of stars produces. These assumptions introduce uncertainties that could, in principle, lead to overestimates of mass. Some researchers argued that the most extreme of Webb's early candidates, the objects that seemed most flagrantly at odds with the standard model, might upon closer inspection prove to be less anomalous than they first appeared. And in some cases, they were right. Follow-up spectroscopic observations, which measure the actual redshift of a galaxy by analyzing the precise wavelengths of its emission and absorption lines, rather than inferring it from the shape of its light curve, confirmed that some of the most dramatic candidates were indeed at the distances suggested by photometric estimates. Others were at lower redshifts than initially thought, which made them more consistent with standard predictions, but also less dramatic, and therefore less likely to appear in popular accounts of Webb's discoveries. But not all of Webb's early findings could be explained away. There remained a core of observations, a population of massive, luminous galaxies at high redshift, that even the most conservative analysis found difficult to fully accommodate within the standard picture. Not impossible, not definitively model-breaking, but difficult. Uncomfortable in the way that only genuinely anomalous data can be. And it was this discomfort, not the headlines about the Big Bang being wrong, which were always overblown, but the quieter, more persistent discomfort of working scientists confronting data that didn't quite fit, that represented the true significance of what Webb had found. There is something deeply human about the discomfort of a challenged model. We build our understanding of the world by constructing frameworks, mental architectures that organize our observations, connect our facts, give shape to our knowledge. And when new observations arrive that do not fit cleanly into those frameworks, we face a choice. We can modify the framework, add epicycles, adjust parameters, extend the model in ways that accommodate the new data while preserving the core structure. Or, if the modifications become sufficiently numerous and sufficiently awkward, we can abandon the framework entirely and begin the difficult, exhilarating work of constructing a new one. The history of science is full of both kinds of responses, and it is not always obvious in real time which kind of response is appropriate. Sometimes the anomaly is a signal that something deep is wrong. Sometimes it is a reminder that our models are always simplifications of a richer reality. The art of science is in learning to tell the difference, and in having the honesty to admit when you cannot. The Hubble tension is one of the places where the discomfort of challenged models had already been accumulating long before Webb arrived. The tension refers to a discrepancy between two independent measurements of the Hubble constant, the parameter that describes the current rate of expansion of the universe. Measured from the cosmic microwave background using the Planck satellite, the Hubble constant comes out to roughly 67 kilometers per second per megaparsec. Measured from the local universe using Cepheid variable stars and type Ia supernovae as distance indicators, the so-called cosmic distance ladder, it comes out to around 73 kilometers per second per megaparsec. These two numbers are not merely different. They are different in a way that cannot be accounted for by the known uncertainties in either measurement. The discrepancy is statistically significant, at the level of phi sigma, meaning there is roughly 1 chance in 3.5 million that it could be explained by random measurement error. Either one of the measurements is systematically wrong in a way that has not yet been identified, or the standard model is missing something. And one of the things Webb was expected to do was help resolve this tension by providing an independent check on the cosmic distance ladder, using its superior ability to detect and characterize Cepheid variables in distant galaxies. What Webb found, when it turned its gaze to the distance ladder, was both reassuring and troubling. It confirmed that the local measurements were not suffering from the specific systematic errors that some had hoped would explain the tension. The Cepheid distances Webb measured were consistent with those measured by Hubble, which meant the local value of the Hubble constant was robust, and therefore that the tension with the Planck value was real and not going away. The universe, it seemed, was expanding faster in the local measurements than in the global ones, and no one could fully explain why. Some cosmologists began to seriously entertain the possibility that something was genuinely wrong with the standard model at a fundamental level. Perhaps dark energy was not a constant, but a dynamical field that has evolved over time. Perhaps there was new physics in the early universe, an early dark energy component, perhaps, that slightly modified the expansion history in ways that affected the inferred value of the Hubble constant from the microwave background. Perhaps the equation of state of dark energy was not exactly -1, as the cosmological constant requires, but something slightly different that could produce the observed discrepancy. These were not crackpot ideas. They were serious proposals from serious scientists, published in peer-reviewed journals, seriously debated at conferences. The Hubble tension had elevated from an annoying discrepancy to a potential crack in the foundation of modern cosmology. And then Webb, while helping to characterize the distance ladder with unprecedented precision, also began to deliver its own set of uncomfortable findings about the nature of early galaxies, adding another layer of tension, another set of observations that were difficult but not impossible to explain to an already complicated picture. The combination of the Hubble tension and the early galaxy problem began to feel, to some cosmologists, like the accumulation of small clues that something larger was being missed, like the way, in detective fiction, a series of seemingly unrelated anomalies gradually resolves into the recognition of a pattern, a deeper logic that was always present but invisible until the right perspective was found. One of the specific findings that generated the most intense discussion was what some researchers began calling the problem of the cosmic titans. These were galaxies, several of them confirmed at high redshift by Webb spectroscopic instruments, that appeared to contain stellar masses comparable to or exceeding those of large present-day galaxies, at epochs when the universe was less than 1 billion years old. In the standard picture of hierarchical structure formation, galaxies grow primarily through mergers. Small galaxies merge to form larger ones, which merge again to form still larger ones, in a bottom-up process driven by the gravitational collapse of dark matter halos. This process takes time. There's a limit to how large a galaxy can grow by a given cosmic age, because there has been only so much time for mergers to occur, only so much time for dark matter halos to collapse and accrete matter. The cosmic titans seemed to be too large too soon. Not impossibly so, not in a way that definitively violated the mathematics of structure formation, but uncomfortably so. Enough to make careful scientists ask whether the assumptions built into their simulations were correct. Those simulations, vast computational endeavors that attempt to model the formation of cosmic structure from first principles, running on some of the world's most powerful supercomputers, have been refined and validated over decades to produce results consistent with the observed universe. But they have been calibrated and tested primarily against observations of the local universe and the moderately distant universe, the universe as it was when it was a few billion years old. Webb was probing territory that had never before been accessible to observation, and the simulations had never been tested against data from those earliest epochs. It was entirely possible that the simulations were wrong in their early universe behavior not because of any fundamental flaw in the underlying physics, but because of simplifying assumptions and numerical approximations that were acceptable for later epochs, but inadequate for the extreme conditions of the early universe. The question of whether early star formation was more efficient than assumed was one such assumption. The treatment of stellar feedback, the way radiation, stellar winds, and supernova explosions affect the surrounding gas and regulate or suppress star formation, was another. Small changes in these parameters could, in principle, produce significant changes in the predicted population of early massive galaxies. The theorists went to work. At the same time that astronomers were grappling with the early galaxy problem, Webb was delivering equally startling results on the question of the nature of the universe's first stars, the so-called population 3 stars, hypothetical objects whose existence was predicted by theory, but which had never been directly observed. Population 3 stars were expected to form from clouds of primordial gas containing only hydrogen, helium, and trace amounts of lithium, the elements produced in the first few minutes after the Big Bang, before any stellar nucleosynthesis had occurred. Without the heavier elements that serve as coolants in present-day star-forming regions, these primordial clouds would have been less efficient at radiating away the heat generated by gravitational collapse, which meant they would have fragmented less effectively and formed stars with much higher masses than typical present-day stars. The first stars may have been hundreds or even thousands of times more massive than the Sun, immensely luminous, burning hot and blue and ferociously, and dying young in cataclysmic explosions that enriched the surrounding gas with the first heavy elements and planted the seeds of future chemical complexity. What had not directly detected individual population 3 stars, they would be far too faint and far too distant for even Webb's extraordinary sensitivity. But it had detected what appeared to be their signatures, chemical fingerprints in the spectra of high redshift galaxies suggesting regions of extremely low metallicity, and in some cases, candidate objects whose spectral properties were consistent with the presence of very massive, hot stars of a type not seen in the local universe. The detection was not definitive. Interpreting spectra at these distances involves uncertainties and ambiguities that require careful analysis and often multiple observations. But the hints were there, tantalizing whispers of the universe's first luminous objects, dimly perceived through the noise of cosmic distance. What made these hints particularly interesting was their potential connection to another of Webb's major early findings, the unexpected prevalence of active galactic nuclei, supermassive black holes, in the act of consuming matter and radiating enormous amounts of energy in the early universe. In the Standard Model, supermassive black holes grow over cosmic time by the accretion of gas and by the mergers of smaller black holes. The black holes found at the centers of galaxies today, including the 4 million solar mass beast at the center of our own Milky Way, are the end products of billions of years of growth. Finding supermassive black holes in the early universe, when there had been little time for growth to occur, was therefore unexpected. And yet Webb found them, actively accreting black holes with masses of hundreds of millions, or even billions of solar masses at redshifts of 6, 7, 8, and beyond. Some of these objects, called quasars, had been detected before by earlier observatories, though typically only the most luminous, most extreme examples could be seen at such distances. Webb's greater sensitivity allowed it to detect less extreme examples, a more typical population of early black holes, and what it found was that these objects were more common, and had grown to larger sizes more quickly than the Standard Model comfortably predicted. The connection between population 3 stars and early supermassive black holes was speculative but intriguing. One hypothesis suggested that the most massive population 3 stars might have ended their lives not in conventional supernova explosions, but in a direct collapse to a black hole, bypassing the supernova phase entirely and producing relatively massive black hole seeds, a few hundred to a few thousand solar masses, that could then serve as the starting points for the rapid growth to supermassive scales. Another hypothesis invoked the direct collapse of massive primordial gas clouds, not mediated by stars at all, into so-called direct collapse black holes, which would begin their lives already at the 100,000 solar mass scale, and would have a significant head start in the race to become supermassive. These scenarios were already under consideration before Webb launched, and Webb's observations were beginning to provide data that could, in principle, distinguish between them, though definitively doing so would require many more observations over many more years. There is something almost vertiginous about contemplating these objects. Black holes contain billions of times the mass of our Sun, already assembled less than 1 billion years after the universe began. A black hole is not a thing in any ordinary sense. It is a region of space-time where gravity has become so intense that nothing, not matter, not light, not information, not time as we ordinarily experience it, can escape. The boundary of a black hole, the event horizon, is a surface of no return, a geometric feature of space-time rather than a physical surface, indivisible itself but detectable by its effects on nearby matter. Matter falling toward a black hole is compressed and heated to extreme temperatures, radiating light across the full electromagnetic spectrum before crossing the horizon and disappearing from the observable universe forever. The most massive black holes, surrounded by the richest accretion flows, outshine entire galaxies. That is what a quasar is, a black hole engine so powerful that its radiation overwhelms the combined light of hundreds of billions of stars. And Webb was finding these engines already running at full power in the universe's first few 100 million years. The question of how they got there so quickly is one of the most compelling open problems in modern astrophysics, and Webb's observations are both deepening the mystery and, slowly, beginning to illuminate its edges. The universe is under no obligation to be simple. This is one of the lessons that the history of science teaches, though it is a lesson that each generation of scientists must relearn for itself. Time after time, what has seemed like a complete and satisfying picture of reality has turned out to be an approximation, accurate within a certain domain, useful for a certain set of purposes, but ultimately insufficient for the deeper questions that always lurk beneath. Newtonian mechanics was not wrong. It remains extraordinarily useful for describing the motion of objects at everyday speeds and sizes. But it was incomplete, and Einstein's relativity revealed the incompleteness in a way that simultaneously resolved existing anomalies and opened new territories of understanding that Newton could not have imagined. Quantum mechanics was not wrong. It is the most precisely tested theory in the history of physics. But it is in tension with general relativity in ways that suggest both are approximations to a deeper theory that has not yet been found. The history of physics is a history of successive approximations, each one more accurate and more comprehensive than the last, each one revealing new depths of complexity that the previous picture had not even been able to frame as a question. There is no reason to think this process is complete. There is, in fact, every reason to think it is very far from complete. Webb's findings about the early universe can be seen in this light, not as evidence that modern cosmology is wrong, but as evidence that it is, as all good scientific theories eventually prove to be, incomplete. The Lambda-CDM model has been an extraordinary achievement. It successfully describes the large-scale structure of the universe, the temperature fluctuations of the cosmic microwave background, the abundances of light elements produced by Big Bang nucleosynthesis, the dynamics of galaxy clusters, the statistics of the galaxy distribution, a vast array of observational facts that no previous model had been able to account for. That is not nothing. That is, in fact, a very great deal. But if Webb is telling us that the model's predictions for the early universe are systematically off in certain respects, that massive galaxies assembled too quickly, that black holes grew too fast, that star formation was more efficient than assumed, then the model is incomplete, and the incompleteness is an opportunity. The nature of dark matter is one candidate source of that incompleteness. Dark matter, the invisible, non-luminous substance that constitutes about 27% of the total energy density of the universe, compared to the mere 5% contributed by ordinary visible matter, is one of the most important and least understood components of the cosmos. It was inferred from its gravitational effects, the rotation curves of galaxies, the velocities of galaxies and clusters, the gravitational lensing of background light, all point to the presence of far more mass than is visible. But despite decades of searching, no one has detected a dark matter particle in the laboratory. The most favored candidate, weakly interacting massive particles, or WIMPs, has evaded detection in increasingly sensitive experiments. Other candidates, axions, sterile neutrinos, primordial black holes, remain unconfirmed. The properties of dark matter that are built into the standard model, how it interacts with itself, how it clusters on small scales, how it influences the formation of the first structures, are assumed rather than measured, and different assumptions lead to different predictions about the early universe. If dark matter has properties that differ from the simplest assumptions, if it has some degree of self-interaction, for example, or if some fraction of it is warm rather than cold, meaning that it has a non-negligible velocity dispersion that prevents it from clustering on the smallest scales, then galaxy formation in the early universe could proceed differently than current models predict. The cosmic Titan's Webb is finding could, in principle, be a clue about the nature of dark matter as much as about the physics of star formation. Dark energy is another candidate source of incompleteness. The cosmological constant, the simplest form of dark energy, a fixed energy density associated with empty space, is in deep tension with fundamental physics. If you try to calculate the value of the cosmological constant from quantum field theory, you get a number that is either zero or enormous, depending on what assumptions you make, and neither of those numbers matches the observed value, which is tiny but non-zero. The cosmological constant problem is one of the deepest unsolved problems in theoretical physics, a gap between our two great theories, quantum mechanics and general relativity, that we do not know how to bridge. If dark energy is not a constant, but a dynamical field, an entity that evolves over time, perhaps approaching the cosmological constant value today, but having had a different value in the early universe, then the expansion history of the universe would be different from the Landau-CDM prediction, and the growth of structure could proceed at a different rate, potentially explaining some of what Webb is seeing. New observations from a different space mission, the Euclid satellite, launched in 2023, are expected to provide constraints on the evolution of dark energy over cosmic time. But Webb's data on high-redshift galaxies is already beginning to place limits on some models. There is a quality to the light from a very distant galaxy that is almost impossible to fully capture in words, but worth attempting. That light left its source billions of years ago, in some cases, more than 13 billion years ago, when the universe was young and different, and full of processes that no longer operate in the same way. For billions of years it traveled across expanding space, its wavelength stretching as the universe itself stretched, carrying information about conditions that no longer exist in the form in which they originally existed. The photons that Webb collects from a galaxy of redshift 12 were emitted when the universe was less than 400 million years old, when our own sun and solar system would not exist for another 9 billion years, when the Milky Way galaxy itself was barely beginning to assemble from smaller pieces. Those photons have been traveling for more than 13 billion years. They have crossed vast regions of empty space, been slightly bent by the gravitational fields of intervening matter, survived the entire subsequent history of cosmic evolution, and finally come to rest in Webb's gold-coated mirror, where they are counted by detectors sensitive enough to register individual photons, translated into digital signals, beamed to Earth, and eventually displayed on computer screens where human eyes can see them. There is something almost unbearably moving about that journey. Light from a world that no longer exists, from stars that burned and died billions of years before the Earth formed, carrying information across an almost incomprehensible gulf of space and time to be received by creatures who, barely a heartbeat ago in cosmic terms, were still learning to shape stone tools. The universe does not care whether we find it comprehensible. It does not arrange itself for our convenience or our comfort. But somehow, inexplicably, there is enough structure in the universe, enough mathematical regularity, enough pattern in the behavior of matter and energy, that we can, with sufficient ingenuity and patience and courage, learn to read it. And what we are learning to read, through Webb's extraordinary eyes, is a chapter of the cosmic story that has never before been accessible to any intelligence anywhere, as far as we know. Whatever the eventual interpretation of Webb's findings, whether they require modest adjustments to the standard model or something more radical, the fact that we can ask the question at all is itself a kind of miracle. Let us turn now to another of Webb's great confrontations with the unexpected, the study of exoplanet atmospheres. This is a domain in which Webb is not merely confirming or challenging existing models, but is opening entirely new territory, doing things that were, before its launch, not merely unprecedented but widely considered impossible with existing technology. The detection of exoplanet atmospheres is one of the hardest observational problems in all of astronomy. A planet is tiny compared to its host star, and the light from the planet, either reflected starlight or the planet's own thermal emission, is swamped by the overwhelming brightness of the star. Detecting the faint spectral signature of atmospheric gases in this context requires measurements of extraordinary precision and stability, sustained over long periods. Webb has managed to do it. Not for all exoplanets, not yet, but for a growing number of carefully chosen targets, primarily using the technique of transmission spectroscopy, in which the light of a star is measured as a planet passes in front of it. During the transit, starlight passes through the thin ring of the planet's atmosphere, and different gases in the atmosphere absorb different wavelengths of light, leaving distinctive fingerprints in the star's spectrum. By comparing the spectrum during transit to the spectrum outside of transit, astronomers can identify which molecules are present in the atmosphere. Webb's sensitivity in the infrared makes it exquisitely suited to this technique, because many of the most important atmospheric molecules, water, carbon dioxide, methane, ammonia, and others, have their strongest absorption features in the infrared. Within its first year of operations, Webb had already delivered results that stunned the exoplanet science community. The detection of carbon dioxide in the atmosphere of WASP 39b, a hot Jupiter, a gas giant orbiting very close to its star, was the first unambiguous detection of carbon dioxide in an exoplanet atmosphere, and it was accomplished with stunning clarity, not a marginal detection at the edge of statistical significance, but a prominent, unmistakable feature in this spectrum. What had done in a single transit what had taken Hubble and Spitzer years of combined effort to approach. And WASP-39b was merely the first. More followed. More atmospheres were characterized, more molecules detected, more constraints placed on the compositions and structures of worlds that no human will ever visit, but which we can now, in a meaningful sense, begin to know. The implications of Webb's atmospheric characterization capabilities extend far beyond the study of hot Jupiters, which are scientifically interesting but not directly relevant to questions about life. The target that has generated the most intense interest, the most debate, and the most carefully calibrated mixture of excitement and caution is a planet called K2-18b. This world, orbiting a red dwarf star about 120 light-years from Earth, is a so-called sub-Neptune, larger than Earth but smaller than Neptune, with a mass about 8.5 times that of our planet, belonging to a class of worlds that has no analog in our own solar system, and whose internal structure and composition are uncertain. K2-18b orbits in the habitable zone of its star, the range of distances at which liquid water could potentially exist on the surface, and had been previously detected to have water vapor in its atmosphere, a finding exciting enough in itself but qualified by the significant uncertainties inherent in pre-Webb spectroscopy. When Webb turned its instruments on K2-18b and analyzed its transmission spectrum, the results were remarkable and immediately controversial. The spectrum showed evidence of carbon dioxide and methane, the two molecules that, if found together in the right proportions in a planetary atmosphere, can be a biosignature, because photosynthesis produces both in ways that inorganic chemistry struggles to sustain. But more than that, there was a tentative suggestion, not a confident detection, but a statistically suggestive feature in the spectrum of dimethyl sulfide, or DMS. Dimethyl sulfide is a molecule produced on Earth primarily by marine microorganisms, particularly phytoplankton. It has no known abiotic source capable of producing it in detectable quantities. If its presence in the atmosphere of K2-18b were confirmed, it would be, to put it carefully, consistent with the presence of biological activity. It would not prove life. Science does not work in proofs. It would provide evidence, preliminary, suggestive, requiring extensive follow-up, that life might be present. The scientific community's response to the K2-18b results was a study in how astronomy handles its most consequential and most uncertain findings. The researchers who made the detection were meticulous in their language, repeatedly emphasizing the preliminary nature of the dimethyl sulfide signal, the need for additional observations, the various sources of uncertainty, the multiple alternative explanations that would need to be ruled out before any biological interpretation could be seriously entertained. The popular press was considerably less restrained. Headlines appeared around the world announcing the discovery of possible alien life, generating a wave of public excitement that the scientists involved felt compelled to repeatedly temper. This dynamic between the nuanced, probabilistic language of science and the binary, definitive language that the public and the media often demand is one of the perpetual challenges of communicating results at the edge of knowledge, where what exists is not certainty, but the asymptotic approach to it. What is unambiguously established about K2-18b is this: it is a world unlike anything in our solar system, orbiting in its star's habitable zone, with an atmosphere containing carbon dioxide and methane, consistent with being what theorists call a Hycean world, a planet with a hydrogen-rich atmosphere overlying a global ocean of liquid water. Whether that ocean exists, whether it is habitable, whether anything lives in it, these questions remain open. But the mere fact that we can ask them with genuine observational data, rather than pure speculation, is extraordinary. Before Webb, we could not have characterized K2-18b's atmosphere in enough detail to even formulate the question precisely. Now we are formulating it, debating it, designing follow-up observations to address it. The universe is not telling us its secrets willingly. It is making us work for them. But it is permitting the work to proceed. The implications of detecting life, even microbial life, beyond Earth would be almost impossible to overstate. It would represent the most profound discovery in the history of humanity, more significant than the Copernican revolution, which displaced our planet from the center of the cosmos, more significant than the Darwinian revolution, which connected us to the rest of life on Earth by the common thread of evolution. The discovery that life exists elsewhere would tell us something fundamental and definitive about the universe itself, that it is, in some deep sense, a living universe, that the chemistry of carbon and water and sunlight that produce life here is not a fluke, but a consequence of physical laws that operate everywhere, that we are not alone in the most profound sense of that word. It would also raise questions that we are not yet equipped to answer, about the frequency of life, the distribution of intelligence, the great silence that the absence of detected extraterrestrial civilizations has always seemed to imply. None of these questions would be answered by the detection of microbes in a Hycean ocean 120 light-years away. But they would all become more urgent. Webb's capabilities in this arena go beyond the search for biosignatures. The telescope is also deepening our understanding of how planetary systems form, how the raw material of young stellar systems is organized, how planets assemble from the disk of gas and dust around a forming star, how the composition of a planetary system is determined by conditions in the protoplanetary disk. Webb has been imaging protoplanetary disks around young stars with unprecedented clarity, revealing structures, gaps, rings, spirals, that betray the presence of forming planets, and providing constraints on the composition of the dust and ice from which planets and comets are built. These observations are relevant to understanding how our own solar system formed, and why it has the particular architecture it does, why the inner planets are rocky and the outer planets are gas and ice giants, why the asteroid belt occupies the space where a larger planet might have formed, why the comets that bombard the inner solar system carry the particular mix of organic molecules and water ice that they do. They are also relevant, more broadly, to understanding why some planetary systems might be hospitable to life and others might not. What factors favor the formation of rocky planets in habitable zones? What determines whether those planets end up with the right mix of elements and the right amount of water to support biology? Among the most haunting of Webb's early results were its images of nearby stellar nurseries, regions of our own galaxy where stars are being born right now, where the same processes that gave birth to our Sun 4.5 billion years ago are playing out before Webb's instruments in extraordinary detail. The Carina Nebula. The pillars of creation in the Eagle Nebula, already famous from Hubble's 1995 image, but now seen with a resolution and depth that transforms them from a beautiful photograph into a scientific document. The Tarantula Nebula in the Large Magellanic Cloud, the nearest example of a region of intense, vigorous star formation, a starburst region, producing stars at a rate far exceeding that of our more sedate Milky Way. These images are not merely beautiful, though they are among the most beautiful things that human instruments have ever produced. They are data. Every filament of gas, every glowing knot of material, every bright young star embedded in its natal cloud is telling us something about the process of stellar birth, about the conditions under which suns and their planetary systems come into existence, about the connection between what happened in the solar system's birth nebula 4.5 billion years ago and what is happening in these nurseries today. There is a continuity to the universe that is easy to miss amid the statistics and the models and the technical complexity of the observations. The carbon in the cells of your body was made in the core of a star that lived and died before the solar system formed. The oxygen you breathe was forged in stellar interiors and scattered by supernova explosions. The iron in your blood traces its origin to the violent deaths of massive stars, some of them, the most massive, in a kind of explosion so extreme that it briefly outshines an entire galaxy, a gamma-ray burst visible across most of the observable universe. You are made of the oldest material in the cosmos, organized by 4 billion years of evolution into a form capable of asking where it came from. And Webb, your instrument, is helping to answer that question not in the abstract but in the specific, naming the processes, quantifying the abundances, tracing the pathways that connect the Big Bang to the biology. This is what Sagan meant when he said, "We are star stuff." Not metaphorically, not poetically, chemically, physically, literally. The atoms that make up your body have a history that stretches back to the beginning of the universe, and that history involves stellar births and deaths, supernova explosions, interstellar chemistry, the formation and destruction of protoplanetary disks, billions of years of planetary geology, and 4 billion years of biological evolution. Webb is the instrument we have built to read the earliest chapters of that history. And what it is finding there, in those early chapters, in the universe's first few 100 million years, is changing our understanding not just of how galaxies formed but of how the universe became the kind of place where stars like the sun could form, where planets like the Earth could exist, where chemistry could become biology, where biology could become consciousness, where consciousness could build telescopes and point them at the sky. One of the chapters Webb is helping to write concerns the process of reionization, the transformation of the early universe from its neutral, opaque state to the transparent, ionized state that characterizes the cosmos we inhabit today. After the Big Bang, the universe expanded and cooled, and about 380,000 years in, it cooled enough for protons and electrons to combine into neutral hydrogen atoms, in a process misleadingly called recombination. From that point on, for several 100 million years, the universe was dark, filled with neutral hydrogen and helium, no stars yet formed, no sources of light, a period cosmologists call the cosmic dark ages. Then the first stars formed, and their ultraviolet radiation began to ionize the surrounding gas. The process of reionization, the progressive ionization of the intergalactic medium by the radiation of the first stars and the first galaxies, took several 100 million years to complete, and understanding its history and its drivers is one of the major open problems in cosmology. Webb is observing high redshift galaxies and quasars that probe the state of the intergalactic medium at different epochs during reionization, providing a census of when and how the process occurred. The neutral hydrogen in the intergalactic medium absorbs light at specific wavelengths, particularly the Lyman alpha wavelength of ultraviolet light, which is redshifted into the optical or infrared by the time it reaches us from high redshift. By studying the Lyman alpha emission from galaxies at different redshifts and the absorption patterns in quasar spectra, Webb is mapping the patchwork of ionized and neutral regions in the early universe, the cosmic bubble structure of reionization, as different galaxies created their own ionized bubbles that eventually merged into the continuous ionized sea of intergalactic space we see today. The picture that is emerging is consistent with the broad outlines of the standard model, but is revealing complexities and variations that the simple models had not captured, a richer, more spatially varied history of reionization than had been assumed. Among the most unexpected contributions Webb has made to our understanding of the universe has been in the domain of gravitational lensing. Massive objects, galaxies, galaxy clusters, concentrations of dark matter, bend the light that passes near them by virtue of their gravitational fields, in accordance with Einstein's general theory of relativity. This effect, gravitational lensing, can magnify and distort the images of background objects, acting as a natural telescope that amplifies the apparent brightness of distant sources and allows us to study them in more detail than would otherwise be possible. Galaxy clusters in particular can act as powerful lenses, producing spectacular arcs and rings in the images of background galaxies. Webb, with its superior sensitivity and angular resolution, has been able to use these natural lenses to study background galaxies at redshifts that would otherwise be too faint to observe, detecting objects in the universe's first few 100 million years that are too dim even for Webb to see without the boost of gravitational magnification. Some of the most dramatic of Webb's gravitational lensing images have revealed individual star clusters and even individual stellar nurseries within galaxies that existed over 13 billion years ago, a level of structural detail in early galaxies that had never before been accessible. These observations are beginning to answer questions about how stars formed in the earliest galaxies, whether they formed in massive clusters similar to the globular clusters we see today orbiting the Milky Way and other nearby galaxies, whether those clusters were responsible for the rapid buildup of stellar mass that Webb is finding, whether the globular clusters we see today and the halos of large galaxies are the survivors of a much larger population that formed in these early star-forming complexes. The connection between the ancient stellar clusters Webb is observing and the globular clusters still orbiting our own galaxy, some of which may be as old as the universe itself, is a thread that runs through cosmic history, connecting the primordial universe to our local cosmic neighborhood. There is a tendency, understandable but limiting, to think about cosmological discoveries in terms of what they tell us about things that are very far away and very long ago, things that seem remote from human experience, from the ordinary concerns of daily life, from the texture of the world we inhabit. But the discoveries Webb is making have implications that, followed carefully enough, bring us back to ourselves, to the question of why the universe is the kind of place that produces observers. The precise values of the physical constants, the strength of gravity, the mass of the electron, the fine structure constant that governs the strength of electromagnetic interactions, are such that they permit the existence of complex chemistry, of stars that burn for billions of years, of planetary systems, of the long geological and biological timescales over which evolution can operate. Change any of these constants by even a small fraction, and the universe becomes incompatible with the existence of complexity, of chemistry, of life. This observation, the anthropic observation, in its most careful form, is not a proof of anything, not a guarantee that the universe was designed for us, but it is a genuine puzzle. Why do the constants have the values they have? Is it chance? Is it selection? Do we inevitably find ourselves in a universe compatible with our existence, among a vast ensemble of universes with different constants? Is it something deeper, a physical principle we have not yet discovered? Webb is not designed to answer this question directly, but the early universe observations it is making, the constraints on galaxy formation, on the growth of black holes, on the reionization of the intergalactic medium, are all relevant to understanding the conditions under which planetary systems can form, in which life might have opportunity to arise. If massive galaxies assembled faster than expected in the early universe, then star formation was occurring more vigorously, more early, more widely than assumed, and the chemical enrichment of the universe, the seeding of galaxies with the heavy elements needed for rocky planets and biochemistry, may have proceeded faster than assumed as well. If the first black holes grew faster than expected, then the feedback they provided, the powerful outflows of matter and radiation that can suppress star formation in surrounding galaxies, was also operating earlier, with implications for the distribution of habitable environments across cosmic time and space. Every new piece of information what provides about the early universe is a piece of the puzzle of cosmic habitability, the question of when and where, across the 13.8 billion year history of the universe, conditions have existed that are compatible with the emergence of life. Our own place in this history is not at the beginning. We are not in the first generation of stars, which formed without the heavy elements needed for rocky planets and organic chemistry. We are not in the second generation, which formed from the ejecta of the first generation supernovae and began the long process of chemical enrichment. We are somewhere in the middle of the universe's story, in a galaxy that has been forming stars for 10 billion years, enriched by countless generations of stellar births and deaths, orbiting a sun that is itself a middle-aged star of the second or third stellar generation, on a planet that has had 4.5 billion years to evolve chemistry and biology. We are, in a sense, a product of cosmic timing, beings who could not have existed in the early universe that Webb is observing, because the universe was not yet ready for us, because the carbon and oxygen and iron and phosphorus that make us had not yet been forged, because the long slow work of stellar nucleosynthesis had not yet been done. We are late arrivals at a party that has been going on for billions of years, shaped by everything that happened before we arrived, inheritors of a cosmic history that we are only now beginning to read. What does it mean for a civilization to discover that the universe is older and larger and stranger than it had previously understood? History provides some guidance. Each great expansion of the known cosmos, from the Earth to the solar system, from the solar system to the Milky Way, from the Milky Way to the universe of galaxies, from the static universe to the expanding one, from the expansion to the acceleration, has been disorienting at first and liberating ultimately. The discovery that the universe is expanding, made by Hubble and Slipher in the 1920s, implied the existence of a beginning, the Big Bang, and thus a cosmic history of staggering depth, a story stretching back 13.8 billion years to conditions of extreme heat and density from which everything that exists emerged. The discovery that the expansion is accelerating, announced in 1998 on the basis of type Ia supernova observations, implied the existence of dark energy, a component of the universe that we do not understand, that has no counterpart in the physics of known particles and forces, that is currently dominating the dynamics of the cosmos, and driving all bound structures apart from one another on the largest scales. Each of these discoveries was initially received with skepticism, subjected to intense scrutiny, gradually accepted as the evidence accumulated. Each one changed not just our picture of the physical universe, but our sense of our own situation within it. Webb's findings are in the process of adding a new chapter to this history of expanding comprehension. The precise nature of that chapter is not yet clear. The observations are still young, the interpretation still contested, the follow-up still ongoing. But the outlines are beginning to emerge. We are learning that the early universe was more productive, more energetic, more structurally complex than we had supposed, that the formation of galaxies, stars, and black holes proceeded faster and more vigorously in the universe's first billion years than the standard model predicts. We are learning that the universe's chemical inventory was enriched with heavy elements earlier than expected, that the conditions for planetary formation and perhaps for life were in place earlier in cosmic history than we had assumed. We are learning that there may be new physics in the early universe, whether in the nature of dark matter, or dark energy, or star formation, or black hole growth, that our current models do not capture. These are not the discoveries of a failed cosmology. They are the discoveries of a successful one, a cosmology that has progressed to the point where it can be tested against the actual early universe, rather than merely extrapolated to it, and that is sophisticated enough to recognize when the tests reveal unexpected results. The Landis-EDM model has served us extraordinarily well. It will continue to serve us, in modified or extended or qualified form, as we absorb what Webb is teaching us. Science does not work by throwing away what works. It works by understanding where and why models fall short, and by building something better in those specific places. The history of physics is full of examples of this process. Newtonian mechanics subsumed into special relativity, classical electrodynamics into quantum electrodynamics, Newtonian gravity into general relativity, and in each case, the new theory contained the old one as a limiting case, valid in the domain where it had been tested but extended and corrected beyond that domain. The same process, surely, will play out in cosmology. What Webb is finding, in the end, is what science always finds when it gains access to a new domain of observation, that the universe is richer, more complex, more surprising than the models built to describe it. This is not a failure. It is the nature of the universe, inexhaustibly complex, endlessly surprising, responsive to every new instrument and every new question we bring to it. The universe does not run out of answers because we do not run out of questions, and we do not run out of questions because the universe does not run out of complexity. Webb has opened a window onto the universe's first billion years that was previously inaccessible, and what it has seen through that window has confirmed some things we thought we knew, challenged others, and revealed entirely new puzzles that previous generations of scientists could not even have formulated. That is what it means to have a great scientific instrument. That is what it means to look. The fear that scientists felt, and to use that word precisely, many did feel something that functioned as fear, was not the fear of being wrong. Scientists are accustomed to being wrong. The provisional nature of scientific knowledge is not a bug but a feature. It is precisely what allows science to correct its errors and converge on better descriptions of reality. The fear was more specific and more interesting than that. It was the fear of finding something that would be very hard to explain. Not impossible. Nothing the universe can show us is, in principle, impossible to explain eventually, but hard. Hard enough to require rethinking assumptions that had seemed secure. Hard enough to imply that the map of the early universe we had constructed was less accurate than we had believed. Hard enough to demand years or decades of new work before the picture became clear again. And that is precisely what Webb has delivered. Not a refutation, but a complication. Not an overthrow, but an enrichment. Not an answer, but a deeper question, which is always the most valuable thing a scientific instrument can provide. In the grand sweep of cosmic time, the human scientific enterprise is an infant. We have been doing systematic science, in anything like the modern sense, for perhaps 4 centuries. We have been building space-based observatories for 60 years. The James Webb Space Telescope, the most powerful of these observatories, has been operational for barely a few years. And in that brief time, it has already fundamentally altered our understanding of the early universe, opened the first real window onto the atmospheres of worlds beyond our solar system, and provided data that will be analyzed and debated and built upon for decades to come. What will it find in the next decade? What will we see when we turn its instruments on targets we have not yet chosen, when we apply analysis methods that have not yet been invented, when we integrate Webb's data with that from future observatories, the extremely large telescope on the ground, the Nancy Grace Roman Space Telescope, and the LISA Gravitational Wave Observatory in space, that will extend our reach in complementary ways? These are questions that cannot be answered in advance, and that is the point. The virtue of genuine discovery is its unpredictability. If we knew what Webb would find, we would not need to look. The universe has always been more interesting than our models of it. It has always had more to show us than we expected. And the scientists who built Webb, who spent 20 years designing it, fighting for it, waiting for it, and finally unleashing it on the universe, understood this. They built a machine for being surprised, for being educated, for being confronted with the beautiful, disconcerting, awe-inducing truth that the universe is older than our ideas about it, stranger than our models of it, and more generous with its mysteries than any previous generation of observers had been able to appreciate. There is a particular quality to the light that what collects, not just its age, not just its distance, but its relationship to us. That light was emitted by stars and gas clouds that never knew they would be observed. That light traveled for billions of years through a universe that had no conception of observation, no awareness of the beings who would eventually evolve on a small rocky planet around an ordinary star, and develop the technology to collect it and analyze it. The universe is not performing for us. It is not arranged for our comprehension. It simply is, in all its complexity and scale and indifference, and we are the part of it that has developed the capacity to notice. And in that noticing, in the centuries of patient observation and mathematical refinement and technological ambition that culminated in the deployment of Webb at the Lagrange point, in the quiet hum of its instruments collecting photons from the universe's first billion years, there is something that functions, if not as meaning, then as something adjacent to it. The universe has produced, in us, a mechanism for understanding itself. Whether that is a coincidence or a consequence, whether it is remarkable or inevitable, whether it should be called beautiful is a question that science, being honest about its limits, cannot answer. But science can tell you where the photons came from. And that, in the end, is no small thing. The most careful reading of Webb's early results leads not to despair, but to a kind of tempered wonder. Not the naive wonder of a universe that confirms our expectations, but the richer, more adult wonder of a universe that persistently exceeds them. The galaxies that should not yet exist, the black holes that grew too fast, the chemical signatures that hint at biology in distant atmospheres, the structures and protoplanetary disks, the pillars of creation revealed in new light, all of these are not problems with the universe. They are invitations. They are the universe's way of saying, "You are close, you have understood much, but there is more. Come further. Look harder. Ask better questions." The universe has never refused a sincere inquiry. It has only ever responded by revealing that the question we were asking was less interesting than the question we should have been asking, which is precisely the kind of response that keeps science alive and scientists humble and human curiosity from ever being satisfied. The James Webb Space Telescope will continue to observe for at least 10 more years, perhaps longer if its fuel supply allows. In that time, it will collect data that we cannot yet imagine using, answer questions that have not yet been formulated, and inevitably stumble upon findings that will, again, be feared and welcomed in equal measure by the community of scientists who have devoted their lives to understanding the cosmos. It will look deeper into the early universe than we have ever looked before, and it will find things there that will require us to think harder and differently about almost everything we believe we understand. That is not a threat. That is a promise. And it is the most generous promise the universe has ever made to the curious creatures who live on a pale blue dot in an ordinary galaxy in an unremarkable quarter of the observable universe, and who have had the extraordinary audacity to look. Consider for a moment the specificity of what is feared and what is found. Cosmologists feared, in the most technical sense, a violation of what they call the abundance matching relation, the statistical correspondence between the masses of dark matter halos and the stellar masses of the galaxies that form within them. This relation had been calibrated against observations of the relatively recent universe, and it encoded a set of assumptions about the efficiency of galaxy formation across cosmic time. If Webb found many massive galaxies at high redshift, those galaxies would require either abnormally large dark matter halos for their epoch, which would violate theoretical predictions about structure growth, or abnormally high efficiency of converting gas into stars within normal halos, which would violate assumptions about stellar feedback. Both options were uncomfortable. Both required explanation. Both pointed to gaps in our understanding of physics that we had not appreciated were there. The fear was not that the universe was misbehaving. It was that our description of its behavior was more limited than we had known. This is always the case, and it always will be. Every model is a simplification. Every theory is an approximation. Every observation is filtered through instruments with finite sensitivity and resolution and through minds with finite capacity for pattern recognition. Science proceeds by improving all three, by building better instruments, by developing more sophisticated theories, by training better scientists, and by accepting that the process of improvement is infinite, that there is no final theory and no ultimate observation, that the universe's complexity is, in practice, inexhaustible. What has made the next approximation possible? It has pushed the frontier of observation to the universe's first few 100 million years and found that, at that frontier, the story is richer and stranger than the version we told from behind the frontier. The next generation of observatories will push further, and the story will be richer still. This is not failure. This is science. This is the most remarkable, the most successful, the most self-correcting method for learning about reality that our species has ever devised, and it is working, and what it is learning is astonishing. We began with a door, with the image of a gold-plated mirror unfolding in the dark, with the moment when the sky ceases to be a ceiling and becomes a passage to something larger. Every great observatory in the history of astronomy has represented such a moment. Galileo's small telescope revealing the moons of Jupiter and the phases of Venus, Herschel's great reflector mapping the structure of the Milky Way, Hubble's telescope at Mount Wilson resolving the spiral nebulae into individual stars and establishing the scale of the universe, the Hubble Space Telescope delivering images of a depth and clarity that transformed our understanding of galaxy evolution. Webb is the latest in this lineage, and in some ways the most ambitious, the most technically demanding, the most scientifically transformative. It has not been in operation long enough for its full impact to be assessed. The most important discoveries it will make may not have been made yet. The anomalies it has found may be explained in ways that preserve the standard model, or they may require something new and deeper. We do not know. And in that not knowing, in that space of genuine uncertainty where the data are real, but the interpretation is contested, lies everything that makes science not just useful but beautiful. What Webb has found, in the end, is the universe as it is, rather than as we imagined it. And the universe as it is turns out to be, as it has always turned out to be, more complex and more interesting than the universe as we imagined it. The galaxies in Webb's deep fields do not care whether they were supposed to exist at that redshift. The black holes and the early universe did not consult our models before they grew. The carbon dioxide in the atmosphere of WASP 39b, the dimethyl sulfide hinted at in the spectrum of K2-18b, the young stars exploding from their birth nebulae in the Carina and the Tarantula, all of these are simply what the universe does, what it has always done, in the vast and indifferent and strangely generative space between the galaxies and the atoms, between the Big Bang and the heat death. between the first photon and the last. We are here, in the middle of it, briefly, and we have built an extraordinary machine to help us understand where we are. That machine is looking, and what it sees is, as it was always going to be, more than we expected, and less than there is to see, and enough to keep us looking for as long as we have the wisdom and the will to continue. The photons arrive. The detectors count them. The data streams to Earth. The scientists analyze and argue and refine. The picture clarifies, slowly, uncertainly, beautifully. And the universe, vast and ancient and indifferent, and somehow generative of all this wondering, continues its expansion into the dark, galaxies racing apart, the space between them stretching, the light of every galaxy redshifting toward wavelengths that will eventually exceed any instrument we could build, until the observable universe contracts to just the local group, until the stars burn out, until even the protons may eventually decay, until whatever comes after the era of matter replaces this era in the long, incomprehensible sequence of cosmic ages. We will not see that. Our civilization will not see it. Our species may not survive long enough for it to matter. But we are seeing this particular moment in the middle of the cosmic story, this particular chapter in which consciousness has emerged and built machines to read the light and learn to ask the questions that the light is, slowly, answering. And that, in the full context of cosmic time and cosmic scale, is not nothing. It is, if we are honest, everything. There is another dimension to Webb's contributions that has received somewhat less popular attention than the early galaxy problem or the exoplanet atmospheres, but that is in many ways equally transformative for our understanding of the universe's mill history, the long, productive, structurally rich era between the cosmic dawn and the present, spanning roughly from 1 billion to 10 billion years after the Big Bang. This is the era during which the universe was most actively forming stars, when the cosmic star formation rate density, the rate at which new stars were being born per unit volume of space, was at its historic peak, roughly 2 to 3 billion years after the Big Bang, and then gradually declining as the gas supply in galaxies was depleted and as the expanding universe diluted the density of material available for star formation. It is the era during which the Milky Way assembled most of its stars, during which the disk of our galaxy settled into its current orderly rotation, during which the chemical enrichment of the galaxy progressed through generation after generation of stellar birth and death to produce the particular mix of elements present in the solar system, when it formed 4.5 billion years ago. Understanding this era, understanding the mechanisms of galaxy growth and quenching, of metal enrichment and gas cycling, of the interplay between star formation and black hole activity, is one of the central problems of observational cosmology. There is a question so vast, so quietly devastating in its implications, that most people who stumble upon it find themselves standing very still for a moment, as though the ground beneath them has become uncertain. It is a question that arrives not with the thunder of great philosophical disputes, but with the soft, relentless pressure of a tide coming in. You think you are standing safely on the shore of understanding, and then the water is around your ankles, and then your knees, and then you realize that the shore itself was never as solid as you believed. The question is this: if the Big Bang created the universe, if that single, incomprehensible eruption of energy in space-time gave birth to everything that has ever existed, every atom in your body, every star in every galaxy, every thought you have ever had, then what, in all the depth of possible existence, created the Big Bang? It seems, at first, like a simple question. A child asks it. A philosopher asks it. A physicist, staring at equations at 3 a.m. with cold coffee growing a skin beside the keyboard, asks it. And the remarkable thing, the thing that should stop us all in our tracks and remind us how young and how brave and how beautifully confused our species is that we do not yet know the answer. We have theories. We have mathematics of extraordinary elegance. We have machines buried under mountains and stretched across continents, listening and measuring and recording. We have minds of singular brilliance devoted entirely to this pursuit. And still, the question stands, patient as the cosmos itself, waiting. To understand why this question is so profound, we must first sit with what we mean when we say the Big Bang. We must resist the temptation to think of it as an explosion in any conventional sense, the kind you might see in a film, a great fireball expanding outward into pre-existing darkness. That image, however vivid, is misleading in almost every important way. The Big Bang was not an explosion inside space. It was an explosion of space itself. There was no pre-existing void into which the universe expanded. There was no place outside the universe waiting to receive it. Space and time themselves were born in that first instant. The Big Bang was not something that happened in the universe. The universe was something that happened in the Big Bang. This distinction is not merely semantic. It is the pivot around which everything else turns. When we ask what came before the Big Bang, we are already in territory where the question itself may be malformed. The word before implies time. It assumes that time stretches backward without limit, like a river that must have its source somewhere upstream. But if time itself began at the Big Bang, if there is no upstream, no before, no earlier, then asking what came before the Big Bang is like asking what is north of the North Pole. The question uses language correctly. It is grammatically sound. And yet it does not point to anything that can meaningfully exist. Stephen Hawking, whose mind moved through the landscape of theoretical physics the way a hawk moves through air, described this with characteristic clarity. He proposed that the boundary condition of the universe is that it has no boundary. In his no-boundary proposal, developed with physicist James Hartle, time near the very beginning of the universe behaves differently from the time we experience now. In our everyday existence, and even in the cosmic present, time is a direction. It moves, it flows, it carries causality along with it. But in the extreme conditions of the universe's birth, Hawking and Hartle suggested time becomes more like space. It acquires an additional degree of freedom. And in this imaginary time, as Hawking called it, the universe has no singular beginning point, no moment of creation, no edge where something must have pushed it into existence. We must pause here, because imaginary time is one of those phrases that sound like poetry but is actually mathematics. In the formalism of quantum mechanics and general relativity, there is a technique in which time is treated as a complex number, rotated, in a sense, so that it takes on spatial character. This is not a metaphor. It is a mathematical tool that physicists use to perform certain calculations, a trick that sometimes reveals deep truths about the nature of things. When Hawking speaks of imaginary time, he is not suggesting that time is a dream or an illusion. He is pointing toward a possible description of reality in which the question of what came before becomes as empty as asking what is south of the South Pole when you are already at the southernmost point. And yet, for all its mathematical beauty, the Hartle-Hawking proposal is one answer among many. It is a hypothesis, not a settled fact. Science is not a collection of certainties handed down from authority. It is a process, a way of asking questions and testing answers, an ongoing negotiation between the human mind and the nature of reality. And the nature of reality, it turns out, is under no obligation to be simple, or comfortable, or comprehensible to creatures who evolved to find food on a savanna. Our brains are remarkable instruments, but they were not designed, by any process, to intuitively grasp the topology of space-time near a singularity. To go deeper into this question, we must confront the concept of a singularity itself. When physicists trace the history of the universe backward, when they run their equations in reverse, watching galaxies converge, matter condense, temperature rise, space contract, they arrive at a point where the equations break down. The density becomes infinite. The curvature of space-time becomes infinite. The temperature becomes infinite. And when a physical quantity becomes infinite in an equation, it is usually a sign not that infinity actually exists in nature, but that the theory being used has reached the edge of its validity, that something new and as yet unknown must take over. The singularity at the beginning of the universe is almost certainly not a real physical object. It is a sign, written in the language of mathematics, that our current understanding is incomplete. This incompleteness is not a failure. It is an invitation. It is the universe whispering, in the only language it knows, that there is more to discover. General relativity, Einstein's magnificent theory of gravity, of space-time curvature, of the large-scale structure of the cosmos, breaks down at the singularity. Quantum mechanics, the equally magnificent theory of the very small, of probability waves and uncertainty and the discrete nature of energy, also breaks down at the singularity, or rather, it has not yet been properly reconciled with general relativity in a way that will allow it to describe such extreme conditions. What we need, and what we do not yet fully possess, is a theory of quantum gravity, a framework that unifies the very large and the very small, that describes space-time itself as a quantum object, subject to the strange laws of uncertainty and superposition that govern electrons and photons and the foundations of matter. Several candidate theories exist. String theory is the most famous, perhaps the most ambitious, a framework in which the fundamental constituents of reality are not point particles but one-dimensional vibrating strings of energy, and in which extra dimensions of space, curled up at scales far too small for any current instrument to detect, give rise to all the forces and particles we observe. In string theory, there is no singularity at the Big Bang. The strings themselves, and the geometry they inhabit, prevent the infinite densities that appear in the classical equations. What happened at the very beginning is smeared out, in a sense, by the quantum nature of the strings, replaced by a finite but extraordinarily hot and dense state that physics can, in principle, describe. Then there is loop quantum gravity, a different approach that takes space-time itself and quantizes it, makes it granular, discrete, built from fundamental units of space and time at the Planck scale, that almost incomprehensibly small length of approximately 10 to the power of -35 meters where quantum effects become dominant. In loop quantum gravity, space is not continuous like a smooth fabric but pixelated, made of discrete loops and networks. And in this framework, the Big Bang is replaced by what some theorists call the Big Bounce. The universe did not begin from nothing. It contracted, a previous universe collapsing inward under its own gravity until it reached a minimum size set by the quantum of space, and then rebounded, expanding outward into the universe we inhabit today. The Big Bounce is a remarkable idea. It is the universe breathing, inhaling, holding for an eternity measured in the Planck time, and then exhaling in a great cosmic breath that we experience as the expansion of everything. In this picture, the question of what came before the Big Bang has an answer, and the answer is another universe, a predecessor cosmos, governed by the same laws, or perhaps by slightly different ones, which collapsed and gave birth to ours. And if one asks what came before the universe, the answer spirals backward to an infinite regress of bouncing universes, each arising from the collapse of its predecessor, none of them having a true beginning, none of them having a true end. There is something deeply satisfying about this picture, aesthetically and philosophically. It is a vision of the cosmos as fundamentally cyclical, echoing the intuitions of many ancient traditions, the Hindu concept of the kalpa, the great cosmic cycle of creation and dissolution, the Stoic ekpyrosis, the conflagration of the world followed by its rebirth, the universe as an eternal process rather than a finite event. But we must be careful not to confuse aesthetic satisfaction with physical truth. Nature, as we have learned again and again, does not arrange itself to please our sense of beauty or our desire for symmetry. It arranges itself according to principles that we are still learning to read. And so the Big Bounce remains a hypothesis, a beautiful and mathematically interesting one, but not yet confirmed by observation. The signature of a previous contracting universe might, in principle, be encoded in the cosmic microwave background radiation, that faint glow of ancient light that fills the universe in every direction, the afterglow of the hot, dense early cosmos, released when the universe was approximately 380,000 years old. Some physicists have searched the cosmic microwave background for patterns, for circles or other anomalies that might represent the imprint of a previous aeon. The results have been suggestive in moments, but not yet conclusive. The cosmos keeps its secrets with magnificent patience. We must now speak of another class of answers to our great question, answers that go by the name of eternal inflation. To understand eternal inflation, we must first understand ordinary inflation, which is itself one of the most extraordinary ideas in modern cosmology. In the early 1980s, physicist Alan Guth was working through the implications of some particle physics theories on the early universe and realized something remarkable. In the very first fractions of a second after the Big Bang, in an interval so brief it makes the word brief seem like an overstatement, roughly 10 to the power of negative 36 seconds, the universe may have undergone a period of exponential expansion, growing in size by a factor of at least 10 to the power of 26, possibly far more, in an almost instantaneous moment. This inflation, driven by a hypothetical field called the inflaton field temporarily in a high-energy false vacuum state, would explain several features of the universe that otherwise seem impossibly fine-tuned. It would explain why the cosmic microwave background is so extraordinarily uniform in temperature across regions of the sky that, without inflation, could never have been in contact with each other. They would have been causally disconnected, unable to exchange energy or information, and yet they arrived at the same temperature to better than 1 part in 10,000. Inflation solves this by saying that all those regions were once in contact, close together, before inflation stretched the universe to its current vast scale. Inflation also explains why the universe appears geometrically flat, why it does not curve back on itself or curve away from itself at detectable scales, why the total energy density of the cosmos sits so precisely at the critical value. And it explains the origin of the large-scale structure we observe, the galaxies and clusters and superclusters and cosmic filaments, by stretching quantum fluctuations in the inflaton field to macroscopic scales, seeing the density variations that gravity later amplified into the cosmic what we see today. But here is the remarkable extension. When physicists explored the mathematics of inflation in more detail, they found that inflation, once started, is extraordinarily difficult to stop everywhere at once. In most regions of an inflating universe, the inflaton field reaches the bottom of its potential and inflation ends, giving rise to a hot, dense universe like ours. But quantum fluctuations ensure that in some regions, the inflaton field is briefly kicked back up to its high-energy state. In those regions, inflation continues, and continues exponentially. The inflationary patch grows faster than inflation can end within it. New regions are constantly being created by inflation, even as other regions exit inflation and become universes like ours. This is eternal inflation. Once it begins, it never ends globally. The universe as a whole, the multiverse, is a perpetually inflating sea, from which bubble universes like ours constantly nucleate and expand, each one representing a region where inflation has ended and a hot Big Bang has occurred. In this picture, our Big Bang was not the beginning of everything. It was the local end of inflation in our particular bubble, a phase transition in a larger inflating background, a moment when the inflating field in our region finally settled into its low energy state and released its energy as the heat and radiation of our early universe. The eternal inflation picture is staggering in its implications. It suggests that our universe is one of an inconceivably large number of bubble universes, perhaps an infinite number, each one potentially with different physical constants, different laws of nature, different possibilities for the emergence of complexity and life. In some bubbles, the force of gravity might be slightly stronger, causing them to collapse before stars can form. In others, the electromagnetic force might be different, making chemistry impossible. In ours, the constants are what they are, and here we stand, contemplating the whole. There is a version of this picture that connects to string theory in a particularly elegant way. String theory, it turns out, does not predict a unique universe. It predicts an enormous landscape of possible universes. Estimates range from 10 to the power of 500 to much larger numbers, each corresponding to a different way the extra dimensions of string theory can be compactified, curled up at small scales. Each configuration produces different effective laws of physics in the large three-dimensional space we experience. By itself, this landscape seems like a failing of string theory, an embarrassment of riches that prevents any specific prediction. But combined with eternal inflation, it becomes something else entirely. If eternal inflation is constantly creating new bubble universes, and if string theory provides an enormous landscape of possible physical configurations, then eternal inflation might explore the entire landscape over cosmic time, randomly assigning physical constants to each new bubble as it nucleates. Our universe would be one particular patch in this vast exploration, one specific configuration among the nearly infinite possibilities, and we would find ourselves here not because these constants were designed for us, but because only in configurations like ours can stars form, planets form, chemistry happen, life arise, and minds emerge to ask questions about the whole. This is the anthropic principle in its most powerful form, not a design argument, but a selection effect. We are, in a sense, survivors of the multiverse lottery. We do not observe the universes with wrong constants because in those universes, there is no one to observe. The very fact of our existence selects for a universe capable of producing beings who can observe it. This is a profound and somewhat unsettling thought, because it suggests that certain properties of our universe may not have deep causal explanations. They may simply be the values that our particular bubble happened to receive from the random quantum processes of the inflating sea. The cosmological constant, the energy density of empty space, the mysterious dark energy driving the accelerating expansion of the universe, may be the value it is not because some deep principle required it, but because in bubbles where it is much larger, galaxies never form, and in bubbles where it is much smaller or negative, the universe collapses. We live in one of the habitable bubbles. But we are getting ahead of ourselves, in the way that minds exploring the edges of knowledge always do, pulled forward by the gravity of the questions. Let us step back and consider another possibility, one that does not invoke inflation or bouncing or multiverses, but asks an even more fundamental question. Why is there something rather than nothing? This question, articulated most famously by the philosopher Gottfried Wilhelm Leibniz in the 17th century, is perhaps the deepest question of all. Even if we could fully explain the Big Bang, even if we had a complete theory of quantum gravity that described the universe's emergence from a quantum state with perfect mathematical precision, we would still face this deeper puzzle. Why does anything exist at all? Why is there a universe governed by physical laws rather than pure emptiness? Why are there laws at all? The physicist Lawrence Krauss wrote a provocative book arguing that the universe could arise from nothing, from the quantum vacuum, spontaneously, to the well-understood processes of quantum field theory in which particles and antiparticles constantly pop into and out of existence. But Krauss's nothing is not the philosopher's nothing. His nothing is the quantum vacuum, a seething, dynamic, mathematically rich structure governed by physical laws. The philosopher's nothing is truly nothing. No space, no time, no laws, no mathematical structures, no possibility of anything. And the gap between those two nothings is, perhaps, the largest gap in all of human knowledge. The physicist Alexander Vilenkin proposed a specific mechanism by which the universe might have tunneled into existence from nothing, using the mathematics of quantum tunneling, the well-established quantum phenomenon by which particles pass through energy barriers that classical physics says they cannot cross. The Lincoln universe tunneled from a state of no space, no time, no matter, no energy, into a small, closed de Sitter space, and then inflated. The probability of this tunneling event is not zero in his calculation. And in an infinite void of nothing, any event with non-zero probability will eventually occur, given infinite time, but there is no time in nothing, or given, perhaps more precisely, that the absence of time does not prohibit the quantum event from occurring, the universe simply appears. There is something almost mystical about this picture, and yet it is written in the dry, precise language of tensor calculus and quantum field theory. The universe tunneling from nothing is not a supernatural event in Vilenkin's framework. It is an extrapolation of well-tested quantum principles into a domain where no experiment has ever gone. It is a leap of mathematical faith, supported by the remarkable effectiveness of quantum mechanics in every domain where it has been tested, and by the reasonable hope that a theory that works so brilliantly everywhere we can observe might continue to work in regimes we cannot. But hope, however reasonable, is not the same as knowledge. Let us consider the role of time more carefully, because time is the hidden protagonist of this entire story. When we ask what came before the Big Bang, we are implicitly assuming that time is like space, that you can move through it in any direction, that there is a past and a future and a present that slides between them, and that this structure extends infinitely in both directions. But we have known since Einstein that time is not like this. Time is deeply entangled with space. Time is affected by gravity. Time runs at different rates in different gravitational fields, a fact so well established that GPS satellites must correct for it, or their navigation would drift by kilometers per day. Time, in general relativity, is not a backdrop against which the universe plays out. Time is part of the universe, a dimension of the four-dimensional space-time fabric that the universe is. And if time is part of the universe, then asking what happened before the universe is asking what happened before time. It is possible, not certain, but genuinely possible, that this question has no answer, not because we lack the intelligence or the instruments to find one, but because the question itself is structurally empty, like asking for the color of a sound or the weight of a Wednesday. Language gives us the grammar to construct the sentence, but reality does not supply the referent. The concept of before requires time. Before the universe, there may simply be no time, and therefore no before. But here we must be careful about another assumption. one that is so deeply embedded in human thinking that we rarely notice it. We assume that time is one-dimensional, that it is a line, or at most a branching tree, with one direction called future and another called past. But in the exotic mathematics of quantum gravity, this need not be so. Some theories suggest that near the Planck scale, time may be as fuzzy and uncertain as position and momentum are in ordinary quantum mechanics. There may not be a single, well-defined sequence of events. There may not be a unique history stretching back to a unique moment of creation. The universe's past may be, in some deep and technical sense, a superposition of many histories, each with its own amplitude, and what we experience as the definite history of our cosmos may be the result of a quantum decoherence process, a selection from among many possible paths by the act of our existing in this particular present. Richard Feynman's path integral formulation of quantum mechanics gives us a way to think about this. In Feynman's approach, a particle does not follow a single path from one point to another. It follows all possible paths simultaneously, with each path contributing a complex amplitude to the final probability. The most probable path, the classical trajectory, is the one where nearby paths interfere constructively. Applied to the universe as a whole, in the quantum cosmology program pioneered by Hawking, Hartle, and others, this means the universe is described by a wave function, the wave function of the universe, a mathematical object that encodes the probability of every possible configuration of space and matter and energy. The universe does not have a single history. It has a quantum superposition of all possible histories, weighted by their probabilities. In this framework, asking what created the Big Bang is like asking which specific path a photon took on its way through a double slit. The photon did not take a specific path. It took all paths, and the interference of those paths produced a pattern on the screen. The universe did not begin with a single specific event caused by a single specific prior event. It began, or rather, it is, a quantum object, described by a wave function that assigns probabilities to various histories of origin and development. Our particular history, the one we observe and inhabit and wonder about, is one realization of that wave function, perhaps the most probable one given our existence as observers within it. This is not mysticism. It is the most careful application of our best physical theories to the hardest problem we know. But it is also profoundly incomplete. The wave function of the universe requires boundary conditions, rules about what states are allowed at the beginning. Hartle and Hawking proposed the no boundary condition, which we have already visited. The Lincoln proposed creation from nothing. Others have proposed different boundary conditions, each leading to different predictions about the large-scale properties of the universe we observe. And the question of which boundary condition, if any, is the correct one, is not yet settled. There is a school of thought that asks whether the laws of physics themselves require explanation. We have been assuming, throughout this conversation, that the universe arises from within a framework of physical laws, that the Big Bang happened because certain equations, the Einstein field equations, the Schrödinger equation, the standard model of particle physics, describe something real about nature and that nature follows them. But why do those particular equations describe reality? Why not different equations? Why does mathematics describe nature at all? This is what the physicist Eugene Wigner called the unreasonable effectiveness of mathematics, the mysterious and deep fact that abstract mathematical structures developed by human minds, often without any practical motivation, turn out to describe physical reality with uncanny precision. The physicist Max Tegmark has taken this thought to its logical extreme in what he calls the mathematical universe hypothesis. If mathematics describes physical reality so well, he asks, perhaps this is because physical reality is mathematical structure. Not that mathematics is a tool we use to describe the universe, but that the universe is a mathematical object, literally, not metaphorically. In Tegmark's view, all mathematically consistent structures exist physically. Our universe is one such structure, and the apparent fine-tuning of its constants is explained, as in the multiverse picture, by the fact that we can only find ourselves in structures capable of supporting our existence. If Tegmark is right, then asking what created the Big Bang is asking what created a particular mathematical structure. And the answer, in his framework, is that mathematical structures do not need to be created. They simply are. They exist in a realm of pure mathematical necessity, timeless and causeless, just as the number 7 does not need to be created and does not exist in time. Our universe's existence is no more mysterious and no less wondrous than the existence of the integers. This is either a profound illumination or a category error of cosmic proportions, perhaps both. We have been circling around a certain possibility without quite facing it directly. The possibility that the universe has no cause, that it simply exists, without antecedent, without explanation, without reason. This is philosophically unsatisfying to most human minds, because our minds evolved to find causes, to trace chains of causation, to ask why and to expect an answer. The universe as an uncaused fact is deeply uncomfortable. And yet, in logic, every chain of explanation must end somewhere. If we say God created the universe, we must ask what created God. If we say a parent universe created our universe, we must ask what created the parent universe. If we say mathematical structures exist timelessly, we must ask why there are mathematical structures rather than nothing. At some level, the explanatory chain must terminate in something that simply is, without further explanation. Perhaps the most honest thing we can say is that the universe is that terminal fact. Perhaps the universe is the thing that has no prior cause, the foundation upon which all other explanations rest. This is not intellectually satisfying, but intellectual satisfaction is not a reliable guide to truth. The universe does not owe us a story that feels complete. It offers us what it is, and our task is to understand it as best we can with the instruments and intelligence we have been given by the very processes we are trying to understand. There is something humbling and exhilarating in this situation. We are creatures of the Big Bang, assembled from elements forged in stellar furnaces, giving consciousness by 4 billion years of biological evolution, peering back through time with our telescopes and our mathematics, trying to understand where all of this came from. The atoms in our brains, the carbon, the oxygen, the nitrogen, the hydrogen, were present in the early universe, scattered through the cosmos in the first minutes after the Big Bang, drawn together over billions of years by gravity, cooked in stars, scattered by supernovae, gathered into planets, organized by chemistry and biology into nervous systems capable of self-reflection. We are the universe's way of asking about itself. We are the question and, perhaps someday, part of the answer. Consider for a moment the cosmic microwave background radiation, that faint glow at a temperature of 2.725 degrees above absolute zero that permeates all of space. This radiation is a photograph of the universe at 380,000 years of age, the oldest light we can directly observe, the surface beyond which the universe is opaque to photons. In this radiation, the Planck satellite and its predecessors have found tiny temperature fluctuations, variations of 1 part in 100,000, that encode the seeds of all the structure in the universe. Those fluctuations, we believe, were seeded by quantum processes during inflation, stretched to cosmological scales by the exponential expansion of the inflaton field. In the patterns of the cosmic microwave background, we are reading the quantum signature of the universe's birth. We are decoding, and the oldest light available to us, the fingerprints of processes that occurred at energies far beyond anything our particle accelerators can reach. And buried in that ancient light may be information about what came before. If the universe bounced from a previous contracting phase, there might be faint signatures, specific patterns, specific deviations from perfect Gaussian statistics, imprinted in the microwave background by the contracting phase before the bounce. If eternal inflation occurred, gravitational waves produced during inflation should have left a specific pattern of polarization in the microwave background, a swirling pattern called B-modes, whose amplitude would tell us the energy scale of inflation and constrain the models. Several experiments have searched for these primordial B-modes. The BISEC 2 experiment in 2014 announced their detection, a moment of tremendous excitement that turned out to be premature. The signal was contaminated by dust in the Milky Way. The search continues with new and more sensitive instruments because it detected primordial gravitational waves would be the most direct window yet into the physics of the universe's very first moments. We should also speak of the second law of thermodynamics, which is perhaps the most fundamental and least escapable law in all of physics. The second law says that entropy, the disorder, the number of possible arrangements of a system, tends to increase over time. Broken eggs do not spontaneously reassemble. Heat flows from hot bodies to cold bodies, never spontaneously in reverse. The arrow of time, the difference between past and future, the reason memories work in one direction and not the other, is fundamentally rooted in the second law. The past is remembered because it has lower entropy. The future is uncertain because entropy can only increase. Now here is a deep puzzle. The universe today is far from its maximum entropy state. There are stars burning with ordered nuclear energy, living organisms with extraordinarily low internal entropy, galaxies with structured spirals and bars and halos. All of this order exists because the early universe had very low entropy, because the Big Bang produced a universe in a state of remarkable, almost inexplicable order. If entropy must increase, then the early universe must have been in a very special, very low entropy state. And asking what created the Big Bang is, from a thermodynamic perspective, asking where that extraordinarily low entropy initial condition came from. The physicist Roger Penrose has spent decades thinking about this question and arrived at a striking answer in his conformal cyclic cosmology. Penrose proposes that our universe is one aeon in a sequence of eons, each aeon being a universe that begins in a hot, dense, low entropy state, expands for trillions upon trillions of years, and ends in a cold, dark, maximally entropic state dominated by black holes, which eventually evaporate away through Hawking radiation, leaving only photons and a few massless particles and a universe with no meaningful scale. Here is the crucial insight. In such a universe, without mass, conformal symmetry is restored, the laws of physics become scale invariant, and what looks like a maximally expanded cold infinite universe becomes, to a conformal transformation, mathematically equivalent to a new hot, dense Big Bang. The end of one aeon is the beginning of the next. The universe reindents itself, not through a bounce, but through a mathematical equivalence, an identity between extreme ends of the cosmic life cycle. Penrose's conformal cyclic cosmology makes specific predictions that are potentially testable. The black holes of the previous aeon should leave traces in our cosmic microwave background. Concentric rings of slightly different temperature variance, halos centered on the locations of major black hole mergers in the previous universe. Some researchers have reported finding such rings in the data. The statistical significance is debated. The history of cosmological data analysis is full of patterns that turn out to be noise, and also full of patterns that turn out to be real. We must hold these results with appropriate uncertainty, neither dismissing them nor celebrating them prematurely. Let us now take a step even further back and ask a question that physics has not traditionally considered its territory, but which may ultimately be unavoidable. Not just what came before the Big Bang, but why the universe is intelligible at all. Why does it follow laws? Why does it not behave randomly, chaotically, without pattern? The fact that the universe is mathematically describable, that it follows equations, that the same physical laws hold in distant galaxies billions of light years away, and billions of years in the past as they hold here and now in this moment. This lawfulness of nature is not something we can take for granted without explanation. Einstein said that the most incomprehensible thing about the universe is that it is comprehensible. He was not speaking mystically. He was pointing to something genuinely puzzling. The universe did not have to be this way. A universe of pure chaos, where anything could happen at any moment without rhyme or reason, is logically possible. And yet, we find ourselves in a universe where hydrogen atoms on the far side of the observable cosmos have the same spectral lines as hydrogen atoms in our laboratory, where the speed of light is the same everywhere and always, where the same equations that govern the motion of billiard balls on a table, suitably extended and modified, also govern the orbital mechanics of binary pulsars 1,000 light years away. This universality, this lawfulness, is one of the deepest mysteries of existence. Some physicists and philosophers argue that the laws of physics are themselves necessities, that they could not be otherwise, that any consistent mathematical universe must have something like the laws we observe. This view, sometimes called physical necessity, holds that the equations of nature are not arbitrary choices, but logical consequences of coherent existence. Others argue that the laws are contingent, that they happen to be this way, that other laws are genuinely possible, and that the question of why these laws holds is as legitimate and as open as the question of why there is something rather than nothing. The anthropic principle, in various forms, has been invoked to address this. If the laws were different, we would not be here to observe them. Our existence selects for law-governed universes with constants in the right range. But the anthropic principle, while logically valid, is not fully satisfying as an explanation. It tells us why we observe what we observe, but it does not tell us why there is a large collection of universes with different laws to select from. It pushes the question back one level. Why is there a multiverse? Why is there anything for selection to operate on? We are, at this point, approaching the edge of what physics can say and entering a borderland where physics, philosophy, and perhaps something else entirely must collaborate. The question of what created the Big Bang is, at its deepest level, not purely a scientific question. It is a question about the nature of existence itself, about why there is something rather than nothing, about whether existence requires cause or whether it simply is. Science can tell us an enormous amount about how the universe began, about the physical processes of the early moments, about the nature of inflation and quantum fluctuations, and the hot dense plasma of the first seconds. But the ultimate why, the reason there is a universe at all rather than absolute nothingness, may be beyond the reach of any physical theory, not because science is limited in principle, but because the question itself may not be the kind of question that has a physical answer. There is a tradition in physics that holds that the ultimate theory of everything, when and if we find it, will be unique, that there will be only one consistent, mathematically complete description of all of physical reality, and that this uniqueness will itself explain why the universe is as it is. John Archibald Wheeler, one of the most creative and provocative minds in 20th century physics, dreamed of a law without law, a universe that bootstraps itself into existence, where the laws of physics are not given from outside but emerge from the structure of the universe itself, where the universe participates in its own creation through the act of observation, in the language of quantum mechanics. Wheeler's vision was influenced by his deep engagement with quantum mechanics, particularly with the measurement problem, the puzzle of how the quantum superposition of possibilities collapses into a single definite reality when observed. In standard quantum mechanics, observation plays a fundamental role. The act of measurement selects one outcome from many possible ones. Wheeler extended this, provocatively and perhaps too boldly, to cosmology. In his participatory universe, observers are not passive recipients of a pre-existing reality. They are participants in bringing reality into being. The universe, in Wheeler's poetic formulation, is a self-excited circuit, a cosmic loop in which the universe gives rise to observers and observers give rise to the universe. This idea is controversial among physicists, for good reason. It seems to put the cart before the horse, to require observers in order to explain the universe that gave rise to observers. But Wheeler was gesturing towards something important, something that quantum mechanics genuinely does suggest, that at the most fundamental level, reality is not a collection of things with definite properties existing independently of all observation. Reality is a network of relationships, of interactions, of measurements, and the classical world of definite facts emerges from this quantum substrate to a process we do not yet fully understand. Let us consider the arrow of time once more, from a slightly different angle. The laws of physics, with one notable exception, are symmetric under time reversal. If you took a film of any physical process, an electron interacting with a photon, a proton decaying, two galaxies merging, and played it backwards, the reverse process would also be allowed by the laws of physics. And yet the world we observe is profoundly asymmetric in time. Eggs break but do not unbreak. Stars burn but do not unburn. Life ages but does not de-age. This asymmetry arises not from the fundamental laws, which are mostly time-symmetric, but from the initial conditions. The early universe was in a state of extraordinarily low entropy, and the second law tells us that entropy must increase, giving time its direction. But here is the puzzle. Why were the initial conditions of the universe so special? Why did the Big Bang produce a universe of low entropy rather than a universe already in its maximum entropy state? In a universe of maximum entropy, nothing interesting happens. There are no stars, no planets, no chemistry, no life. There is just a uniform lukewarm gas slowly spreading through an infinite space. The fact that we find ourselves in a universe of low entropy, a universe full of structure and complexity, and the dramatic processes of stellar evolution and galaxy formation and biological life, tells us that the Big Bang produced a very special initial state. Special in a way that seems to demand explanation. Penrose has calculated that the probability of the Big Bang producing the universe we observe, chosen at random from all possible initial states of equivalent energy, is approximately 1 in 10 to the power of 10 to the power of 123. This number is so incomprehensibly small that the universe's observed initial conditions cannot be the result of chance. Something must have constrained them, some physical principle or law that we have not yet identified, something that ensured or strongly favored the low entropy beginning that gave rise to everything we see. This constraint is sometimes called the past hypothesis, the assumption that the universe began in a state of low entropy, and its origin is one of the deepest open questions in physics and cosmology. Some theorists argue that quantum gravity will eventually provide the answer, that a correct theory of the quantum beginning of the universe will automatically produce the low entropy initial conditions, that the wave function of the universe with appropriate boundary conditions selects for the smooth, ordered beginning we observe. Others argue that the anthropic principle saves us again. Only in a low entropy universe can observers exist, so we should not be surprised to find ourselves in one. But this merely restates the question rather than answering it. We should spend some time with black holes, because black holes are intimately connected to the question of cosmic origins and may hold clues about what lies beyond the singularity. A black hole is a region of space-time where gravity is so intense that nothing, not light, not any signal, not any influence, can escape. At the center of every black hole, according to general relativity, lies a singularity, a point of infinite density and infinite curvature, similar in mathematical character to the singularity of the Big Bang, but reversed in time. A black hole singularity is in the future for anything that falls through the horizon. The Big Bang singularity was in the past of our universe. If quantum gravity resolves the singularity of the Big Bang, replaces the infinite density with a finite but very high density, a quantum gravity regime where the smooth classical spacetime breaks down into something more fundamental, it should also resolve the singularities inside black holes. In loop quantum gravity, models suggest that the singularity inside a black hole is replaced by a region of high but finite density, beyond which spacetime continues, potentially into a new region of spacetime. In some models, this new region has the character of a new expanding universe, what has been called a black hole bounce, analogous to the Big Bounce, where the collapsing matter inside a black hole reaches maximum density and then rebounds, creating a new space-time region that inflates outward on the other side of what was the singularity. This would mean that every black hole is, in some sense, a universe. That our universe was born from the collapse of matter inside a black hole in a parent universe. That the black holes forming in our universe are, right now, generating new baby universes, invisible to us behind their event horizons. This picture, sometimes called fecund universes or cosmological natural selection, was developed by Lee Smolin, who added to it an evolutionary twist. If the physical constants of each baby universe are slightly randomized relative to the parent universe, then universes that produce many black holes, because they have constants suitable for long-lived stars and gravitational collapse, will produce many offspring, and over cosmic generations, the population of universes will be dominated by those with constants that maximize black hole production. Our universe's constants, Smolin argues, are near the maximum for black hole production given the constraints of physics. This is a beautiful and audacious idea, applying the logic of natural selection to cosmology itself. It makes, in principle, testable predictions. If our constants are near the maximum for black hole production, then small changes to any constant should reduce the number of black holes our universe can form. Some physicists find this intriguing. Others are skeptical, both of the specific predictions and of the underlying mechanism. The transmittance of physical constants from parent to child universe is a conjecture without a detailed physical mechanism. But it is a conjecture that takes the form of a scientific hypothesis. It makes predictions that could, in principle, be tested, and that is a virtue. It is worth pausing to appreciate just how strange all of this is. We began with a question that seemed simple: what created the Big Bang? And we have arrived at visions of eternally inflating multiverses, universes that bounce, black holes that give birth to new cosmos, wave functions of the universe, imaginary time, mathematical structures existing without physical substrate, and the possibility that the question itself may be meaningless. The strangeness is not a failing of our theories. It is a reflection of the genuine strangeness of the universe at its foundations. Our everyday intuitions evolved to help us survive on the surface of a medium-sized planet orbiting a medium-sized star. They are beautifully calibrated for a world of rocks and rivers and predators and prey. They are not calibrated for the quantum gravity regime, for scales of space, and time billions of orders of magnitude smaller than anything we encounter in daily life. And yet we are using those same minds, expanded and sharpened by mathematics and experiment and centuries of accumulated insight, to reason about the deepest nature of reality. That we have come as far as we have is extraordinary. That there is so much further to go is the gift. Dark energy deserves a moment of our attention in this context, because it is one of the most profound mysteries of contemporary cosmology and may be connected to the question of cosmic origins in ways we have not fully understood. In 1998, two independent teams of astronomers studying distant type Ia supernovae as standard candles to measure the expansion history of the universe made a discovery that shocked the physics community. The expansion of the universe is accelerating. Galaxies are not just moving away from each other. They are moving away from each other faster and faster. Something, dark energy, they called it, a placeholder name for our ignorance, is pushing space itself apart, overcoming the gravitational attraction of all the matter in the universe at the largest scales. Dark energy constitutes approximately 68% of the total energy content of the universe. It is, in terms of energy, the dominant component of the cosmos. And we do not know what it is. The simplest explanation is that it is the energy of empty space, the cosmological constant that Einstein introduced and then abandoned, the zero-point energy of quantum fields permeating all of space-time. But when physicists calculate the expected value of this vacuum energy from quantum field theory, they get a number approximately 120 orders of magnitude larger than the observed value of the cosmological constant. This is the worst prediction in the history of science, a discrepancy so enormous that it suggests something fundamental is missing from our understanding. The cosmological constant problem is, in some ways, a new version of the question we have been asking all along. Why is the energy of empty space the value it is, rather than the value quantum field theory naively predicts? Why is it small enough to allow galaxies and stars and planets to form, but large enough to drive the late-time acceleration of the universe? The anthropic argument suggests that we should not be surprised by this value. If it were larger, structure would not form, and we would not be here. But the multiverse of string theory's landscape, if it exists, does provide a vast collection of possible values, and in combination with the anthropic selection principle, it may explain why we find ourselves in a universe with a cosmological constant in the habitable range. The relationship between dark energy and the universe's ultimate fate also carries echoes of the creation question. If dark energy is truly a cosmological constant, a fixed property of empty space that does not change with time, then the universe's expansion will accelerate forever. Over trillions of years, the galaxies beyond our local group will recede beyond the cosmic horizon, invisible to any future astronomer. Stars will burn out, one by one, over hundreds of trillions of years. Black holes will evaporate through Hawking radiation over incomprehensibly long timescales. And the universe will approach its maximum entropy heat death, a cold, dark, uniform, structureless expanse of photons and a few relic particles, expanding forever toward infinite dilution. In Penrose's conformal cyclic cosmology, this heat death is not the end but the doorway to a new beginning. In the eternal inflation picture, our universe's heat death is irrelevant to the vast inflating multiverse, which continues to generate new bubbles long after our local pocket has grown cold and still. In loop quantum cosmology, the universe might bounce again, though the specific conditions for a bounce in a cosmological constant-dominated universe are not yet clear. And in Tegmark's mathematical universe, each history, each mathematical structure that exists, plays out completely, timelessly, including ours, in its full length from the quantum beginning to the heat death at the end. There is a word that comes to mind when contemplating all of this, a word that the great scientists and the great poets have reached for across the centuries when confronted with the enormity of existence. The word is awe. It is not a very scientific word. It does not appear in equations. It cannot be measured or quantified or submitted to peer review. And yet, it is perhaps the most honest response to what we find when we look at the universe at its most fundamental level. Awe at the fact that the universe exists at all. Awe at its mathematical elegance, at the deep and beautiful laws that govern its behavior, from the quantum foam of the Planck scale to the large-scale structure of the cosmic web. Awe at the fact that from a hot, dense, undifferentiated beginning, the universe evolved over 13.8 billion years into something that includes consciousness, includes beings who can wonder, who can ask questions, who can build telescopes and particle accelerators and mathematics, and use them to peer back toward the beginning of time. Carl Sagan spoke often of the cosmos as something deeply personal, something we are part of rather than observers of. We are, he said, a way for the cosmos to know itself. This is not merely poetic. It is physically precise. The matter that makes up our bodies was forged in stellar nucleosynthesis, scattered by supernovae, gathered by gravity, organized by chemistry, shaped by evolution, and assembled over billions of years and countless generations into beings capable of self-reflection. We are the universe in a very real sense, looking at itself. And when we ask where the universe came from, when we trace the history of space-time back toward the singularity and peer into the quantum fog of the very first moments, we are the universe asking about its own origin. This creates a strange loop, a kind of cosmic recursion. The universe created conditions for life. Life created conditions for intelligence. Intelligence created conditions for science. Science is now asking how the universe came to exist. The questioner and the question are the same entity, separated only by the extraordinary distance of scale and time. We are singularities of awareness embedded in a universe that may or may not have arisen from a singularity of density and temperature. We are, in a very profound sense, the universe's way of asking about itself, and the question we are asking is, why am I here? The honest answer, the answer that respects both the power of human knowledge and its limits, is this: we do not know. We have extraordinary ideas, beautiful theories, suggestive mathematics, and preliminary observations. We have the Hartle-Hawking no-boundary proposal, eternal inflation, loop quantum cosmology, conformal cyclic cosmology, the multiverse landscape, the mathematical universe hypothesis, quantum tunneling from nothing, and a dozen other frameworks, each capturing something important, each incomplete in its own way. We are at the beginning of understanding, not the end. We are, in the history of cosmic self-knowledge, in the equivalent of the early days of astronomy, when people first realized that the wandering stars were not gods, but bodies moving in space according to laws that could be written down and understood. The fact that we do not know is not a reason for despair or for invoking explanations that lie outside the domain of physical inquiry. It is a reason for continued investigation, for building better telescopes and more sensitive detectors and more powerful computers and more powerful mathematics. The history of science is a history of questions that seemed unanswerable, yielding, slowly and sometimes subtly, to persistent and creative inquiry. The nature of the stars, the structure of matter, the origin of species, the mechanism of heredity, the large-scale structure of the universe, each of these seemed, at some point in history, to be beyond the reach of human knowledge. Each yielded, in time, to the patient application of the scientific method. The origin of the universe may yield too. It may not. There may be aspects of this question, the deepest aspects, the question of why there is anything at all, that lie permanently beyond the reach of any empirical science, that reside in the domain of metaphysics or mathematics or philosophy, or something we do not yet have a name for. But the boundary between the knowable and the unknowable is not fixed. Every generation has believed that certain questions were permanently beyond reach, and every generation has been proven partially wrong by the next. We should hold our confidence in the limits of human knowledge with appropriate humility. We should also acknowledge that the question we have been exploring, what created the Big Bang, is not merely academic. It is not just a puzzle for cosmologists and philosophers to argue about in seminars. It is the deepest possible expression of the human impulse to understand, the impulse that drives all of science and much of art and philosophy and religion. To ask where we came from, at the most fundamental level, is to ask who we are. It is to stand at the edge of the known and look into the dark beyond, not with fear, but with the peculiar, restless, insatiable curiosity that is perhaps the most defining characteristic of our species. There is a temptation, when facing a question of this magnitude, to retreat into the comfort of familiar frameworks, religious, philosophical, or scientific, and declare the question answered. But intellectual honesty requires that we resist this temptation. No existing framework fully answers the question of what created the Big Bang. Not the no-boundary proposal, which describes but does not fully explain the universe's quantum beginning. Not eternal inflation, which defers the question to the origin of the inflating background. Not the mathematical universe hypothesis, which reframes but does not eliminate the question of why mathematical structures exist. Not religion, which posits a creator and then faces the question of the creator's origin. Every answer at this level of depth gives birth to a new question, and the chain of new questions extends outward toward a horizon that recedes as we approach it. This recession of the horizon is not a failure of understanding. It is the nature of understanding itself at the edge of knowledge. The more we learn about the universe, the more we realize there is to learn. The more precisely we can describe the first moments of cosmic history, the more clearly we can see the questions that remain. This is not frustrating. It is glorious. It means that the universe is not small, not shallow, not exhausted by any finite investigation. It means that every answer is the beginning of a new adventure. The particle accelerators at CERN and elsewhere push our understanding of fundamental physics to energies of the order of tera-electron volts. The energies of the early universe, in the first tiny fractions of a second, reached energies of the order of 10 to the 19 giga-electron volts, the Planck energy, 16 orders of magnitude beyond what our most powerful accelerators can reach. We cannot recreate the conditions of the Big Bang in any laboratory we could realistically build. We must infer those conditions indirectly from the large-scale structure of the universe, from the cosmic microwave background, from the abundances of light elements synthesized in the first few minutes of cosmic history, from the theoretical frameworks that best fit all available data. This makes cosmology a uniquely challenging science. We cannot run the experiment multiple times. We have one universe to observe, one set of data, one cosmic history to reconstruct. We must be extraordinarily careful about confirmation bias, about the human tendency to see patterns in noise, about the temptation to believe beautiful theories without sufficient empirical support. The history of cosmology is full of beautiful theories that turn out to be wrong, or partially wrong, or right in unexpected ways. The steady-state theory, which held that the universe was eternal and unchanging, and that matter was continuously created to fill the voids left by expansion, was an elegant idea. It was wrong. The inflationary universe, introduced as an elegant solution to several cosmological puzzles, may be right. The evidence is suggestive, but not yet conclusive. Science advances through this interplay of beautiful ideas and brutal empirical testing. The brutality is not cruelty, it is necessity. Reality does not care about our theory's elegance. It cares only about what is true. And determining what is true about the very beginning of the universe is perhaps the hardest empirical challenge our species has ever faced. It is a challenge worthy of our best efforts, our most careful thinking, our most sensitive instruments, and our deepest humility. As we approach the closing of this exploration, it seems right to return to the question one more time, not in hopes of resolving it, but of holding it clearly. What created the Big Bang? The universe began 13.8 billion years ago in a state of extraordinary density and temperature, in the very early moments of which the physics we know breaks down. Before a certain moment, perhaps of the order of Planck time, we have no reliable physical description of what was happening. The universe may have tunneled into existence from nothing, in a quantum event with no prior cause. It may have bounced from a previous contracting phase, a predecessor universe, whose contraction seeded our expansion. It may be one of infinitely many bubbles in an eternally inflating multiverse, a local end to inflation in an inflating background without beginning. It may be one aeon in Penrose's conformal cyclic sequence, the child of a previous universe's cold final state. It may be one mathematical structure among all possible mathematical structures that simply are timelessly, in a platonic landscape of pure mathematics. Or, and this possibility must be held alongside the others, it may be something entirely different from any of these, something that no one has yet imagined, a framework so foreign to our current thinking that it will require a revolution in understanding comparable to the Copernican revolution, or the Darwinian revolution, or the quantum revolution. Such revolutions have happened before. They will happen again. The universe has surprised us before. It will surprise us again. What is certain, what the totality of human experience and human knowledge suggests with overwhelming force, is that the universe is real, that it is governed by comprehensible laws, and that the application of careful reasoning and empirical investigation to the question of its origin will yield, over time, insights that we cannot currently anticipate. The path from the burning question to the partial answer to the new and deeper question is the path of science, and it is a path of extraordinary beauty. We began, all those years ago in our collective history, by watching the stars and asking what they were. We have come so far. We have measured the composition of stars with spectroscopes, the distances to galaxies, with the period luminosity relation of Cepheid variables, the age of the universe from the cosmic microwave background, the nature of space-time from the motion of binary pulsars, the existence of gravitational waves from the merger of black holes a billion light years away. We have sent instruments into the outer solar system, listened to the radio murmur of distant quasars, mapped the large-scale structure of the cosmos in 3 dimensions across billions of light years. We have descended, in our imagination and our mathematics, to scales far smaller than any atom, to the Planck length where space and time themselves may cease to have meaning. We have ascended, in our telescopes and our theories, to scales far larger than any galaxy, to the topology of the universe as a whole. And through all of this, through every discovery and every revolution and every humbling correction, the fundamental question remains, still open, still vibrating with all the force of its original asking. What came before? What was the seed of everything? What is the ground of being? Why is there something rather than nothing? These are not questions that will be answered in a single paper, a single discovery, a single generation of scientists. They are questions that will accompany us into the future, growing richer and more precisely formulated as our knowledge grows, leading us always forward into deeper understanding and deeper mystery. There is a peace in this, if we allow ourselves to feel it. A peace in the recognition that the universe is larger than our ability to comprehend it, and that this largesse is not a reproach but an invitation. We are small by cosmic measures. We are brief by cosmic timescales. Our planet is a pale blue dot in the outer arm of an ordinary spiral galaxy in a universe of 2 trillion galaxies. And yet here we are, asking the deepest questions. Here we are, building instruments of extraordinary sensitivity to hear the faint echoes of the universe's birth. Here we are, writing equations that describe the curvature of space-time and the quantum properties of matter and the large-scale topology of the cosmos. This is remarkable. It is the most remarkable thing about the universe. Not its size, not its age, not its complexity, but the fact that it is produced, in at least one small corner of one ordinary galaxy, beings capable of wonder. Beings who ask not only how to survive, but how the universe began. Beings who look at the night sky and see not just darkness and distant fire, but depth and history and question. The question remains, what created the Big Bang? We do not know. And in not knowing, we are most ourselves, curious, humble, reaching, alive to the mystery of a universe that gave rise to us, and that we are only beginning to understand. The cosmos is not finished with its surprises, and we are not finished with our questions. The two facts together, the universe's inexhaustibility and our undying curiosity, are perhaps the most beautiful thing in all of existence. They are the guarantee that the conversation between mind and cosmos, this strange and magnificent conversation that began when the first human looked at the stars and wondered, will continue for as long as there are minds to ask and stars to answer. In the end, perhaps, the question is its own reward. Not because ignorance is acceptable, not because the search for knowledge is futile, but because the question of what created the Big Bang, the question of ultimate origins, of why existence exists, is the question that drives the deepest and most beautiful and most human of all enterprises, the attempt to understand where we came from and what we are. It is the question that has no final answer, or whose final answer is always the beginning of a deeper question. And perhaps that is exactly as it should be. Perhaps the universe is not a closed book waiting to be read, but an open conversation, an ongoing dialogue between the cosmos and the minds it has produced. A conversation that began with the first flash of cosmic fire 13.8 billion years ago and continues in this very moment, in the mind that holds this question, in the silence that follows every answer and gives birth to the next question. We are here. The universe is here. The question is here. And that is enough to sustain a species, and a civilization, and a science, for as long as the stars continue to burn. There is a photograph taken by a machine no human hand has ever touched, from a position in space no human eye has ever occupied, and in that photograph there is a smear of light so ancient that it began its journey toward us when the universe itself was still learning how to make stars. The light is faint. It is the color of rust and memory. It has traveled for more than 13 billion years across an expanding emptiness that has no center and no edge, and it has arrived, after all that impossible wandering, at a mirror made of gold, floating in the permanent shadow of a sunshield the size of a tennis court, at the second Lagrange point, approximately 1.5 million kilometers from the pale blue world, where a species of upright apes once looked at the night sky and asked the first and oldest question: what is all of this? And why is it here? And now, in the data encoded in that faint smear of rust-colored light, something has appeared that should not be there. Something that does not fit the equations. Something that, according to everything we thought we knew about the origin and architecture of reality, is not merely surprising but, in the quiet and devastating language of theoretical physics, impossible. The James Webb Space Telescope was not built to overthrow our understanding of the cosmos. It was built to refine it. It was designed to be the successor to Hubble, a more powerful eye, a deeper reach into the infrared spectrum, where the oldest light in the universe has been stretched by the expansion of space itself into wavelengths invisible to the human eye but readable by instruments of extraordinary sensitivity. The telescope was decades in the making. It survived budget overruns and political battles and engineering challenges that seemed, at times, insurmountable. Its primary mirror, 6.5 meters across, is composed of 18 hexagonal segments coated in a layer of gold so thin that if you gathered all of it together it would barely fill a teaspoon. And yet, that gold is precisely what allows the mirror to reflect infrared light with an efficiency that borders on the miraculous. When it launched on Christmas morning, 2021, aboard an Ariane 5 rocket from the European spaceport in Kourou, French Guiana, it carried with it not only the hopes of thousands of scientists and engineers, but also the weight of a question that humanity has been asking since before we had the language to frame it properly. Are we alone? Is the universe what we think it is? And is the story we have been telling ourselves about the beginning of everything actually true? For nearly a century, that story has been remarkably consistent. It goes something like this. Approximately 13.8 billion years ago, all of space, all of time, all of matter and energy, everything that would ever become a galaxy, or a star, or a planet, or a thought in a human mind, was compressed into a state of unimaginable density and temperature. Then, for reasons we do not fully understand, it expanded. Not into something, because there was no something for it to expand into. Space itself expanded. Time itself began. And from that initial condition of incomprehensible heat and density, the universe cooled, and as it cooled, the first particles formed, and those particles combined into the simplest atoms, hydrogen and helium, and those atoms drifted in vast clouds through the expanding darkness and gravity that most patient of forces pulled those clouds together, and the first stars ignited, and the first galaxies assembled themselves from the gravitational cooperation of billions of stars, and the heavier elements were forged in the nuclear furnaces of stellar cores and scattered into space by supernovae, and from those heavier elements new generations of stars formed, with disks of debris around them that coalesced into planets, and on at least one of those planets, in at least one of those solar systems, in at least one of those galaxies, chemistry became biology, and biology became consciousness. And consciousness looked up at the sky and began to wonder. This is the standard model of cosmology. It is called the Landesidium model, where lambda refers to the cosmological constant, the mysterious energy that is accelerating the expansion of the universe, and cesium stands for cold dark matter, the invisible substance that provides the gravitational scaffolding upon which galaxies are built. It is a model that has been tested and refined over decades. It is supported by multiple independent lines of evidence. The cosmic microwave background radiation, that faint afterglow of the Big Bang that fills every cubic centimeter of space with photons that have been cooling for 13.8 billion years, matches the predictions of the model to extraordinary precision. The observed abundances of hydrogen, helium, and lithium in the universe agree with the calculations of Big Bang nucleosynthesis. The large-scale distribution of galaxies, the way they cluster and form cosmic filaments and walls and voids, is consistent with the gravitational evolution of density fluctuations seeded in the earliest moments of cosmic history. By every measure we have devised, the model works. It is, without question, one of the greatest intellectual achievements of our species. And yet, the James Webb Space Telescope is now showing us things that the model did not predict. Galaxies that are too massive, too bright, too mature, too early. Galaxies that appear to have assembled themselves with a speed and efficiency that our equations say should not have been possible in the time available. Galaxies that existed when the universe was barely a few 100 million years old, which in cosmic terms is like finding a fully grown oak tree in a forest that was planted yesterday. And it is not just one galaxy. It is not an anomaly, a statistical fluke, an artifact of calibration or instrument error. It is a pattern. A persistent, growing, deeply uncomfortable pattern that is forcing some of the most careful and conservative minds in physics to whisper a sentence that, in the culture of science, carries the weight of a revolution. Something is wrong with the model. To understand why these observations are so disturbing, you need to understand what the universe was supposed to look like in its infancy. According to the Standard Model, the first few 100 million years after the Big Bang were a time of gradual assembly. The first stars, the so-called population 3 stars, were thought to be enormous, primitive, composed almost entirely of hydrogen and helium, burning hot and bright and dying young. These first stars would have enriched the surrounding gas with heavier elements, and from that enriched gas, the first small galaxies would have begun to form. These early galaxies were expected to be small, irregular, chaotic. They were supposed to be the building blocks from which larger galaxies would later be assembled through a long, slow process of mergers and accretion. The technical term for this is hierarchical structure formation, and it is one of the central predictions of the Landesidium model. Big galaxies are not born big. They grow big. They accumulate mass over billions of years by consuming smaller galaxies, by drawing in gas from the intergalactic medium, by the patient, incremental work of gravity operating across cosmic time. But what Webb is seeing does not look like that. What Webb is seeing, when it peers into the deepest infrared, when it captures the light that has been traveling since the universe was barely 300 or 400 million years old, is galaxies that look disturbingly mature. Galaxies with stellar masses of tens of billions of solar masses. Galaxies with well-defined structures, disk-like morphologies, even spiral arms. Galaxies that, by every visual and spectroscopic measure, appear to have been forming stars at rates that would require either far more raw material than should have been available or far more efficient star formation processes than we have ever observed in the local universe. These are not the small, irregular proto-galaxies that the model predicted. These are objects that look like they have been around for billions of years, but they exist at a time when the universe itself was less than 500 million years old. The first of these objects to attract widespread attention was a galaxy designated Glass Z13, detected in the Webb data within weeks of the telescope beginning its science operations in July 2022. Its redshift, a measure of how much the expansion of the universe has stretched its light, suggested that it existed when the universe was roughly 300 million years old. This was surprising but not yet alarming. Then came more. Source 93316. Jade's GSZ 13-0. And then, most dramatically, a set of galaxies identified in the SUR survey that appeared not only to be extremely distant, but also extremely massive, with stellar masses comparable to the Milky Way, which has had nearly 14 billion years to accumulate its stars. These galaxies appear to have done, in a few 100 million years, what our own galaxy took the entire history of the universe to accomplish. The reaction in the scientific community was a mixture of excitement and unease. Excitement because this is what telescopes are for, this is what science does, you build a better instrument, and you find things you did not expect, and those unexpected findings are how knowledge advances. But unease because the implications, if these observations are confirmed and their interpretation is correct, are profound. They suggest that either our understanding of how galaxies form is fundamentally incomplete, or our understanding of the early universe itself is wrong, or, most disturbingly, both. It is at this point that the Nobel laureate enters the story. And it is at this point that the conversation shifts from the careful, measured language of observational astronomy to something more radical, more unsettling, and infinitely more fascinating. Because when a scientist of sufficient stature and sufficient caution says publicly that the data is pointing toward the possibility that this may not be our universe, that the cosmos we inhabit may not operate according to the rules we have assumed, that the very foundations of our cosmological model may need to be rebuilt, the scientific world pays attention. Not because authority determines truth in science, it does not, but because when someone who has spent a lifetime building and testing and defending the standard model begins to question it, the evidence must be compelling indeed. The phrase itself is striking. This is not our universe. It does not mean that we have somehow slipped into an alternate reality, though the metaphor is tempting. What it means, in the precise and careful language of theoretical physics, is that the universe we are observing through the James Webb Space Telescope does not match the universe that our best mathematical models predict. The observed universe and the theoretical universe have diverged. And the divergence is not small. It is not a minor discrepancy that can be absorbed by adjusting a parameter or adding a correction term. It is a fundamental mismatch between what we expected to see and what we are actually seeing, and it strikes at the heart of our most basic assumptions about cosmic evolution. To appreciate the depth of this crisis, you must understand how deeply the Landau-CDM model is woven into the fabric of modern physics. It is not just a model of the universe. It is the model. It is the framework within which virtually all of modern cosmology operates. It connects the physics of the very small, the quantum fluctuations that seeded the structure of the universe, to the physics of the very large, the gravitational dynamics that govern the evolution of galaxies and galaxy clusters. It incorporates general relativity, Einstein's geometric description of gravity, as the governing theory of spacetime. It includes the physics of baryonic matter, the ordinary atoms that make up stars and planets and people. It includes dark matter, the mysterious substance that interacts with ordinary matter only through gravity, and whose existence is inferred from its gravitational effects on galaxies and the large-scale structure of the cosmos. And it includes dark energy, the even more mysterious force that is driving the accelerating expansion of the universe. Together, these components account for the total energy budget of the cosmos. Ordinary matter makes up about 5%, dark matter about 27%, dark energy about 68%. And this budget, this precise accounting of the cosmic inventory, is what allows cosmologists to run simulations of the universe, to start with the initial conditions encoded in the cosmic microwave background and evolve them forward in time using the laws of physics, and to predict what the universe should look like at every epoch of its history. The predictions of these simulations have been spectacularly successful. They predict the web-like structure of the cosmic filaments along which galaxies are arrayed. They predict the statistical properties of galaxy clusters. They predict the relationship between the mass of a galaxy and the mass of its central black hole. They predict the way in which galaxies evolve over time, growing from small irregular clumps into the grand spirals and giant ellipticals that populate the local universe. These successes have built an enormous amount of confidence in the model. And that confidence, which is entirely justified by the evidence, is precisely what makes the Webb observations so troubling. Because the model does not predict what Webb is seeing. The model says that galaxies that massive, that mature, that structurally organized should not exist at those redshifts. The model says that the universe at 300 million years of age should be a place of small, faint, irregular proto-galaxies, not a place where objects with tens of billions of solar masses are already shining with the confident luminosity of middle-aged galaxies. Let us pause here and consider the scale of what we are discussing. A galaxy with a stellar mass of 10 billion solar masses contains 10 billion stars, each of which is a nuclear furnace converting hydrogen into helium and, in its later stages, into the heavier elements that make up the periodic table. Each of those stars is embedded in a gravitational relationship with every other star in the galaxy. Each has its own history of formation, its own trajectory through the galaxy, its own eventual fate, whether as a white dwarf cooling quietly into darkness, a neutron star spinning in an electromagnetic fury, or a black hole swallowing light itself. And the galaxy as a whole has its own larger story, a story of gas flowing in from the intergalactic medium, of star formation regions lighting up like cities seen from orbit, of supernovae enriching the gas with heavier elements, of the central supermassive black hole growing by accretion, of the galaxy's dark matter halo providing the gravitational well within which all of this activity unfolds. To assemble such an object in a few 100 million years requires either an extraordinarily efficient process of star formation or an extraordinarily large reservoir of raw material, or both, and the Standard Model does not readily accommodate either possibility. There are, of course, less dramatic explanations. Science is cautious by nature, and the first response to any anomalous observation is always to question the observation itself. Are the redshifts correct? Could the photometric redshifts, which are estimated from the colors of the galaxies rather than from direct spectroscopic measurements, be wrong? This is a legitimate concern, because photometric redshifts are inherently less precise than spectroscopic ones, and there are known degeneracies in the relationship between galaxy colors and redshifts that can lead to misidentifications. A galaxy that appears to be at a redshift of 13 might actually be at a redshift of 5, which would place it at a much later epoch when the existence of a massive galaxy would be less surprising. Early on, this was the most commonly cited explanation for the Webb surprises. Wait for the spectroscopy, people said. The spectroscopy will sort it out. And spectroscopy has been done. Not for all of the candidate high redshift galaxies, but for a significant and growing number of them. And while some of the candidates have indeed turned out to be at lower redshifts than initially estimated, a substantial fraction have been confirmed. The redshifts are real. The galaxies are genuinely at the distances indicated by their colors. They genuinely existed when the universe was very young. And their stellar masses, while subject to some uncertainty depending on the assumptions made about stellar populations and dust and star formation histories, are genuinely large. Not all of them are as massive as the most dramatic early estimates suggested, but many of them are still massive enough to pose a serious challenge to the Standard Model. Another possibility is that the stellar mass estimates are wrong. The mass of a galaxy is not measured directly. It is inferred from the galaxy's luminosity and color, using models of stellar populations that predict how much light a given mass of stars should produce at different wavelengths. These models depend on assumptions about the initial mass function, the distribution of masses among newly formed stars, the metallicity of the stars, the amount and properties of dust, and the star formation history. If any of these assumptions are wrong, the inferred masses could be wrong too. Perhaps the early galaxies had a different initial mass function, skewed toward more massive stars that produce more light per unit of mass. This would mean that the galaxies appear more massive than they actually are. This is a plausible and important consideration, and it is actively being investigated. But even with generous adjustments to the stellar population models, many of the Webb galaxies remain uncomfortably massive. And then, there is the question of the galaxies' morphologies. It is not just their masses that are surprising. It is their shapes. Some of the earliest galaxies observed by Webb show remarkably organized structures. Disk-like morphologies. Bar structures. Features that, in the local universe, are associated with dynamically mature systems that have had time to settle into equilibrium. The presence of such structures at very high redshift suggests that these galaxies have been evolving for longer than the age of the universe at that epoch should allow, or that the processes of dynamical relaxation are faster than we thought, or that there is some other mechanism at work that we have not yet identified. It is the accumulation of all these surprises, the masses, the luminosities, the morphologies, the sheer number of unexpectedly mature galaxies at unexpectedly high redshifts, that has begun to shift the conversation from surprise to concern, and from concern to something approaching a genuine crisis of confidence in the Standard Model. And it is this crisis that has led some of the most prominent figures in physics to begin speaking publicly about the possibility that something fundamental may need to change. The universe, it turns out, may be trying to tell us something. And what it is trying to tell us may be more radical than anything we have heard since Edwin Hubble discovered that the nebulae were galaxies, and that the galaxies were receding, since Arno Penzias and Robert Wilson stumbled upon the cosmic microwave background radiation while trying to eliminate noise from a radio antenna, since the Supernova Cosmology Project and the High-Z Supernova Search Team independently discovered that the expansion of the universe is accelerating. Each of these discoveries reshaped our understanding of the cosmos in fundamental ways. Each required the abandonment of deeply held assumptions. Each was resisted before it was accepted. And each, in retrospect, seems obvious, as though the universe had been trying to tell us all along and we simply were not listening. What the universe may be trying to tell us now is that the story of its infancy, the story we have been telling for nearly a century, is incomplete at best and wrong at worst. And this is not a comfortable realization. It is one thing to discover a new planet, or a new type of star, or even a new force of nature. These are additions to the existing framework. They expand the map without redrawing it. But it is quite another thing to discover that the map itself is distorted, that the fundamental assumptions upon which it was drawn are flawed, that the coordinates themselves may be in error. This is what the Webb observations threaten to do. Not to add a new feature to the map of the cosmos, but to redraw the map entirely. Consider what it would mean if the Standard Model of cosmology requires fundamental revision. The Lavoisier model is not just a theory about galaxies and stars. It is a theory about the nature of space and time. It is built upon general relativity, which describes gravity as the curvature of spacetime caused by the presence of mass and energy. It incorporates the cosmological principle, the assumption that the universe is, on the largest scales, homogeneous and isotropic, the same in every direction and at every location. It assumes that the laws of physics are the same everywhere and at every time. It assumes that the initial conditions of the universe can be described by a set of cosmological parameters, the density of matter, the density of dark energy, the Hubble constant, the amplitude and spectral index of primordial fluctuations, that can be measured with increasing precision and that, once measured, determine the entire subsequent evolution of the cosmos. If the model needs to be revised, it is not just the story of galaxy formation that changes. It is potentially the story of everything. There are several directions that such a revision might take, and each of them is fascinating in its own way. One possibility is that the physics of the early universe is different from what we have assumed. Perhaps the dark energy that we observe today, the force that is driving the accelerating expansion of the universe, behaved differently in the early universe. Perhaps it was stronger, or perhaps it had a different equation of state, meaning that the relationship between its pressure and its density was different from what we observe locally. This could have altered the rate of expansion in the early universe, providing more time for structure formation than the standard model predicts, or it could have altered the growth rate of density perturbations, allowing galaxies to assemble more quickly. This is not a speculative fantasy. There are well-motivated theoretical frameworks, such as quintessence models and early dark energy models, that predict exactly this kind of behavior, and some of these models have been developed precisely to address tensions between the standard model and observational data that predate the Webb observations. Another possibility is that dark matter is not cold. In the standard model, dark matter is assumed to be composed of particles that are massive, slow-moving, and interact with ordinary matter only through gravity. This is what makes it cold. Cold dark matter forms structures from the bottom up, with small halos forming first and then merging into larger ones, the hierarchical structure formation that predicts the slow, gradual assembly of galaxies. But if dark matter has properties that differ from this assumption, if it is warm rather than cold, meaning its particles have higher velocities, or if it interacts with itself through some force other than gravity, or if it decays or annihilates over time, then the process of structure formation could be very different. Warm dark matter, for example, suppresses the formation of small-scale structures, which might seem like it would make the problem worse, but it could also lead to the earlier formation of larger structures by allowing the gravitational collapse to occur at larger scales more quickly. The details are complex and model-dependent, and the observational constraints on dark matter properties are tight, but there is room within the current data for alternatives to the simplest cold dark matter scenario. A third possibility, and perhaps the most radical, is that general relativity itself, the theory of gravity that underpins the entire standard model, may need to be modified on cosmological scales. Einstein's theory has been tested with extraordinary precision in the solar system and in binary pulsar systems, and, more recently, to the detection of gravitational waves from merging black holes and neutron stars. It has passed every test with flying colors. But all of these tests probe gravity on relatively small scales, from the scale of the solar system to the scale of individual galaxies, or galaxy clusters. On the scale of the universe as a whole, the scale on which cosmology operates, general relativity has been tested less directly. The evidence for dark matter and dark energy, which together make up 95% of the cosmic energy budget, is itself derived from the assumption that general relativity is correct on these scales. If gravity behaves differently at the largest scales, then the need for dark matter and dark energy might be reduced or eliminated, and the predictions for structure formation in the early universe could be very different. This is not a new idea. Modified gravity theories, such as modified Newtonian dynamics, and its relativistic extensions, have been proposed and debated for decades. They have had some notable successes, particularly in explaining the rotation curves of galaxies without invoking dark matter, and some notable failures, particularly in explaining the dynamics of galaxy clusters and the properties of the cosmic microwave background. But the landscape of modified gravity theories has expanded considerably in recent years, with new proposals that attempt to reconcile the successes of general relativity on small scales with possible modifications on cosmological scales. The Webb observations, if they cannot be accommodated within the standard Landau-CDM framework, could provide powerful new motivation for taking these alternatives seriously. And then, there is the possibility that the answer lies not in changing the fundamental physics, but in changing our understanding of how galaxies form. Perhaps the processes of star formation and galaxy assembly in the early universe were qualitatively different from what we observe in the local universe. Perhaps the first generation of stars was more massive, more luminous, and more efficiently produced than our current models assume. Perhaps the feedback processes, the ways in which stars and supernovae and black holes inject energy into the surrounding gas and regulate future star formation, were different in the dense, metal-poor environment of the early universe. Perhaps there were mechanisms of galaxy growth that operated in the early universe but have since ceased, processes that could rapidly assemble large quantities of stellar mass in ways that do not occur in the more diffuse and metal-enriched environment of the present-day cosmos. These are not fundamental revisions to physics. They are revisions to astrophysics, to our understanding of the complex, nonlinear processes by which the raw materials of the universe are transformed into the organized structures that populate it. And they may be sufficient to explain the Webb observations without requiring changes to the underlying cosmological model. The honest answer, the answer that any careful scientist would give if pressed, is that we do not yet know which of these possibilities is correct. We may need more data. We almost certainly need more spectroscopic confirmations of high redshift galaxies. We need better models of stellar populations in the early universe. We need improved simulations that can explore the consequences of different assumptions about dark matter, dark energy, and the physics of galaxy formation. We need time, and we need patience, and we need the willingness to follow the evidence wherever it leads, even if it leads to places we did not expect and did not want to go. But the mere fact that these questions are being asked, the mere fact that serious scientists are seriously considering the possibility that the standard model of cosmology may be fundamentally flawed, is itself a momentous development. It is a reminder that science is not a collection of settled truths, but an ongoing process of inquiry, a conversation between the human mind and the natural world that is never finished, never complete, always open to revision in the light of new evidence. The standard model of cosmology is not a scripture. It is a hypothesis, the best hypothesis we have been able to construct given the evidence available to us, and it has served us extraordinarily well. But no hypothesis is sacred. No model is immune to the challenge of data. And the data from the James Webb Space Telescope is issuing that challenge with a clarity and an insistence that cannot be ignored. Let us return to the telescope itself, because there is something almost poetic about the instrument that is delivering these revelations. The James Webb Space Telescope is, in a very real sense, a time machine. It does not transport us physically into the past, but it allows us to see the past, to observe the universe as it was billions of years ago, because the light that reaches its mirror has been traveling for billions of years. When Webb observes a galaxy at a redshift of 13, it is seeing the galaxy as it was approximately 13.4 billion years ago, when the universe was roughly 330 million years old. The photons that Webb captures from such a galaxy have been traveling through space since before the Earth existed, since before the Sun existed, since before the Milky Way had assembled itself into its present form. Those photons left their source in a universe that was denser, hotter, and smaller than the universe we inhabit today, a universe in which the cosmic microwave background radiation was not the faint, cool whisper it is now, but a warm bath of light filling all of space, a universe in which the first atoms had only recently become transparent to radiation and the first stars were just beginning to ignite. To capture those photons, would had to be placed in one of the coldest and darkest environments accessible to human engineering. It orbits the L2 Lagrange point, a gravitational equilibrium point where the combined pull of the Sun and Earth allows the telescope to maintain a stable position with minimal expenditure of fuel. At L2, Webb is always in the shadow of the Earth, as seen from the Sun, and its sun shield, a 5-layered structure of aluminized and silicon-coated cactin, keeps the telescope's instruments at a temperature of approximately minus 233 degrees Celsius, just 40 degrees above absolute zero. At these temperatures, the telescope's own thermal radiation is minimized, allowing it to detect the faint infrared light of the most distant objects in the universe without being blinded by its own heat. The instruments aboard Webb are marvels of engineering. The near-infrared camera, or NIRCam, captures images at wavelengths from 0.6 to 5 microns, covering the range where the light of the most distant galaxies is found. The near-infrared spectrograph, NIRSpec, can obtain spectra of up to 100 objects simultaneously, dissecting their light into its component wavelengths and revealing the chemical composition, temperature, density, and velocity of the emitting gas. The mid-infrared instrument, MIRI, extends Webb's vision to wavelengths up to 28 microns, probing the dusty regions where stars are born and the cold debris disks around other stars where planets may be forming. And the fine guidance sensor, a near-infrared imager and slitless spectrograph, FGS NIRIS, provides precise pointing and additional spectroscopic capabilities. Together, these instruments give Webb a view of the infrared universe that is not merely better than anything that has come before but qualitatively different, a view that reveals structures and processes that were previously invisible to us. It is this qualitative difference that makes the Webb observations so significant. Previous infrared telescopes, including the Spitzer Space Telescope and ground-based facilities with adaptive optics, had hinted at the existence of unexpectedly massive galaxies at high redshifts. But their resolution and sensitivity were limited, and the hints remained ambiguous. Webb has removed that ambiguity. Its sharper vision and deeper reach have turned hints into confirmations, suggestions into data, possibilities into facts. And the facts, as they accumulate, are painting a picture of the early universe that is more complex, more dynamic, and more mysterious than anyone expected. The galaxies that Webb is finding at high redshifts are not just massive. They are also, in many cases, remarkably bright. Their luminosities, the total amount of light they emit, are in some cases comparable to or greater than the most luminous galaxies in the local universe. This brightness implies intense star formation, with stars being produced at rates of hundreds or even thousands of solar masses per year. For comparison, the Milky Way currently produces new stars at a rate of roughly 1 to 3 solar masses per year. The star formation rates implied by the Webb observations are so extreme that they raise questions about the availability of gas in the early universe. Where did all that material come from? How was it assembled so quickly? And how were the conditions in the early universe so favorable for star formation on such a dramatic scale? One clue comes from the spectra of some of these early galaxies, which show signatures of active galactic nuclei, supermassive black holes at the centers of the galaxies that are actively accreting matter and producing enormous amounts of energy. The presence of active galactic nuclei at such early times is itself remarkable, because forming a supermassive black hole, an object with a mass of millions or billions of times that of the Sun, requires either a very long time or a very efficient formation mechanism. In the standard picture, supermassive black holes grow from smaller seed black holes through a process of accretion, gradually consuming gas and merging with other black holes over hundreds of millions or billions of years. But if supermassive black holes are already present and actively accreting in galaxies that existed when the universe was only a few 100 million years old, then the seeds must have been planted very early and must have grown very quickly. This has led to renewed interest in the idea of direct collapse black holes, massive black holes that form not from the collapse of individual stars, but from the direct gravitational collapse of enormous clouds of gas in the early universe, bypassing the intermediate stage of stellar formation entirely. Such objects could provide the seeds from which supermassive black holes grow, and they could form much more quickly than the conventional stellar remnant pathway allows. The active galactic nuclei also contribute to the luminosity of the early galaxies, which complicates the interpretation of their stellar masses. Some of the light attributed to stars may actually be coming from the accretion disk around the central black hole, which would mean that the stellar mass estimates are too high. This is an important caveat, and it is being actively investigated. But even accounting for this contamination, many of the early galaxies remain uncomfortably massive. There is another aspect of the Webb discoveries that has received less public attention, but is equally important scientifically. It concerns not the most massive galaxies, but the most numerous ones. Webb has revealed that the number density of galaxies at high redshifts, the number of galaxies per unit volume of space, is significantly higher than the standard model predicts. This is not just a matter of finding a few unexpectedly massive outliers. It is a matter of finding too many galaxies of all masses. The luminosity function, which describes the distribution of galaxy luminosities at a given epoch, is shifted toward brighter values at high redshifts compared to the model predictions. There are more bright galaxies and more galaxies in total than there should be. This excess is present across a range of redshifts, from roughly redshift 6 to redshift 14, and it becomes more pronounced at the highest redshifts, where the discrepancy between observations and predictions is the largest. This excess in the galaxy number density is, in some ways, an even more robust challenge to the standard model than the existence of individual massive galaxies. Individual massive galaxies could be explained as rare statistical fluctuations, objects that formed in the most overdense regions of the early universe, where the conditions for rapid galaxy assembly were exceptionally favorable. But a systematic excess in the number density of galaxies across a wide range of luminosities and redshifts is harder to explain as a fluctuation. It suggests that the overall process of galaxy formation in the early universe was more efficient than the model predicts, not just in extreme environments, but everywhere. This brings us back to the question of what, exactly, is wrong. Is it the cosmology or the astrophysics? Is the problem with the fundamental physics that governs the expansion and evolution of the universe? Or is it with our understanding of the complex baryonic processes that determine how galaxies form and evolve within the cosmic framework? This is a crucial distinction, because the implications of the two possibilities are very different. If the problem is with the astrophysics, then we need better models of star formation, feedback, and galaxy assembly, but the underlying cosmological framework remains intact. If the problem is with the cosmology, then we may need to revise our understanding of the fundamental forces and components that shape the universe. The evidence, as it currently stands, does not definitively favor one possibility over the other. There are astrophysical models that can accommodate some of the Webb observations without changing the cosmology. For example, models in which the initial mass function in the early universe was top-heavy, meaning that a larger fraction of newly formed stars were very massive, can produce more light per unit of stellar mass and thus reconcile the observed luminosities with lower stellar masses. Models in which star formation in the early universe was more bursty, with intense episodes of star formation separated by periods of relative quiescence, can also help, because the observed luminosities reflect only the instantaneous star formation rate, not the time average rate. And models in which the feedback from supernovae and active galactic nuclei was less effective at suppressing star formation in the early universe, perhaps because the gas was denser and cooler and harder to heat, can also increase the efficiency of galaxy assembly. But there are also observations that are harder to explain within the standard framework, even with generous astrophysical adjustments. The most massive galaxies at the highest redshifts push the limits of what is possible even with the most optimistic assumptions about star formation efficiency and stellar population models. And the systematic excess in the galaxy number density, if it persists as more data are collected and the systematic uncertainties are better understood, points to a more fundamental problem. Meanwhile, the Webb observations are not the only challenge facing the Standard Model. There is also the Hubble tension, the persistent and growing discrepancy between the value of the Hubble constant, which measures the current rate of expansion of the universe, as determined from observations of the local universe, and as inferred from the cosmic microwave background under the assumption of the Lambda-CDM model. Local measurements, based on observations of type Ia supernovae and Cepheid variable stars, give a value of roughly 73 km per second per megaparsec. The cosmic microwave background, as measured by the Planck satellite, gives a value of roughly 67.4 km per second per megaparsec. The discrepancy, which has persisted for years and has resisted numerous attempts at resolution, is now statistically significant at a level that makes it very unlikely to be due to chance. If the Hubble tension is real, if it is not an artifact of systematic errors in either the local or the cosmological measurements, then it implies that the Lambda-CDM model is missing something. And whatever it is missing might also be responsible for the unexpected properties of galaxies in the early universe. The convergence of these challenges, the early massive galaxies, the galaxy number density excess, the Hubble tension, and other smaller but persistent anomalies, has created what some physicists have called a crisis in cosmology. This is not a crisis in the sense that the enterprise of cosmology is failing. It is a crisis in the sense that the current framework, which has been so successful for so long, may be reaching the limits of its applicability. It is the kind of crisis that has preceded every major revolution in physics, from the crisis of the luminiferous ether that led to special relativity, to the crisis of black body radiation that led to quantum mechanics, to the crisis of the static universe that led to the Big Bang theory. Each of these crises was uncomfortable while it lasted. Each required the abandonment of deeply held assumptions, and each led to a deeper and more comprehensive understanding of nature. We may be at such a moment now. The James Webb Space Telescope, by giving us our deepest and clearest view of the early universe, may have revealed that the story we have been telling about the cosmos is a first draft, brilliant in its broad outlines but flawed in its details, a story that captures much of the truth but not all of it, a story that needs to be revised in the light of new evidence. And the revision, when it comes, may be more profound than we currently imagine. There is a temptation, in moments like this, to be either too conservative or too radical. The conservative temptation is to assume that the anomalies will go away, that they are artifacts of incomplete data or imperfect analysis, that the Standard Model will absorb these challenges as it has absorbed others. The radical temptation is to declare the Standard Model dead and to reach for exotic alternatives, new physics, extra dimensions, variable constants of nature, modifications to gravity that have never been tested and may never be testable. The truth, as always, is likely to be somewhere in between. The Standard Model will not be overthrown entirely, because it explains too much too well. But it will be modified, extended, refined, in ways that we cannot yet predict. And the modifications may teach us things about the universe that we never expected to learn. Consider, for a moment, what we might learn if the early universe was indeed more efficient at forming galaxies than the Standard Model predicts. This would tell us something profound about the nature of gravity and the physics of gas in extreme environments. It would tell us that the interplay between gravity, thermodynamics, and nuclear physics in the early universe produced outcomes that our simulations, which are among the most sophisticated computational efforts ever undertaken by our species, failed to predict. It would tell us that the universe is more creative, more dynamic, more capable of self-organization than we gave it credit for. And it would remind us that the universe is under no obligation to conform to our expectations. Or consider what we might learn if the dark sector, the dark matter and dark energy that together make up 95% of the cosmic energy budget, turns out to have properties different from what we have assumed. Dark matter that interacts with itself, that decays over time, that has a temperature, that is composed not of one type of particle but of several, each with its own properties and interactions. This would open up an entirely new realm of physics. It would mean that the invisible universe, the vast majority of reality, is not the simple, featureless backdrop that we have imagined, but a complex, dynamic realm with its own structures, its own processes, its own history. And dark energy that changes over time, that is not a simple cosmological constant, but a dynamic field that evolves with the expansion of the universe. This would have implications not only for the past, but for the future, for the ultimate fate of the cosmos, for the question of whether the expansion of the universe will continue forever, accelerating until every galaxy is beyond the horizon of every other galaxy, or whether it will eventually reverse, leading to a contraction and perhaps a new beginning. These are not idle speculations. They are the kinds of questions that the Webb observations are forcing us to ask. And they are the kinds of questions whose answers, when they come, will reshape our understanding of reality in ways that are difficult to predict but certain to be profound. Let us take a step further back and consider what all of this means in the broader context of human knowledge. We are a species that has existed for perhaps 300,000 years, a blink of an eye in cosmic terms. For most of that time, we knew nothing about the true nature of the cosmos. We lived on a small planet orbiting a medium-sized star in an unremarkable part of an ordinary galaxy, and we thought the universe consisted of what we could see with our unaided eyes: a dome of stars, a few wandering planets, the sun and the moon. We told stories about the stars, stories of gods and heroes and animals, stories that gave the night sky meaning and made the darkness less terrifying. These stories were wrong in their details but right in their impulse, the impulse to look up, to wonder, to seek understanding. Then, a few centuries ago, we invented the telescope, and the universe expanded. The stars became suns. The nebulae became galaxies. The cosmos revealed itself to be not the small, static, geocentric stage that our ancestors had imagined, but a vast, dynamic, expanding arena of unimaginable size and age. And with each new instrument, each new discovery, the universe has continued to expand, not just physically but conceptually, growing in complexity and mystery even as our understanding of it has deepened. The James Webb Space Telescope is the latest and most powerful of these instruments, and it is continuing this tradition of revelation. It is showing us things we did not expect to see, things that challenge our most cherished theories, things that remind us of how much we do not know. And this is exactly as it should be. This is the purpose of science. Not to confirm our expectations, but to challenge them. Not to reassure us that the universe is simple and comprehensible, but to reveal its true complexity, and to push us to develop new frameworks of understanding that are equal to that complexity. The universe is not our universe, in the sense that it does not belong to us. It does not exist for our convenience. It does not conform to our theories. It is what it is, vast and ancient and strange, and our job is not to force it into our categories, but to expand our categories, to accommodate it. The James Webb Space Telescope is helping us do that. The data it is gathering, the images it is capturing, the spectra it is recording, these are not just numbers and pixels. They are messages from the deep past, whispers from the infancy of the cosmos, telling us things about reality that we could not have learned any other way. And the message they are delivering, the uncomfortable, thrilling, humbling message, is that the universe is bigger, stranger, and more mysterious than we thought. The light that reaches the golden mirror of the James Webb Space Telescope has traveled across billions of years of expanding space. It has passed through the voids between galaxy clusters, regions of space so empty that a human being standing in the center of such a void would see nothing, absolutely nothing, in any direction. It has been gravitationally lensed by foreground galaxy clusters, its path bent, and its image distorted by the warping of space-time around concentrations of mass. It has been absorbed and re-emitted by intervening clouds of gas and dust, its original spectrum modified by each encounter. And it has been stretched, inexorably, by the expansion of the universe itself, its wavelength growing longer and longer as the space through which it travels expands, shifting from the ultraviolet through the visible into the infrared, from blue to red to a deep, invisible warmth that only the most sensitive instruments can detect. By the time this light reaches Webb, it carries within it a record of the conditions that prevailed in the universe when it was emitted. The spectrum of the light tells us the temperature of the gas that produced it, the chemical elements present in the gas, the speed at which the gas was moving, the density of the medium through which the light has traveled. It is a time capsule, a message in a bottle thrown into the cosmic ocean billions of years ago, and only now washing up on the shore of our awareness. And what the message says is that the young universe was a more vigorous, more productive, more structurally complex place than we had imagined. Think about what this means for a moment. The light we are receiving from these distant galaxies was emitted by stars that no longer exist. Those stars burned through their nuclear fuel billions of years ago. The galaxies they inhabited have long since evolved, merged with other galaxies, been disrupted by gravitational encounters, or been consumed by the relentless growth of their central black holes. The universe that produced this light is gone. What exists now, at the location where those photons were emitted, is something utterly different from what we are seeing. We are observing ghosts, shadows, echoes of a reality that passed away before our own sun was born. And yet those ghosts are real. The light is real. The information it carries is real. And the contradiction it presents between what we expected to find and what we actually found is real. This is one of the most remarkable aspects of astronomy, and it is something that distinguishes it from every other science. When a biologist studies a cell, the cell is there, present, alive, available for immediate examination. When a chemist studies a reaction, the reaction is happening now, in the laboratory, under controlled conditions. But when an astronomer studies a distant galaxy, the galaxy as it appears is a historical artifact. The light has been traveling for so long that the object we see no longer exists in the form we are observing it. We are always looking at the past. We can never observe the present state of any distant object. And the further back we look, the more foreign the universe becomes, the less familiar, the more surprising. The James Webb Space Telescope is looking further back than any instrument in history, and the universe it is revealing is the most foreign we have ever encountered. It is a universe in which the rules of galaxy formation that apply in the local cosmos seem to break down, in which the neat, orderly progression from small to large, from simple to complex, from chaos to structure, appears to have been short-circuited by processes we do not yet understand. It is a universe that is, in some profound sense, not the universe we thought we knew. And this is where the story becomes not just scientifically important, but philosophically profound. Because the question of what the universe is, and how it works is not just a question for physicists. It is a question for all of us. It is a question about the nature of reality itself, about the ground beneath our feet, the sky above our heads, the fabric of existence within which our lives unfold. When we discover that the universe is not what we thought it was, we discover something about ourselves as well. We discover the limits of our imagination. We discover the extent of our ignorance. And we discover, once again, the breathtaking, humbling, exhilarating truth that reality is always stranger than our best attempts to comprehend it. There is a famous passage in the literature of science in which a great physicist, reflecting on the history of discovery, noted that the universe is not only stranger than we imagine, but stranger than we can imagine. This sentiment, which has been attributed to various thinkers in various forms, captures something essential about the relationship between the human mind and the cosmos. Our minds evolved to navigate the savannah, to track prey, to avoid predators, to recognize faces and interpret social cues. They did not evolve to comprehend the curvature of space-time, or the wave function of the electron, or the expansion of the universe. The fact that we can comprehend these things at all, that we can build telescopes and write equations and develop theories that describe the behavior of matter and energy across 13 billion years of cosmic history, is itself one of the great mysteries. Why should a brain that evolved to avoid lions be capable of understanding black holes? Why should a nervous system shaped by the demands of survival on a small rocky planet be able to deduce the composition of stars millions of light years away? The very existence of science is a kind of miracle, a testimony to the strange and wonderful fact that the universe has produced, in at least one corner of itself, beings capable of understanding it. But our understanding is always partial, always provisional, always subject to revision. And the revisions, when they come, are not signs of failure. They are signs of progress. The history of science is not a history of truths being discovered once and for all. It is a history of successive approximations, each one closer to reality than the last, each one revealing new dimensions of complexity that the previous approximation had hidden. Newtonian gravity was a brilliant approximation that described the motion of planets and the fall of apples with remarkable accuracy. But it was superseded by general relativity, which revealed that gravity is not a force but a curvature of space-time, and which makes predictions that differ from Newton's in the strong field regime and at the cosmological scale. General relativity, in turn, is understood to be an approximation of some deeper theory, a theory of quantum gravity that unifies the description of space-time with the principles of quantum mechanics, a theory that we do not yet possess, but that we believe must exist because general relativity and quantum mechanics, as currently formulated, are incompatible with each other in certain extreme situations, such as the interior of black holes and the first instant of the Big Bang. The Webb observations may be pointing us toward that deeper theory. Not directly, not explicitly, but by revealing the limitations of our current understanding, by showing us where the approximations break down, by highlighting the gaps in our knowledge that need to be filled. The early massive galaxies, the excess galaxy number densities, the surprisingly mature morphologies, these are not just puzzles to be solved. They are clues to a deeper reality, signposts pointing toward a more complete and more accurate description of the universe. And the process of following those clues, of interpreting the data, of developing and testing new theories, of building new instruments and making new observations, this process is itself one of the most remarkable activities that our species engages in. It is a collective endeavor involving thousands of scientists in dozens of countries, speaking different languages and working in different traditions, but united by a common commitment to understanding the natural world. It is an endeavor that spans generations, building on the work of those who came before and laying the foundation for those who will come after. And it is an endeavor that, at its best, embodies the finest qualities of the human spirit: curiosity, honesty, humility, perseverance, the willingness to be wrong, and the courage to follow the truth wherever it leads. The James Webb Space Telescope cost approximately $10 billion and took more than 20 years to develop, from initial concept to launch. It was a collaboration between NASA, the European Space Agency, and the Canadian Space Agency, involving contributions from hundreds of institutions and thousands of individuals. Its development was plagued by delays, cost overruns, and technical challenges that at times threatened to cancel the project entirely. There were moments when it seemed impossible that such a complex and delicate instrument could be built, launched, deployed, and operated successfully. The telescope had to unfold itself in space, a process involving the deployment of the sun shield, the unfolding of the secondary mirror, and the alignment of the 18 primary mirror segments, all of which had to work perfectly because, unlike the Hubble Space Telescope, Webb is too far from Earth to be serviced by astronauts. There was no margin for error. A single failure in any of these steps could have rendered the entire telescope useless. And yet it worked. Every deployment step succeeded. Every mirror segment aligned. Every instrument performed at or beyond its specifications. The first images, released to the public in July 2022, were breathtaking, not just for their scientific content, but for their sheer beauty. The deep field images showed thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length. Each galaxy a vast collection of billions of stars, each star potentially orbited by planets, each planet a world with its own history and its own possibilities. The images of nebulae showed the stellar nurseries where new stars are being born, vast clouds of gas and dust illuminated by the radiation of young, hot stars, sculpted by stellar winds into shapes of haunting beauty. The images of exoplanet atmospheres revealed the chemical signatures of water, carbon dioxide, and other molecules in the atmospheres of worlds orbiting other stars, bringing us one step closer to the ultimate question of whether life exists elsewhere in the cosmos. But it is the cosmological observations, the observations of the most distant galaxies in the observable universe, that have the potential to be the most transformative. Because these observations are not just showing us pretty pictures. They are testing the foundations of our understanding of reality. And the tests are revealing cracks in those foundations. Cracks that may widen as more data are collected and more analysis is performed. The next few years will be critical. Webb is expected to operate for at least 20 years, far longer than its original 5-year mission requirement, thanks to the fuel efficiency of its launch and orbital insertion. During that time, it will continue to observe the distant universe, gathering more data on high redshift galaxies, refining the measurements of their masses, luminosities, and morphologies, obtaining spectroscopic confirmations of their redshifts, and extending the observations to even earlier epochs. It will also observe the intermediate redshift universe, the epoch between redshift 1 and redshift 6, where galaxies are undergoing the most dramatic transformations and where the effects of any modifications to the standard model should be visible. And it will observe the local universe, studying the properties of nearby galaxies and galaxy clusters with unprecedented detail, calibrating the models of stellar populations and galaxy evolution that are essential for interpreting the high redshift observations. At the same time, other telescopes and experiments will provide complementary data. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct the Legacy Survey of Space and Time, a 10-year survey of the entire visible southern sky that will catalog billions of galaxies, measure the weak gravitational lensing distortions caused by the large-scale structure of the universe, and track the brightening and fading of millions of supernovae and other variable objects. The Euclid Space Telescope, launched by the European Space Agency, will survey the geometry and expansion history of the universe with unprecedented precision, constraining the properties of dark energy and the growth rate of cosmic structure. The Roman Space Telescope, NASA's next great observatory, will combine the wide field of view needed for large surveys with the infrared sensitivity needed to study the distant universe. And ground-based telescopes, including the extremely large telescope, the 30-meter telescope, and the Giant Magellan Telescope, will provide spectroscopic follow-up of the most interesting objects discovered by the space telescopes. Together, these observational programs will assemble a comprehensive picture of the universe's evolution from the earliest times to the present, a picture that will either confirm the standard model or reveal its limitations. And the theoretical response will be equally vigorous. Hundreds of physicists and cosmologists are already working on models that can account for the Webb observations, exploring modifications to the dark sector, alternative theories of gravity, new models of galaxy formation, and entirely new theoretical frameworks. The pace of publication has accelerated dramatically since the first Webb results were released, and the quality and sophistication of the theoretical work is impressive. This is science at its best. Observation driving theory. Theory predicting observation. The two in constant dialogue, each pushing the other toward a deeper understanding of nature. And the stakes could not be higher. We are asking nothing less than what the universe is made of, how it began, how it evolved, and what its ultimate fate will be. These are the biggest questions that science can ask, and the answers, when they come, will rewrite the textbooks and reshape our conception of reality. Let us now turn to some of the specific theoretical proposals that have emerged in response to the Webb observations, because these proposals, even if they ultimately prove to be wrong, illuminate the range of possibilities and the depth of creativity that physicists bring to the challenge of understanding the cosmos. One of the most discussed proposals involves a modification to the properties of dark energy in the early universe. In the Standard Model, dark energy is described by the cosmological constant, a fixed energy density that pervades all of space and that drives the accelerating expansion of the universe. The cosmological constant is, in a sense, the simplest possible form of dark energy. It does not change over time. It does not interact with matter or radiation. It does not cluster or form structures. It is simply a constant background energy that affects the expansion rate of the universe. But there is no fundamental reason why dark energy must take this simple form. It could be a dynamic field, a form of energy whose density changes over time, a field that was perhaps much stronger in the early universe and that has since faded to its current, relatively modest value. If dark energy was stronger in the early universe, it could have affected the expansion rate in ways that altered the timeline of structure formation. Specifically, a stronger dark energy in the early universe could have delayed the onset of matter domination, the epoch at which the energy density of matter exceeded the energy density of radiation, and the universe began to form structures in earnest. Alternatively, certain forms of early dark energy could have enhanced the growth of density perturbations, allowing structures to form more quickly. The details depend on the specific model, but the general idea is that a dynamic dark energy could have created conditions more favorable for rapid galaxy assembly than the standard cosmological constant scenario. This idea has received support from an unexpected quarter. Observations of the cosmic microwave background by the Atacama Cosmology Telescope and the South Pole Telescope have provided hints, though not yet definitive evidence, that an early dark energy component could help resolve the Hubble tension, the discrepancy between local and cosmological measurements of the expansion rate. If early dark energy can simultaneously resolve the Hubble tension and explain the abundance of massive galaxies at high redshifts, it would be a remarkably elegant solution, a single modification to the standard model that addresses two of its most prominent challenges. Another proposal involves modifications to the initial conditions of the universe, specifically to the spectrum of primordial density fluctuations. In the standard model, these fluctuations are generated during inflation, the epoch of exponential expansion that occurred in the first fraction of a second after the Big Bang. The fluctuations are described by a nearly scale-invariant power spectrum, meaning that the amplitude of the fluctuations is nearly the same on all scales. This is a prediction of the simplest models of inflation, and it is beautifully confirmed by observations of the cosmic microwave background. But more complex models of inflation can produce power spectra that deviate from scale invariance, with excess power on certain scales. If there is excess power on the scales that correspond to the masses of the early galaxies observed by Webb, this could enhance the formation of massive structures at early times without requiring changes to the physics of dark matter, dark energy, or gravity. This is an intriguing possibility because it connects the Webb observations to the physics of the very early universe, the first infinitesimal fraction of a second after the Big Bang, when the conditions were so extreme that our current understanding of physics is at its most uncertain. Inflation is a well-established paradigm, but the specific model of inflation that operated in the early universe is not known. There are hundreds of proposed models, each with its own predictions for the primordial power spectrum, and the observational constraints, while powerful, leave room for significant variations. The Webb observations, by probing the consequences of the primordial power spectrum and a much later epoch, could potentially distinguish between different models of inflation, a remarkable feat that connects the first fraction of a second of the universe's history to events that occurred hundreds of millions of years later. A third proposal, perhaps the most philosophically provocative, involves the possibility that the fundamental constants of nature may not be constant. The laws of physics, as we currently understand them, are characterized by a set of numerical constants, the speed of light, the gravitational constant, Planck's constant, the masses of elementary particles, the strengths of the fundamental forces. These constants are assumed to be fixed, unchanging, the same at every point in space and at every moment in time. This assumption is deeply embedded in the structure of physics, and there is strong observational evidence supporting it. But some theoretical frameworks, particularly those that attempt to unify gravity with the other fundamental forces, predict that the constants of nature may vary, either over time or from one region of space to another. If the gravitational constant, for example, was slightly different in the early universe, this could have dramatic effects on the rate of structure formation. A stronger gravitational constant would cause matter to collapse more quickly, leading to the earlier formation of more massive structures. A different fine structure constant, which governs the strength of the electromagnetic force, could alter the physics of atomic transitions and the opacity of the primordial gas, affecting the cooling rate of gas clouds and the efficiency of star formation. These are speculative ideas, and the observational constraints on variations in the fundamental constants are extremely tight. But the constraints are tightest in the local universe and at relatively recent cosmological epochs. At the very high redshifts probed by Webb, the constraints are weaker, and there may be room for variations that are too small to detect locally but large enough to affect the formation of the first galaxies. Let us also consider a possibility that is less often discussed in the scientific literature, but that has deep implications for our understanding of the universe. What if the universe we observe is not representative of the universe as a whole? The observable universe, the region of space from which light has had time to reach us since the Big Bang, is a sphere roughly 93 billion light-years in diameter. This is an enormous volume, but it may be only a tiny fraction of the total universe, which could be much larger, perhaps infinitely larger. If the universe is not perfectly homogeneous on scales larger than the observable universe, if there are variations in the fundamental properties of matter and energy from one region to another, then the laws of physics that we measure in our local patch of the universe may not apply everywhere. This is the landscape of string theory, the multiverse of eternal inflation, the vast ensemble of possible universes predicted by some of the most ambitious theoretical frameworks in modern physics. In such a picture, the universe we observe is not the universe. It is a universe, one of many, each with its own properties, its own laws, its own history. And the question of why our universe has the particular properties it is becomes not a question of fundamental physics, but a question of selection, of why we happen to find ourselves in a region of the multiverse where the conditions are compatible with the existence of observers. This is a deeply controversial idea, and many physicists are uncomfortable with it, because it seems to undermine the explanatory power of physics. If the laws of nature vary from one region of the multiverse to another, then asking why the laws are what they are in our universe is like asking why we live on this particular planet rather than on some other planet. The answer is simply that this is where we happen to be, and the conditions here happen to be compatible with our existence. This anthropic reasoning is viewed by some as a retreat from explanation, a giving up on the search for a deeper understanding. But others see it as a natural consequence of our best theories of fundamental physics, a prediction that should be taken seriously even if it is unsatisfying. The Webb observations, by revealing that the early universe was more complex and more dynamic than expected, could potentially provide evidence for or against these ideas. If the standard model of cosmology can be modified in a simple and natural way to accommodate the observations, this would argue against the need for exotic explanations like varying constants or multiverse selection. But if the observations resist all attempts at modification within the conventional framework, they could point toward a deeper level of reality that we have not yet begun to explore. There is one more aspect of the Webb discoveries that deserves attention, and it concerns the nature of the first light in the universe. For decades, cosmologists have been searching for evidence of the first generation of stars, the so-called population 3 stars, which are predicted to have formed from the primordial gas of hydrogen and helium, without any of the heavier elements that are produced by later generations of stars. These first stars are expected to have been very different from the stars we observe today. They should have been extremely massive, perhaps hundreds of times the mass of the Sun, and extremely luminous, burning through their nuclear fuel in just a few million years before exploding as supernovae or collapsing directly into black holes. No population 3 star has ever been definitively observed, because they are expected to have existed only in the very earliest epochs of the universe, and to have been replaced by later generations of stars within a relatively short time. Webb, with its ability to probe the earliest epochs of cosmic history, was expected to find evidence of these first stars, perhaps in the form of galaxies with extremely low metallicities, with chemical compositions dominated by hydrogen and helium and lacking the heavier elements that are the signature of previous stellar generations. But the galaxies that Webb has found at the highest redshifts are not metal-free. They show evidence of enrichment by heavier elements, suggesting that at least one generation of stars had already lived and died before the galaxies we are observing formed. This means that the epoch of population 3 stars is even earlier than the highest redshifts that Webb has probed, or that the transition from the first generation to the second generation of stars occurred very rapidly. This is another puzzle, another piece of evidence that the early universe was moving faster, evolving more quickly, and producing more complexity than our models predicted. It is as if the universe was in a hurry, as if the processes of cosmic evolution that we have been studying in slow motion in the local universe were operating at fast forward in the first few 100 million years. And perhaps, in a sense, they were. The early universe was denser, hotter, and more energetic than the universe we see around us today. The gas was closer together. The gravitational forces were stronger relative to the pressure forces that resist collapse. The radiation field was more intense. The cosmic microwave background was not a faint whisper, but a bright glow that pervaded all of space. In these conditions, it is perhaps not surprising that the processes of star formation and galaxy assembly operated differently from the way they operate today. The surprise is not that they were different, but that they were so much more different than we expected, that the difference between the early universe and the late universe is not merely quantitative, but apparently qualitative, not just a matter of degree, but a matter of kind. This qualitative difference is at the heart of the current scientific debate. Is the early universe simply a more extreme version of the late universe, operating according to the same physical laws, but in a more energetic regime? Or is there something genuinely different about the physics of the early universe, something that our current theories do not capture, something that requires new concepts and new frameworks to understand? The answer to this question will determine the direction of cosmology for the next generation. As we contemplate these profound questions, it is worth stepping back and reflecting on the extraordinary chain of events that has led us to this moment. 100 years ago, we did not know that the universe was expanding. 50 years ago, we did not know that the expansion was accelerating. 20 years ago, we did not have a telescope capable of observing the first galaxies. And now, in the span of just a few years, a single instrument has revealed that the story of the universe's infancy may need to be fundamentally rewritten. The pace of discovery is accelerating. Every month brings new papers, new analysis, new observations that add to the growing body of evidence. The spectroscopic surveys are confirming more and more high redshift galaxies. The photometric catalogs are revealing the statistical properties of the early galaxy population with increasing precision. The theoretical models are becoming more sophisticated, incorporating more physics, exploring more of the parameter space, making more specific and testable predictions.
In the stillness before dawn, when the world sleeps and stars pierce the darkness with their ancient light, there exists a place where humanity has constructed its most ambitious instrument of understanding. Deep beneath the Swiss-French border, some 100 meters underground, the European Organization for Nuclear Research, known to the world as CERN, operates a machine that defies ordinary comprehension. The Large Hadron Collider, a circular tunnel 17 kilometers in circumference, accelerates subatomic particles to 99.999999% the speed of light, crashing them together in a controlled violence that seeks to recreate the first microseconds of the universe itself. And in doing so, it has begun to reveal something that may fundamentally alter our understanding of reality's deepest nature, a crack, as it were, in the edifice of everything we thought we knew. What does it mean, one might ask on such a contemplative night, when the instruments of science whispered to us of asymmetries where we expected symmetry, of unexpected particles where we found only empty space, of fundamental forces behaving in ways that defy our most elegant equations? It means, perhaps, that we stand at a threshold. Not the threshold of knowledge, for that threshold has always existed, and humanity has spent its entire conscious existence standing at that peculiar juncture between the known and the utterly unknown. Rather, we stand at a threshold of humility, a moment when our theoretical frameworks, constructed with such mathematical precision and philosophical care, have revealed their incompleteness. Part 1. The ancient desire to understand. To understand the discoveries at CERN, one must first contemplate the deeper human impulse that drives such endeavors. We are pattern recognition creatures, evolved over millions of years to perceive subtle regularities in our environment. A rustling in the grass might indicate a predator. A change in cloud formations might suggest approaching weather. The positions of stars in the sky offered our ancestors both calendar and navigation. This fundamental capability, to perceive order within apparent chaos, to discern the underlying rules that govern phenomena, has never ceased its operation within us. We took this capacity, refined it through millennia of careful observation, and eventually formalized it into what we now call science. But science is not merely the cataloging of observations. At its deepest level, it is the quest for unity, the belief, which has proven remarkably justified, that the same fundamental principles operate throughout the cosmos. When Isaac Newton discovered that the gravitational force pulling an apple downward was the same force holding the moon in its orbit and the planets in their paths around the sun, he revealed something profound. The universe is not a collection of disconnected phenomena, but an integrated whole governed by discoverable laws. This unification, this reduction of apparent complexity to underlying simplicity, became the supreme goal of physics. 3 centuries of scientific progress have been marked by successive unifications. Electricity and magnetism, initially understood as separate forces, revealed themselves to be different manifestations of a single electromagnetic force. Light itself emerged as an electromagnetic phenomenon, a ripple in the very fabric of space and time. The weak and strong nuclear forces, initially mysterious, became integrated into frameworks of stunning mathematical beauty. And throughout the 20th century, physicists pursued what many consider the ultimate dream, a unified field theory that would show all forces as different facets of a single, elegant principle. This dream remains unrealized, yet never before has it seemed more tantalizing. With each discovery, with each extension of our knowledge toward higher energies and smaller scales, we approach something fundamental about reality. The question that animates CERN, that draws thousands of physicists from nations across the globe, is not merely practical or technical. It is existential. What are the deepest laws of nature? What is the universe made of? What principles hold it all together? And what do these principles tell us about our place within the cosmos? Part 2. The Cathedral of Understanding. Before one can appreciate what CERN has begun to question, one must first understand what has been built, a theoretical structure of such power and elegance that it stands as one of humanity's greatest intellectual achievements. The standard model of particle physics is not a single discovery, but rather a vast architecture constructed over nearly a century by countless physicists, each contribution laying another brick in a building of breathtaking sophistication. At the foundation lies a simple but profound principle. The universe, in all its apparent complexity, is made of elementary particles. Not just atoms, as we learned in childhood chemistry, but entities far smaller and more fundamental. the electrons that orbit atomic nuclei, the quarks that compose the nucleus itself, the photons of light, the W and Z bosons that mediate the weak force. All of these, the Standard Model tells us, are elementary particles. They are fundamental, irreducible, the basic building blocks from which all matter and energy are constructed. These particles interact through four fundamental forces. The strongest is the strong nuclear force, which binds quarks together into protons and neutrons, and binds these nucleons into atomic nuclei with such power that immense energies are required to separate them. The electromagnetic force holds electrons to nuclei and atoms to atoms, giving rise to all chemistry and biology. The weak force, responsible for certain types of radioactive decay, operates at subatomic scales and is crucial for the processes that power the sun. And gravity, the weakest force by far, but the most familiar to our everyday experience, shapes the large-scale structure of the cosmos. What renders this conceptual edifice so remarkable is not merely the unification of these forces into a coherent mathematical framework, but the precision with which the Standard Model's predictions have been verified by experiment. When theoretical physicists, working only with mathematics and principles of symmetry, predicted the existence of particles before they were observed, and then experimenters found those particles exactly where and with the properties predicted, it vindicated not only specific theories, but the entire scientific enterprise itself. The Standard Model's accuracy is extraordinary. Its predictions confirmed to many decimal places, its framework producing results that align with observation in nearly every conceivable test. Consider for a moment what this means. Humanity, a species that emerged barely 1 million years ago, living on a tiny planet orbiting an ordinary star, has used the unique gift of consciousness and mathematics to decode the fundamental nature of reality itself. We have determined the rules by which the universe operates. We have built a framework so comprehensive and so accurate that it can predict the results of experiments not yet performed. By any measure, this is an astonishing achievement, a triumph of human intellect that would seem impossible to explain except through the recognition that the universe operates according to principles that the human mind, itself shaped by cosmic evolution, can in some measure grasp. Part 3. The Whispers of Incompleteness. Yet even in the moment of its greatest triumph, the Standard Model harbored within itself the seeds of its own insufficiency. As physicists tested its predictions to ever greater precision, as they explored the universe across ever more extreme energies and conditions, certain anomalies began to emerge. Quiet at first, like the distant rumble of distant thunder, these discrepancies suggested that something fundamental remained unaccounted for. The first and perhaps most obvious problem was gravity itself. Newton's theory of gravitation, refined by Einstein's general relativity, describes gravity as a bending of spacetime itself caused by mass and energy. This is a beautiful and elegant theory, confirmed by countless observations. Yet it is fundamentally incompatible with quantum mechanics, the framework that governs particle physics. At the scales that CERN explores, at the energies where particles interact, the effects of gravity are utterly negligible, too small to measure. But at even higher energies, at the Planck scale where quantum effects of gravity might become significant, the two frameworks diverge fundamentally. A complete description of nature must unify gravity with quantum mechanics, yet for nearly a century, this has remained an unsolved problem. But this was not the only crack. There was the matter of antimatter, or rather, the terrible asymmetry in their abundance. The Standard Model predicts that when the universe was born, in the first microseconds after the Big Bang, equal amounts of matter and antimatter would have been created. Yet when matter and antimatter meet, they annihilate one another in a burst of energy. If equal amounts had been created, everything would have annihilated, leaving only radiation and no matter at all. Yet here we are, a universe made of matter, our atoms of matter, our very bodies of matter. Somehow, inexplicably, there was slightly more matter than antimatter in the early universe. For every billion antimatter particles, there was 1,000,000,001 matter particles. And it is from that infinitesimal asymmetry that all the stars, galaxies, planets, and living beings in the universe emerged. The Standard Model cannot explain this asymmetry. It remains one of the deepest mysteries in physics. There was also the puzzle of dark matter and dark energy. Astronomers observing the motions of galaxies discovered that the visible matter, stars, gas, planets, all the luminous stuff we can see, accounts for only about 5% of the total mass and energy content of the universe. Some 27% is dark matter, a form of matter that does not interact with light but exerts gravitational effects. And approximately 68% is dark energy, even more mysterious, a form of energy that seems to permeate all of space and is causing the expansion of the universe to accelerate. The Standard Model is essentially silent on the nature of these invisible constituents that comprise 95% of the universe. It is as if we have built an elaborate theory to explain a small corner of reality, while the vast majority of reality's substance remains utterly mysterious. And then, there was the problem of the Higgs boson itself, or more precisely, the problem of mass. In the Standard Model, particles acquire mass through their interaction with a pervasive quantum field, the Higgs field. But the calculations suggest that quantum corrections should make particles vastly more massive than they are observed to be. Why are electrons so light? Why are quarks so light? The Standard Model, without introducing new physics, cannot answer these questions. It is as if the universe has been carefully tuned, with parameters adjusted to particular values that allow for the existence of atoms, stars, and ultimately life. Such fine-tuning struck many physicists as deeply suspicious, suggesting that something fundamental was missing from the theory. These were not fatal flaws in the Standard Model. It continued to make predictions that were confirmed with remarkable precision. But they were like small cracks in the foundation of a great cathedral, visible to those who examined closely, suggesting that beneath the beautiful surface lay something that needed deeper understanding. The physicists working at CERN, therefore, were not merely testing a theory they believed was complete. They were searching for the deeper theory that would encompass the Standard Model while answering the questions it could not address. They were seeking the more fundamental layer of reality. Part 4. The Apparatus of Discovery. To discover the crack that unravels everything, one must first look where the cracks are most likely to appear, at the highest energies, where particles interact with such violence that the structure of space-time itself might be strained. This is why the Large Hadron Collider represents such a profound investment in the human quest to understand the fundamental nature of reality. It is the most powerful particle accelerator ever built, designed specifically to reach energies where new physics might reveal itself. The operation of such a machine is a marvel of engineering and physics combined. Protons, the nuclei of hydrogen atoms, are accelerated to nearly the speed of light and injected into the circular tunnel. They circulate around the 17-kilometer loop thousands of times per second, guided by powerful superconducting magnets cooled to nearly absolute zero. Electromagnetic cavities aligned around the ring add energy to the protons with each pass, accelerating them to higher and higher velocities. The process continues until the protons reach energies of several trillion electron volts, energies that did not exist naturally anywhere in the universe since the Big Bang itself. At designated collision points around the ring, beams of protons traveling in opposite directions are brought together. The intersection is not precise. The protons are not like billiard balls that can be made to collide at a single point. Rather, the beam profiles at the collision point are carefully controlled, and when they cross, occasionally protons will indeed collide head-on. In these collisions, the kinetic energy of the protons is converted into mass, creating new particles. And among these newly created particles might be the evidence of physics beyond the standard model. What makes this search so challenging, however, is that these new particles, if they exist, are not created in every collision. They are rare events, appearing perhaps once in billions of collisions. The machine must therefore operate at incredibly high luminosity, producing billions of collisions per second. The data recorded from each collision is enormous, measured in terabytes per second. Sophisticated computer algorithms, the products of artificial intelligence and decades of development, must sift through this torrent of data to identify the rare signals that might indicate something new. The physicists working with this apparatus understand themselves to be engaged in an enterprise fundamentally different from merely testing predictions. They are hunters of the unknown, searching for signals in noise, seeking the traces of forces or particles that have never been observed. In this quest, they employ not only the tools of experimental physics, but also the methodology of science itself. The careful formulation of hypotheses, the design of experiments to test those hypotheses, and the willingness to be surprised by nature. It is work that requires immense patience, for it may take years of running the machine, analyzing data, and refining techniques before any signal becomes clear enough to declare as a discovery. Part 5. The signal in the noise. Science often proceeds not through dramatic eureka moments, but through the slow accumulation of evidence, the gradual shift in probability as data accumulates. So it has been with CERN's latest findings. Working across multiple detector experiments, massive structures weighing thousands of tons, buried beneath the Earth, capable of recording the traces of particles created in the collision's aftermath. Physicists have observed anomalies that collectively suggest something is amiss with our understanding of fundamental physics. The anomalies are subtle. When certain particles decay, they do so in patterns that deviate slightly but consistently from the predictions of the standard model. When other particles are created in the collisions, their properties sometimes differ from what theory predicts. These are not massive deviations, not experiments showing results off by an order of magnitude. Rather, they are deviations of a few percent, precisely measured deviations that appear when you examine billions of events and extract their statistical properties. Any individual measurement might be explained away as a fluctuation, a statistical artifact. But when multiple independent measurements all deviate in the same direction, when the deviations appear consistently across different experiments, the probability that they are merely statistical noise becomes vanishingly small. In classical physics, an anomaly is something that breaks the rules. In quantum mechanics, anomalies have a deeper meaning. They represent fundamental asymmetries in the laws of nature that cannot be cancelled by any choice of renormalization. The anomalies that CERN is detecting appear to violate something called lepton universality. This is a principle enshrined in the standard model that states electrons, muons, and tau particles, the three charged leptons, interact identically with the weak force that mediates radioactive decay. They differ in mass, but their fundamental interactions should be identical. Yet in certain decay processes, this universality appears to be broken. The weak force seems to couple with slightly different strength to electrons versus muons. What makes this particularly intriguing is that similar anomalies have been detected in different channels, different types of particle decays, all pointing toward a violation of lepton universality. The significance of these measurements has grown over time, as more data has accumulated and more sophisticated analyses have been performed. Each new measurement pulls the conclusion further away from what the standard model predicts. Physicists calculate the probability that such deviations could occur purely by chance, through statistical fluctuation. The probability shrinks with each new data point. What once seemed like a possible statistical fluctuation begins to take on the appearance of a genuine signal. But this is only one anomaly. There are others. Measurements of the muon's magnetic moment, a quantum property that describes how the muon interacts with magnetic fields, show a small but persistent deviation from theoretical predictions. The electron's own magnetic moment shows analogous tensions. The mass of the W boson, measured with incredible precision, differs slightly from what precision electroweak fits predict. These individual anomalies might each be explainable as experimental or theoretical artifacts, but together they begin to paint a picture of a universe that does not quite conform to the standard model we have so carefully constructed. Together, these measurements hint at new physics, new particles, new forces, new principles operating at the fundamental level. The question that animates the CERN community is not whether anomalies exist, but what they mean. Do they represent genuine deviations from the standard model, or will continued data-taking and refinement of theoretical calculations eventually reconcile the observations with existing theory? History suggests that sometimes new physics is revealed in such ways, but other times apparent anomalies resolve themselves. The only way to know for certain is to continue the quest for understanding, to push higher in energy, to measure with greater precision, and to follow where the data leads. Part 6. Theories of the Beyond. If CERN's anomalies represent genuine signals of new physics, what might be the nature of this new physics? The theoretical physics community has proposed numerous possibilities, each suggesting different ways that reality might extend beyond the standard model. To understand these possibilities is to glimpse the frontiers of our current understanding, the hypothetical territories that might lie just beyond our current knowledge. One possibility is the existence of new particles, interactions between the known particles and yet undiscovered particles that leave subtle signatures in the observations. The pattern of anomalies and rare decays might be caused by a new heavy particle that couples specifically to the weak force in a way that deviates from the standard model's predictions. Such particles could be bosons, force carriers like the photon or W boson, or fermions, like the quarks and leptons we already know. If such particles exist, the question becomes, why were they not discovered long ago? The answer is that they might be extremely heavy, with masses that exceed the energies CERN can currently create. But their effects could still be felt indirectly, in the subtle deviations from standard model predictions that appear in precision measurements. Another possibility is supersymmetry, a principle that proposes a deep symmetry between bosons and fermions. In supersymmetric theories, every known particle would have a heavier superpartner. The electron would have the selectron, the quark would have the squark, and so forth. This framework was developed to address certain theoretical problems with the standard model, and has the elegant feature of naturally including gravity within the quantum framework. If supersymmetry is real, it would explain the fine-tuning problems that have puzzled physicists for decades. However, despite extensive searches, no evidence for supersymmetric particles has been found. They may simply be too heavy for current accelerators to create. A third possibility is that the universe possesses additional dimensions of space beyond the three we are familiar with. String theory, the most ambitious attempt to unify all forces including gravity, naturally incorporates extra dimensions. These dimensions might be extremely small, curled up at scales far smaller than we can currently probe. Or they might be larger, with particles able to move through them in ways that would create new effects in particle collisions. If the anomalies CERN is observing are caused by particles traveling into or interactions involving extra dimensions, it would be a discovery of revolutionary proportions. There are also more exotic possibilities. Leptoquarks, particles that would carry characteristics of both quarks and leptons, could cause the patterns of anomalies observed in rare decays. Compositeness, the idea that electrons and quarks are not truly elementary, but are made of still smaller constituents, might manifest as deviations from the Standard Model's predictions at high energies. Z-prime bosons, hypothetical cousins of the Z boson that mediates the weak force, might exist and couple to particles in non-standard ways. What is remarkable is that each of these theoretical frameworks makes specific predictions that differ from the Standard Model in particular ways. The anomalies CERN is observing, if they are genuine, will provide clues to which of these theories, if any, is correct. The pattern of anomalies, their magnitudes, and their relationships to one another will serve as a fingerprint identifying the new physics at work. In this sense, nature is revealing itself not through a sudden, dramatic discovery of a new particle, but through a gradual clarification of what is amiss with our current framework. It is a subtler revelation, but no less profound. Part 7. Echoes through the universe. To contemplate the implications of CERN's discoveries is to begin to understand how intimately connected the smallest scales of reality are with the largest. Particle physics is not an isolated corner of human knowledge, interesting only to specialists in laboratories. Rather, the fundamental particles and forces we study at CERN are intimately related to the structure and evolution of the entire cosmos. Consider first the question of matter-antimatter asymmetry. Any explanation of why the universe contains matter rather than equal parts matter and antimatter must involve physics that violates the symmetry between matter and antimatter. The Standard Model possesses such violations, but they are far too small to account for the observed asymmetry. New physics, such as that hinted at by CERN's anomalies, might involve more substantial matter-antimatter violations. Such physics could have profound implications for our understanding of the Big Bang. In the early universe, mere fractions of a second after the beginning, the energies were so high that today's new physics might have been common. The asymmetries produced by this physics might have left an imprint on the universe that echoes down through billions of years to the present day. Understanding the particles and forces at CERN could shed light on why the universe exists in the form we observe it. Similarly, the dark matter problem, the fact that 27% of the universe's mass and energy is in a form invisible to light, might find its answer in new particles discovered or constrained by CERN. Some of the leading candidates for dark matter particles, such as weakly interacting massive particles, WIMPs, or axions, can be probed through the precision measurements made at the Large Hadron Collider. If CERN's anomalies indeed signal new particles or forces, these might be connected to the dark matter in ways we do not yet understand. A unified explanation of the anomalies and dark matter would represent a profound advance in understanding the cosmos. The discovery of new physics beyond the Standard Model would also have implications for our understanding of the Big Bang and the universe's earliest moments. The inflationary period that occurred in the first fraction of a second after the Big Bang is thought to have stretched quantum fluctuations to cosmic scales, creating the variations in density that eventually grew into galaxies. The physics of inflation depends sensitively on the properties of the particles and fields present in the early universe. New particles or interactions discovered at CERN could change our understanding of inflation, altering our predictions for what the cosmic microwave background radiation, the afterglow of the Big Bang, should look like. In turn, observations of this radiation could provide constraints on the theories being tested at CERN, creating a feedback loop between particle physics and cosmology. Perhaps most profoundly, the discovery that the Standard Model is incomplete would have philosophical implications for our understanding of the human place in the cosmos. For more than half a century, the Standard Model has been our best description of fundamental reality. Scientists have built careers understanding its implications. Engineers have designed the experiments to test it. Students have learned it as received truth. The discovery that it is incomplete, that our understanding of the fundamental laws of nature is less complete than we thought, would be both humbling and liberating. Humbling because it would show once again that human knowledge, however vast, remains finite and provisional. Liberating because it would open new possibilities, new domains of understanding that await exploration. It would remind us that the universe remains, in important respects, a mystery, and that the pursuit of understanding that mystery is a distinctly human endeavor that may continue indefinitely. Part 8. The Boundaries of the Known. Yet as CERN pushes the boundaries of our knowledge, it is important to recognize the fundamental limits that constrain the quest to understand the ultimate nature of reality. These limits are not merely practical or technical, though the technical challenges of building and operating high-energy particle accelerators are formidable. Rather, they are limits that appear to be intrinsic to nature itself, boundaries that may be insurmountable. Consider the Planck scale, a length scale approximately 10 to the minus 35 meters, a billion times smaller than a proton. At this scale, quantum gravity becomes important. The gravitational force between two particles becomes comparable to the other fundamental forces. To probe this scale would require an accelerator as large as the solar system, and would require the energy equivalent to billions of stars. Such an accelerator is not merely impractical in today's economic and technological context. It is fundamentally impossible given the matter and energy resources available in the universe. We cannot, in principle, directly observe the physics at the Planck scale. The universe itself sets a limit on human knowledge at this scale. This realization, that there exist boundaries to what can be known, limits imposed by the universe itself rather than by human limitations, has profound implications. It suggests that unified theories of everything, frameworks that would completely explain all phenomena from the quantum to the cosmic scale, may forever remain inaccessible to direct experimental verification. We may be able to construct such theories, to write down mathematical equations that supposedly describe everything, but we may never be able to prove them correct through experiment. Instead, we may be forced to rely on indirect evidence, on the consistency of theoretical frameworks, and on their power to explain the phenomena we can observe. There is also a more subtle limit on knowledge that has been recognized in recent decades, the limit imposed by quantum mechanics itself. Information about the world cannot be copied perfectly. The mere act of measuring a quantum system changes it. There exists an irreducible randomness in nature. Not everything that happens can be predicted with certainty, even in principle. The universe is not a cosmic clockwork where perfect knowledge of initial conditions would allow perfect prediction of all future states. Rather, probability and indeterminacy are woven into the fabric of reality at the deepest level. This does not render physics merely probabilistic in practice, with underlying determinism remaining unknown. Rather, indeterminacy appears to be fundamental. These limits, the Planck scale barrier preventing access to quantum gravity phenomena, the inherent limits imposed by quantum mechanics on what can be observed and predicted, form the boundaries of the territory that human knowledge can hope to explore. CERN and other experiments push relentlessly toward these boundaries, seeking to understand as much as possible before the limits are reached. This effort is not futile. even though it is ultimately bounded. Rather, it represents the highest expression of human curiosity, the drive to understand the cosmos, knowing that complete understanding may forever remain beyond reach, yet pressing forward nonetheless. Part 9. The Cosmic Perspective. To work at CERN, or to follow closely the discoveries emerging from this laboratory, is to participate in something larger than oneself, a collective human endeavor that extends backward through generations and forward into the future. It is to stand in a tradition that stretches back to the ancient astronomers who first mapped the stars, to Copernicus and Galileo who revolutionized our understanding of the cosmos, to Newton who revealed the universal laws of motion and gravitation, and to Einstein who showed that space and time themselves are dynamic, subject to bending and warping by matter and energy. In the 20th century, this tradition gave birth to quantum mechanics and particle physics, frameworks that reveal the probabilistic nature of reality and the existence of fundamental particles. The physicists who developed these frameworks, Planck, Heisenberg, Schrödinger, Dirac, and countless others, worked with the best tools and knowledge available in their time. They built upon the achievements of their predecessors while pushing beyond the boundaries of previous understanding. Now, in the 21st century, we continue this tradition. We use the tools they created, the language of quantum mechanics, the insights of symmetry and conservation laws, to probe deeper still. The physicists working at CERN are custodians of this grand tradition, but they are also innovators and explorers. They are not content to accept the standard model as a final word on reality, even though it has been so successful. They build ever more powerful machines, devise ever more sophisticated experiments, and analyze data with ever more advanced techniques in pursuit of the next breakthrough. They do this not for personal glory, though recognition certainly motivates many scientists. Rather, they do it because the quest to understand the universe is a fundamental human drive, arising from the same impulse that led our ancestors to wonder at the stars and seek to comprehend them. And it is important to recognize that this quest is not the work of isolated individuals toiling in laboratories. CERN employs nearly 2,500 people in permanent and semi-permanent positions, but the laboratory serves a community of nearly 13,000 scientists and engineers from 110 countries. The large detector experiments each involve hundreds of physicists and engineers, organized into numerous working groups, collaborating on the analysis of data. The theoretical physics community, scattered across universities and research institutes worldwide, develops the frameworks that guide experimental work and interpret the results. International collaboration on this scale is itself a remarkable human achievement, demonstrating that the quest to understand fundamental reality can unite people across national and cultural boundaries. This collaboration is not new. Since the beginning of modern science, researchers have built upon each other's work, shared findings, and worked collectively toward shared goals. The scientific method itself is a collaborative endeavor across time, each generation standing on the shoulders of its predecessors, seeing further because they have been lifted higher. CERN's existence and the discoveries it is producing are only possible because of this cooperative framework. The anomalies detected at CERN are significant not only because they might signal new physics, but because they represent the fruit of a vast collaborative effort spanning decades and continents. Part 10. The mystery deepens. In our modern age, saturated with information and characterized by rapid technological change, it is easy to lose sight of something fundamental about science and the pursuit of knowledge. Science is not primarily a method for eliminating mysteries. Rather, it is a structured approach to investigating mysteries while maintaining rigorous standards of evidence and logical reasoning. In the process of solving old mysteries, science tends to reveal new ones. Each answer to a question about how the universe works typically leads to deeper questions about why the universe works that way. The anomalies CERN is detecting exemplify this perfectly. Their existence is somewhat mysterious in itself. Why these particular deviations? Why in these particular measurements? Why clustered around lepton universality? The answers to these questions might involve new particles, new forces, or new principles. But each answer, once obtained, would undoubtedly lead to further questions. If new particles are discovered, why do these particles have the masses they have? Why do they interact with the fundamental forces in the way they do? Why does nature possess this particular spectrum of particles and forces rather than some other spectrum? In this sense, the crack that CERN is discovering in the edifice of the Standard Model is not a disaster or a catastrophe. Rather, it is an opportunity. It is a signal that nature still has secrets to reveal, that the universe remains fundamentally mysterious in important ways. And it is precisely this quality of mystery that drives the scientific enterprise forward. Without mystery, there would be no reason to do science, no motivation to build great laboratories and conduct careful experiments. It is the existence of the unknown that gives meaning to the quest for knowledge. The physicist and author Carl Sagan once wrote that we are made of star stuff, that the atoms that comprise our bodies were forged in the interiors of stars that have long since exploded. This profound truth connects us physically to the cosmos. But there is another connection, equally important. We are made of the same fundamental particles and governed by the same fundamental laws as everything else in the universe. When we investigate particle physics, when we conduct experiments at CERN, we are ultimately investigating ourselves. We are looking into the mirror that nature holds up, trying to understand the fundamental principles that made us possible. And in this investigation, we encounter not final answers, but deeper questions, not complete knowledge, but a more nuanced understanding of our ignorance. We learn what we do not know. We discover the contours of the mystery that surrounds us. And in doing so, we fulfill a fundamental human need, the need to understand, to seek meaning, to ask why. This is perhaps the deepest significance of CERN's discovery. It is not that a crack has been found in the Standard Model, though that is important. Rather, it is that we have once again glimpsed the profound mystery at the heart of reality, and found ourselves compelled to press further, to ask deeper questions, to seek a more complete understanding. Part 11. Peering further into the abyss. Looking forward, the question becomes, what are the next steps in the investigation of the anomalies CERN has discovered? How will physicists determine whether these anomalies represent genuine signals of new physics, or whether further data and improved theoretical understanding will eventually reconcile them with the Standard Model? The answer lies in multiple complementary approaches, each providing independent checks on the other. First, CERN itself will continue operating the Large Hadron Collider at higher and higher luminosity. The machine has been operated at only about a quarter of its design luminosity in recent years. As upgrades to the accelerator and detectors are completed, the rate of data collection will increase. More collisions mean more opportunities to observe rare processes, more statistical power to discern signals from background noise. With more data, any genuine signal should become progressively clearer, while statistical fluctuations should average out. This increase in data rate is expected to continue for several more decades, potentially providing hundreds of times more collisions than have been collected so far. Second, theorists will continue refining the Standard Model calculations and exploring possible extensions beyond it. The deviations CERN has observed, while suggestive, are not yet statistically definitive at the level physicists typically require for a discovery claim. Much work remains in understanding the exact size of standard model predictions, accounting for all sources of uncertainty, and investigating what patterns of deviations might be expected if various theoretical extensions are correct. As theoretical understanding improves, it may become clear that some anomalies are actually in better agreement with the standard model than initially thought, while others represent more significant deviations requiring new physics. Third, other experiments and observatories will provide complementary evidence. Precision measurements made by atomic and nuclear physics experiments probe the structure of fundamental interactions at scales different from those at CERN. Cosmological observations, measurements of the cosmic microwave background radiation, observations of distant supernovae, detections of gravitational waves, all provide windows into the properties of fundamental particles and forces. A genuine breakdown of the standard model should reveal itself across multiple independent experimental programs, not only at CERN. The convergence of evidence from diverse sources would be far more compelling than anomalies from a single experiment. And finally, there is the possibility that new facilities will be constructed to probe energies beyond those accessible at the Large Hadron Collider. Proposals have been advanced for electron-positron colliders, for muon colliders, for larger proton colliders. Such facilities would provide new opportunities to discover or constrain new particles and interactions. The question of whether such a facility will be built, where it will be built, and when it will come online remains open. But the scientific case for such a facility is clear. If the anomalies CERN has detected represent genuine new physics, a more powerful accelerator might reveal the new particles or forces responsible more directly than the subtle deviations observed so far. Part 12. How we know what we know. The discoveries emerging from CERN raise profound questions, not only about the nature of physical reality, but also about the nature of scientific knowledge itself. How do we know what we know? What constitutes evidence for a discovery? When can we claim to have found genuine new physics rather than merely statistical fluctuations? These are questions at the intersection of physics and philosophy, questions that have occupied the minds of physicists and philosophers of science throughout the modern scientific era. The scientific method, in its classical formulation, involves the formation of hypotheses, the design of experiments to test those hypotheses, the collection of data, and the interpretation of that data in light of the original hypotheses and competing alternatives. But the practice of science, particularly in particle physics, often proceeds in more subtle ways. Experiments typically do not directly test a single hypothesis, but rather constrain a space of possibilities. Measurements do not yield definitive yes or no answers, but rather probability distributions representing the likelihood of various outcomes given the data. The concept of statistical significance is particularly important here. Physicists have adopted a convention that a signal is considered evidence if the probability of observing the signal purely by chance, given the standard model's predictions, is less than 1 in 3,500, 3 standard deviations. A signal achieves the status of discovery only if the probability of it occurring by chance is less than 1 in 3.5 million, 5 standard deviations. These high thresholds reflect the recognition that even unlikely events occasionally occur by pure chance, especially when searching through large datasets looking for anomalies. The possibility of having found a statistical fluctuation rather than genuine new physics must be carefully guarded against. By these conventional standards, CERN's anomalies remain in the interesting category, suggesting new physics might be present but not yet achieving the statistical threshold required for a definitive discovery claim. This situation is actually quite common in science. Many important discoveries began as tantalizing hints that gradually accumulated evidence over years or decades. The discovery of the Higgs boson, for example, involved the gradual accumulation of evidence from multiple experiments until the signal became undeniable. The anomalies CERN is detecting may follow a similar path. But there is another philosophical dimension to CERN's discovery that is equally important: the question of how theories are chosen and evaluated. Physics seeks not merely to describe phenomena, but to explain them through underlying principles. The Standard Model is not simply a convenient formula for making predictions. It embodies certain theoretical values: simplicity, elegance, unification. A successful theory should be able to explain why nature is structured as it is, not merely describe how nature behaves. If the anomalies detected at CERN can be explained by extending the Standard Model in ways that preserve or enhance these theoretical values, then CERN may be pointing us toward a deeper and more elegant understanding of reality. The crack in the edifice might be the beginning of the construction of an even more beautiful cathedral. Part 13. Matter in the Cosmic Context. While CERN focuses on the realm of the infinitesimally small, probing the properties of particles and forces at the highest energies, it is important to remember that this investigation is ultimately in service of understanding the cosmos as a whole, from the first fraction of a second after the Big Bang to the present day, 13.8 billion years later, and onward into the far future. The early universe, in the moments immediately after the Big Bang, would have been inconceivably hot. So hot that all particles would have possessed enormous energies comparable to those produced in CERN's collisions. As the universe expanded and cooled, these high-energy states would have given way to the particles and forces we observe today. But the physics of that early era left imprints on the universe, subtle signatures that we can still detect billions of years later. Understanding these signatures requires understanding the fundamental particles and forces, which is precisely what CERN investigates. One such signature is the slight excess of matter over antimatter that allows the universe to contain anything at all. Another is the nature of the dark matter that comprises most of the universe's mass. A third is the spectrum of temperature variations in the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. These observations from cosmology provide powerful constraints on theories of fundamental physics. Conversely, theories developed through particle physics experiments can make predictions about what we should observe in the cosmos. The dialogue between particle physics and cosmology has become increasingly important in modern physics, with each field providing insights that guide the other. In this broader context, CERN's anomalies take on additional significance. If the deviations from the Standard Model are genuine, and if they arise from new particles or forces, these new physics might have been crucial in determining the properties of the early universe. They might explain why matter prevails over antimatter, why the universe possesses the dark matter it does, why the large-scale structure of the cosmos has the particular features it exhibits. Understanding fundamental particle physics is not merely an abstract intellectual exercise. It is intimately connected to understanding our own existence, our origins, and the nature of the universe that gave birth to us. Part 14. The Nature of Reality Reconsidered. In contemplating CERN's discoveries, one is inevitably drawn to meditate on the very nature of reality itself. What is the universe made of, ultimately? What are the fundamental constituents from which all existence is constructed? These questions have occupied philosophers and mystics for millennia, yet it is only in the modern scientific era that we have developed tools sufficiently powerful to investigate them in quantitative, testable ways. The quantum mechanical view of reality that has emerged from a century of physics is profoundly counterintuitive. Particles do not possess definite properties until they are measured. They exist in superpositions of multiple states simultaneously, resolving into definite states only when observed. They can be in two places at once, They can tunnel through barriers. They can become entangled with one another such that knowing the state of one instantly determines the state of another regardless of distance. This quantum reality is so strange that it has generated numerous philosophical interpretations. The Copenhagen interpretation, the many worlds interpretation, pilot wave theory, each attempting to make sense of what quantum mechanics tells us about the nature of existence. Added to this quantum strangeness is the relativistic perspective, inherited from Einstein's theories. Space and time are not fixed, absolute backgrounds against which physics unfolds. Rather, space and time are dynamical, shaped by the mass and energy they contain. They can be curved, warped, stretched, and compressed. Events that are simultaneous in one reference frame may occur in a different order in another reference frame. The universe's geometry is determined by its content. Reality, at both the quantum and relativistic scales, is far stranger and more wonderful than our everyday intuitions would suggest. The Standard Model, for all its successes, is built upon these strange foundations. It is a quantum field theory, describing reality not as a collection of definite particles, but as a collection of fields, quantum entities that permeate all of space and can fluctuate, producing particles that represent excitations of those fields. Electrons are ripples in the electron field. Photons are ripples in the electromagnetic field. Quarks are ripples in the quark fields. The forces between these particles arise from the exchange of other particles, themselves excitations of different fields. This picture is extraordinarily abstract, far removed from our everyday experience of discrete, localized objects. And yet, this abstract mathematical framework makes predictions that agree with experiment to astonishing precision. The magnetic moment of the electron, predicted by the marriage of quantum mechanics and special relativity, is accurate to more than 10 decimal places. The properties of the Higgs boson, predicted by the Standard Model, align with observations to remarkable accuracy. How is it possible that mathematics, a creation of human minds, can describe reality with such fidelity? This is the profound mystery that contemplating CERN's work should inspire in us. We are creatures of the cosmos, made of the same atoms, and governed by the same fundamental laws as everything else. And within our consciousness lies the capacity to apprehend these laws, to express them in mathematical language, to use that language to make predictions about phenomena we have never observed. This mysterious conjunction of consciousness and cosmos, of thought and reality, remains ultimately inexplicable. Part 15. Pathways Forward. If CERN's anomalies do indeed point toward physics beyond the Standard Model, the implications for future research directions are profound. New experimental techniques would need to be developed to directly detect or constrain the new particles or forces responsible. Theoretical frameworks would need to be extended and refined to incorporate these new elements while maintaining consistency with all existing observations. The field of particle physics would enter a new era of discovery and investigation. But the significance extends beyond the technical domain of physics. Throughout human history, major revisions in scientific understanding have had profound cultural impacts. The Copernican revolution, which placed the sun rather than the earth at the center of the solar system, required centuries to become accepted but ultimately transformed how humans understood their place in the cosmos. The Darwinian revolution, which showed that all living things are related through common descent and natural selection, sparked philosophical and theological upheaval that continues to this day. Einstein's revolutions in understanding space, time, and gravity transformed our most basic conceptions of reality. A genuine discovery of new fundamental physics would represent another such transformation. It would demonstrate that our understanding of reality, while impressive, remains incomplete. It would show that there are still deep questions to answer, mysteries to explore, new lands to discover. In an age sometimes characterized by a sense that all the fundamental questions have been asked and most have been answered, such a discovery would reaffirm the enduring nature of the quest for understanding. It would inspire new generations of scientists to pursue careers in physics, attracted by the challenge of investigating genuinely new phenomena. Moreover, the methodologies developed at CERN have applications far beyond fundamental physics. The data analysis techniques developed to extract signals from noise, the machine learning algorithms trained on massive datasets, the precision measurement techniques, all have found applications in medicine, engineering, environmental science, and numerous other fields. The spin-offs from CERN's work have contributed to technologies that benefit society, from positron emission tomography scanners used in medical imaging to the World Wide Web itself, developed at CERN to meet the laboratory's data-sharing needs. Further discoveries at CERN might lead to additional practical applications we cannot yet foresee. Part 16. The Community of Inquiry. One cannot fully understand the significance of CERN's work without appreciating the human community that makes it possible. Physics is often presented as a body of abstract knowledge, timeless truths about the nature of reality. Yet physics is made by humans, and the pursuit of knowledge at CERN is fundamentally a human endeavor, shaped by the ambitions, curiosities, frustrations, and triumphs of the thousands of individuals who work there. The experimental physicists working at CERN spend years designing and building detector systems of staggering complexity, systems capable of detecting the traces of particles created in the collision and reconstructing their properties from these traces. These are not solitary endeavors. They involve engineers, computer scientists, technicians, and physicists working in coordination to solve problems and implement solutions. The theoretical physicists working on the interpretation of CERN's data are engaged in a global conversation, comparing their understanding, debating interpretations, proposing new models. Postdoctoral researchers and graduate students, the next generation of scientists, are trained in this environment, learning not only the technical details of physics, but also the cultural values of the scientific community: openness, rigor, the willingness to be proven wrong. The social dynamics of this community are important to understanding how scientific progress occurs. Individual researchers become invested in particular interpretations or theories, sometimes to the point of bias. Yet the peer review process, the requirement to present results at conferences and in journals, the critical scrutiny of colleagues, these mechanisms help to overcome individual biases and move the field toward truth. Science progresses not because individual scientists are perfectly objective, but because the scientific community collectively has developed institutions and practices designed to minimize the impact of individual subjectivity. Moreover, the international nature of CERN's collaboration demonstrates that the pursuit of fundamental knowledge can transcend political and national boundaries. Physicists from nations that have been in conflict, that currently maintain tense relations, work side by side at CERN. They share data, collaborate on analyses, publish joint papers. In an increasingly fragmented world, CERN stands as an example of what humanity can achieve when we put aside narrow national interests in service of a larger goal: understanding the universe. This alone, independent of any scientific discoveries, makes CERN an institution of profound significance. Part 17. Meditations at the Edge of Knowledge. As we contemplate the findings emerging from CERN, and as we consider what they might mean for our understanding of the universe, we find ourselves in a peculiar position. We have built an extraordinary apparatus for investigating nature's deepest secrets. We have developed sophisticated theoretical frameworks that predict the properties of fundamental particles with stunning accuracy. Yet we have also discovered that this framework, for all its power, appears to be incomplete. There are cracks in the edifice, anomalies that suggest something has been left out of our understanding. This situation, standing at the frontier of knowledge, with hints of something beyond but not yet clear what, is oddly reminiscent of standing on a beach at dusk. The sun is setting, the light is fading, and beyond the familiar shore lies the dark ocean. We can see its surface, can understand something of its properties, but its depths remain unexplored. The foam of the waves at the edge carries tantalizing signs of what lies further out. The slightly greater intensity of the waves, the subtle changes in the water's composition, the occasional glint of something moving in the deeper water. These signs suggest that there is more to discover, more to understand, more to explore. The uncertainty that characterizes the current moment in particle physics, where discoveries are suggested but not yet confirmed, where new physics seems to lurk just beyond the reach of current experiments, may itself be valuable. Uncertainty drives inquiry. Certainty, if it could be achieved, would allow science to rest. But the universe, fortunately or unfortunately, does not seem inclined to grant us the comfort of complete certainty. Instead, it parcels out knowledge gradually, revealing just enough to entice further investigation, and in each revelation placing us face to face with new mysteries. To be a physicist, or simply to take seriously the pursuit of understanding how the universe works, is to have made a commitment to following the evidence wherever it leads, to remaining open to being surprised, to accepting that fundamental principles of reality may be quite different from what we assume. It is a posture of humility before nature, combined with confidence in the human ability to understand. It is a recognition that the universe is genuinely interesting, that it holds surprises, secrets, depths we have not yet fathomed. And it is an affirmation that the effort to fathom these depths is intrinsically valuable, worthy of dedication and resources, part of what makes us human. Part 18. The Unfinished Symphony. In the coming years and decades, the investigation into CERN's anomalies will continue. More data will be accumulated, more precise measurements will be made, more theoretical work will clarify the implications of the observations. It is impossible to predict with certainty what will be discovered. Will the anomalies strengthen, becoming increasingly incompatible with the standard model and pointing towards specific new physics? Will new particles be discovered directly, their properties making clear the nature of the physics beyond the standard model? Or will the anomalies gradually diminish as measurement techniques improve and theoretical understanding deepens, revealing them to be nothing more than statistical fluctuations? Any of these outcomes is scientifically significant. If the anomalies grow stronger and clear new physics emerges, humanity will have made a genuine leap in understanding the fundamental nature of reality. If they fade away, the field will have learned that the standard model's domain of validity extends even further than previously believed, and the search for new physics will redirect itself toward other signals or phenomena. If they resolve into deeper understanding without invoking new particles, we will have gained insight into the subtle structure of quantum field theory itself. But whatever the specific outcome, the larger enterprise continues. Physicists will continue building more sensitive experiments, developing more powerful theories, training the next generation of scientists to carry forward the quest. CERN will continue operating and eventually be joined or replaced by ever more powerful machines. The community that gathers around these questions will persist, driven by the fundamental human urge to understand. This is how science advances, not through occasional flashes of brilliant insight, though those do occur, but through steady, persistent effort applied across decades and generations. Individual discoveries lead to new questions, which drive the search for new discoveries. The accumulated knowledge of centuries provides the foundation upon which each new generation builds. The crack that CERN has discovered in the Standard Model may be the first opening through which we catch a glimpse of deeper physics, or it may prove to be nothing more than a hairline fracture without deeper significance. But the very act of searching, of investigating, of remaining open to what nature has to teach us, is itself profoundly meaningful. Part 19. What binds the universe together? At the deepest level, the investigation at CERN is an investigation into what binds the universe together, the fundamental forces and principles that give it unity rather than allowing it to dissolve into disconnected chaos. We have learned that the forces we observe are unified in particular ways. Electromagnetism is a unified description of electricity and magnetism. The electroweak force unifies electromagnetism with a weak nuclear force. These unifications revealed that what appeared to be distinct phenomena were actually different manifestations of a single underlying principle. The anomalies CERN has discovered may represent the first hints of yet deeper unification, a principle of unity that encompasses even more of the universe's diversity of forces. Or they may suggest that the universe's structure is more complex than a simple hierarchy of unifications, that perhaps there are multiple ways that different aspects of nature can be understood, each valid within its domain, but each potentially incomplete outside that domain. The question of unity in physics is not merely technical. It embodies a profound philosophical commitment, a belief that the universe is not arbitrary, not a collection of disconnected domains with independent rules, but rather a coherent whole governed by discoverable principles. This belief, which has motivated physics since Newton, has proven justified again and again. Yet it also remains an article of faith, in the sense that there is no prior reason to suppose the universe must be unified. It could have been that every phenomenon required its own explanation, its own principles. The fact that it is not, that great diversity flows from simple underlying principles, remains one of the deepest wonders of existence. And as we investigate these binding principles, we also investigate the origins of meaning itself. Why is there something rather than nothing? Why does the universe follow mathematical laws? Why can consciousness understand these laws? These questions transcend physics in the narrow sense, reaching toward philosophy, theology, and the deepest concerns of the human spirit. Yet they are questions that physics, by investigating the fundamental nature of reality, touches upon. In seeking to understand the universe's binding principles, we are also seeking to understand ourselves, what we are made of, how we came to exist, what our place is in the vast cosmos. Part 20. In the Stillness Before Sleep. As we conclude this meditation on CERN's discoveries, we return to the beginning, to the contemplative stillness of the night, when the world is quiet and the mind turns inward, reflecting on the mysteries that surround us. Somewhere beneath the Swiss-French border, the Large Hadron Collider continues its work, night and day, year after year, crashing particles together in pursuit of understanding. Above, in the night sky, the same stars that have guided human inquiry since time immemorial continue their eternal dance, offering their light to anyone who takes the time to look upward and wonder. The anomalies CERN has discovered, these subtle deviations from the predictions of the Standard Model, represent something profound about the human condition and our relationship with the cosmos. They represent our capacity to ask questions about the fundamental nature of reality. They represent our willingness to build great machines and marshal vast resources in service of understanding. They represent the cumulative achievement of human genius, stretched across centuries and applied through the combined efforts of thousands of dedicated researchers. And they represent the humbling recognition that despite all we have learned, there remains far more that we do not know. In the face of such mystery, we might feel a sense of helplessness or despair. The universe is vast beyond comprehension, and our knowledge of it is vanishingly small by comparison. Yet this realization need not lead to despair. Rather, it can inspire awe, a sense of wonder at the beauty and strangeness of existence. It can inspire humility, a recognition that we are small, but also that we are part of something grand. And it can inspire determination, the resolve to continue investigating, to push further into the unknown, to seek to understand. The crack that CERN has found in the edifice of the Standard Model is not a sign of failure or incompleteness in human understanding, though it does reveal incompleteness. Rather, it is a sign that the universe still has secrets to reveal, that the pursuit of knowledge remains alive and vital, that there are genuine mysteries remaining to be solved. And in an age when much seems decided, when conventional wisdom often seems unquestionable, this openness to new discovery, this willingness to have our understanding overturned, is precious. It reminds us that the search for truth is more important than adherence to past certainties. Carl Sagan, whose poetic vision has guided much of this meditation, once wrote that science is a method for testing knowledge against the universe, for separating what we wish to be true from what actually is true. CERN, through its precise experiments and careful measurements, is engaged in exactly this process. It is testing our knowledge of fundamental physics against the universe itself. And the universe, through the anomalies that CERN has detected, is beginning to whisper that our knowledge, while impressive, remains incomplete. As we contemplate these mysteries before sleep comes, we can take comfort in knowing that this process will continue, that future generations of scientists will build upon the work of their predecessors, using ever more powerful tools and deeper insights to probe the mysteries of nature, that the conversation between human consciousness and cosmic reality, conducted through the language of mathematics and experimental verification, will deepen and evolve, that the universe, inexhaustibly strange and wonderful, will continue to reveal its secrets to those patient and dedicated enough to seek them, and that in this seeking, in this sustained effort to understand the fundamental nature of reality, we fulfill something essential in our nature as the universe becomes conscious of itself. Epilogue: The Legacy of Questions. The discoveries at CERN are not endpoints, but waypoints in humanity's long journey toward understanding. The crack that has been found in the Standard Model is not a tragedy but an invitation to probe deeper, to ask harder questions, to push further into the territory that remains unexplored. The physics of the future will stand upon the foundation that today's physicists have built, and future generations will likely look back upon our current understanding as primitive and incomplete, just as we view the physics of a century ago. This is not discouraging, it is exhilarating. It means that the quest will continue, that there will always be new mysteries to investigate, that human inquiry into the fundamental nature of reality will not soon reach an endpoint. It means that young people today, looking at the anomalies CERN has discovered, can see in them the seeds of future discoveries that they might help to cultivate. It means that the enterprise of physics, and more broadly the enterprise of science, remains vital and alive, capable of generating genuine novelty and surprising us with unexpected insights into the structure of the universe. And so we end where we began, in contemplative stillness, recognizing that we stand at a threshold between the known and the unknown. Behind us lies the accumulated understanding of centuries of scientific inquiry. Ahead of us lies territory unmapped and questions unanswered. The anomalies that CERN has discovered are lights pointing into that territory, suggesting paths for future exploration. Whether they lead to revolutionary discoveries or to refined understanding of phenomena already known, they beckon us forward, reminding us that the universe remains ultimately mysterious, that wonder and awe are appropriate responses to the fundamental nature of existence. In the silence and darkness of the night, as the Large Hadron Collider continues its patient work far beneath our feet, and as physicists across the globe continue analyzing data and developing theories, we can rest assured that the human quest to understand the cosmos continues unabated. The crack in the edifice may be the beginning of something magnificent, a deeper theory, a more complete understanding, a revolution in our conception of fundamental reality. Or it may be something more subtle, a refinement and extension of existing frameworks. But either way, it represents the unfolding of the human spirit's greatest adventure, the attempt to understand the universe that birthed us. And in that attempt lies the best of what humanity has to offer.
On a clear night, when you step away from the artificial glow of cities and look upward, you encounter a sight that has moved humans since before we learned to speak about the stars. The night sky presents itself as a dome studded with lights, orderly, eternal, comprehensible. This ancient comfort, this sense that the cosmos is somehow knowable and finite, dissolves instantly once we understand what we are actually seeing. Those pinpricks of light are not mere decoration on a celestial sphere. They are suns, countless suns, each one a furnace of unimaginable proportions, burning through millions of tons of hydrogen every single second, and yet appearing to us as nothing more than a photon or two reaching our patient eyes across incomprehensible distances. Our own sun occupies a peculiar place in this hierarchy. In the human imagination, it is supreme, the giver of all earthly light and warmth, the body around which all meaningful celestial motion occurs. We have built our mythologies upon its apparent supremacy, our calendars around its rhythms, our physics initially upon the assumption that it occupied the center of everything. And yet, the sun is, by the standards of the cosmos, nothing particularly remarkable. It is a yellow dwarf, a classification that immediately identifies it as belonging to the most common category of stars. It is middle-aged, neither young nor ancient on the timescales we are discussing. Its mass is such that it will eventually expand, cool, and fade into darkness, but not for billions of years yet. In short, our sun is ordinary. But the universe, in its incomprehensible vastness, contains objects that defy the ordinariness we have assigned to our own star. There exist in the cosmos stellar bodies so immense, so monumentally vast, that they challenge our cognitive capacity to grasp scale itself. These are the red supergiants and hypergiant stars, objects that represent the most extreme expression of stellar growth that matter can achieve before it collapses under its own weight or explodes in a final, catastrophic discharge of energy. Among these titans, one star stands out, at least for now, as the largest ever directly detected and measured by human observers, Stephenson 2-18. To speak of this star, as we shall in the pages that follow, is to speak of extremity itself. It is to confront the fact that the universe, for all its apparent order and intelligibility, contains phenomena that seem to exist almost as refutations of our expectations. How can something become so large? What physical processes could possibly generate an object so massive yet so tenuous, so luminous yet so diffuse? And, perhaps most profoundly, what does the existence of such objects tell us about the nature of reality itself, about the laws that govern the distribution of matter and energy across billions of light years of space and time? These are the questions we shall explore. We shall move from the theoretical frameworks that allow us to understand stellar evolution to the observational techniques that permit us to detect these distant objects, to the specific case of Stephenson 2 to 18 itself. And, perhaps most importantly, we shall allow ourselves to stand in wonder before the sheer scale and majesty of what we are contemplating, a wonder that is not antagonistic to scientific understanding, but rather its proper companion and completion. To understand how a star could possibly grow to the size of Stephenson 2 to 18, we must first understand how stars work, how they are born, how they age, and what determines the ultimate fate of each individual stellar object. The history of this understanding is itself a remarkable testament to human ingenuity, for we cannot travel to the stars, cannot sample them, cannot conduct experiments upon them. All we can do is observe them, measure the light they emit, and use the laws of physics to infer their properties. That we have succeeded as well as we have in this task speaks to the predictive power of our scientific understanding. A star is, at its most fundamental level, a sphere of gas held together by its own gravitational attraction. The larger the sphere of gas, the greater the weight it bears at its center, and therefore the higher the temperature and pressure in the core. When a cloud of gas contracts under gravity, which is what happens during star formation, it heats up. If the cloud contains enough mass, the temperature at the center will eventually reach the point at which nuclear fusion can occur. Hydrogen nuclei will fuse together, combining into helium, and in the process, releasing enormous quantities of energy in the form of radiation. This outward pressure of radiation, pushing against the inward crush of gravity, creates a balance. The star settles into a state of equilibrium, and for the duration of its main sequence lifetime, the period in which hydrogen fuses into helium, this balance holds. It is a remarkably stable state, one that can persist for billions of years. Our own Sun is currently in this main sequence phase, a phase that it has inhabited for approximately 4.6 billion years, and will remain in for another 5 billion years or so. For most of a star's life, it remains relatively stable in size and luminosity. However, this stability cannot last forever. Stars are creatures of change, and the changes that come at the end of the main sequence are among the most violent transformations that the universe has to offer. The key to understanding what happens at this stage lies in recognizing that a star is constantly burning through its fuel. The hydrogen in the core is being converted into helium, and this is a one-way process. Eventually, and for a star with the mass of our Sun, this takes roughly 10 billion years, the hydrogen begins to run out. The core, now composed primarily of helium, contracts further under gravity. As it contracts, it heats up. If the temperature becomes high enough, helium begins to fuse into carbon and oxygen. This ignition of helium fusion provides a new source of outward pressure, but it also sets in motion a series of changes that fundamentally alter the structure of the star. For massive stars, those containing many times the mass of our Sun, this process unfolds much more rapidly, and the subsequent transformations are far more extreme. A star with 20 times the Sun's mass, for instance, will exhaust its main sequence, hydrogen, in only a few million years. Once that fuel is depleted, the core contracts and heats, and helium fusion begins. When the helium is nearly exhausted, the core contracts and heats again, and carbon fusion commences. This cycle continues, with each new fuel consuming itself in turn, with each contraction making the star's core hotter and more violent. The star expands and contracts, swinging through different configurations, burning through heavier and heavier elements, carbon, neon, magnesium, silicon, iron. With each new stage of fusion, the outer layers of the star become more turbulent, more extended. The star swells. It grows. It expands outward into the space surrounding it. This is how red giants are created. These are stars that have exhausted the hydrogen fuel in their cores and have entered the phase of helium burning and beyond. Their outer atmospheres expand dramatically, cooling as they do. This cooling causes them to glow with a characteristic red light that gives them their name, the longer wavelengths that characterize a cooler object. A red giant can be truly enormous. Our Sun, when it becomes a red giant, will swell to a size that will likely engulf Mercury and Venus, and possibly Earth as well. We can observe red giants in the night sky, the most famous being Betelgeuse, the red supergiant that marks the shoulder of the constellation Orion. But the story does not end with red giants. For very massive stars, even more extreme evolution awaits. A star must reach a certain mass, roughly 8 times the mass of our Sun, in order to eventually produce a red supergiant, the next step up in the hierarchy of stellar size and drama. Red supergiants are among the largest and most luminous objects in the universe. Some of them have radii 500, 600, even 700 times larger than our Sun. This means that if you were to place such a star at the center of our solar system, its surface would extend well beyond the orbit of Jupiter. The sheer physical size of these objects strains credulity. How can something be so large? And yet, there they are, radiating enormous quantities of light into space, burning through their fuel at prodigious rates, living out the final act of their existence in spectacular fashion. The reason that red supergiants can grow so large is related to the particular phase of stellar evolution in which they exist. They are in the throes of fusing carbon, oxygen, silicon, and other elements. Between each stage of fusion, the core contracts, heats up, and ignites the next fuel. But each contraction also causes the outer layers to respond to the change in pressure support from the core. The outer layers expand and cool. The star bloats. Eventually, it contracts again, but the contraction is never quite complete. The star never quite returns to its previous size. Over the course of the star's final million years or so, before it explodes as a supernova, it can grow to astonishing dimensions. This is the regime in which we find the most extreme stars known to humanity, the red supergiants and the hypergiant stars. These are the most luminous, the most extended, and the most massive stars that current models of stellar evolution predict should exist. And yet, even here, at the frontier of stellar extremity, we find that nature has managed to exceed our expectations. The largest stars we know of are genuinely, bewilderingly enormous. Before we can meaningfully discuss the largest star ever discovered, we must address the question of how we actually measure stellar size. This is not, in fact, a trivial problem. Stars are extraordinarily distant objects. The nearest star to us other than the Sun, Proxima Centauri, is more than 4 light-years away. This means that the light we see from it today was emitted 4 years ago, when the star has moved since then, but the light has been traveling through the darkness of space for all that time before reaching us. For a star that is thousands of light-years away, and Stephenson 2 to 18 is indeed at such distances, the light it emits takes thousands of years to reach Earth. Furthermore, even for the nearest stars, direct telescopic observation of stellar disks is extremely difficult. The stars are so distant that they appear as point sources of light, even through our most powerful telescopes. We cannot simply point a telescope at a star and see a disk and measure its angular diameter the way we would measure the angular diameter of the moon. Rather, we must use indirect methods, each of which has its own limitations and sources of uncertainty. One of the earliest and most powerful indirect methods for measuring the sizes of stars is the use of eclipsing binary systems. When 2 stars orbit one another, and their orbital plane happens to be aligned with Earth such that they eclipse each other from our perspective, we gain valuable information. As one star passes in front of the other, the light we receive changes. By carefully observing these light curves, the pattern of light changes over time. We can determine the sizes of the 2 stars, because the duration of the eclipse tells us how long it takes for one star to pass in front of the other, which tells us something about their relative sizes and their orbital speeds. This method is reliable and has been used for more than a century to measure stellar radii. Another method involves the use of spectroscopy, the analysis of light broken down into its component wavelengths. By studying the spectrum of a star, we can determine what elements it contains, how hot its surface is, and other physical properties. In particular, the width of spectral lines tells us about the temperature and density of the star's atmosphere. For very large stars with low surface gravities, this can give us information about the star's radius, since for a star of a given mass, the surface gravity is inversely related to the radius squared. A larger star has lower surface gravity than a smaller star of the same mass. But the most powerful modern method for measuring stellar size is interferometry. Interferometry exploits the wave nature of light. When light from 2 points passes through apertures and then recombines, the waves interfere with one another, creating a pattern of bright and dark fringes. By analyzing this interference pattern, it is possible to determine the angular size of the object from which the light originated. When multiple telescopes are used together in an interferometric array, the effective size of the observations can be dramatically increased, allowing for much finer angular resolution than any single telescope could achieve. Stellar interferometry has become increasingly sophisticated over the past few decades. Facilities like the Very Large Telescope Interferometer in Chile and the Chara array in the United States have revolutionized our ability to measure the angular diameters of stars, particularly giant and supergiant stars that are relatively nearby. By measuring the angular diameter of a star and knowing its distance, typically determined using the parallax method, in which the apparent shift in a star's position as Earth orbits the Sun is measured, we can calculate the actual physical size of the star. It is important to recognize that these measurements come with uncertainties. The distance measurement can be uncertain, the angular diameter measurement has limitations in precision, and the definition of the stellar surface itself is somewhat ambiguous. A star does not have a sharp, well-defined edge the way a planet does, but rather a gradient from the dense, hot interior through the tenuous, cool outer atmosphere. Nevertheless, modern measurements have achieved a level of precision that allows us to meaningfully rank stars by size, and to detect subtle changes in stellar properties over time. It is by means of these techniques, particularly stellar interferometry combined with distance measurements from parallax and other methods, that we have been able to identify and measure the largest stars known to exist. And it is through the application of these techniques that we have come to know Stephenson 2-18 as the champion of stellar size, at least as of the time of writing. In the year 2019, a team of astronomers announced the discovery of what appeared to be the largest star ever definitively measured. The star bore the designation Stephenson 2-18, having been identified during a systematic survey of previously known stellar objects. The name follows a particular nomenclature, and #X201c, Stephenson, and #X201d refers to one of the star catalogs in which it appears. The N #X201c, 2 and #X201d indicates that it was the second such catalog the discoverers were examining, and #X201c, 18 and #X201d is simply a sequential number assigned to this particular object within that catalog. Stephenson 2-18 is a red supergiant star located approximately 19,000 light-years away in the constellation of Scutum, in the equatorial region of the Milky Way galaxy. To put this distance in perspective, the light we see from Stephenson 2-18 today was emitted when the most advanced human civilization on Earth was the ancient Egyptian Empire, during the reign of the pharaohs, and the age before writing had spread widely through the ancient world. For 19,000 years, this light has been traveling through the darkness of space, crossing the vast distances between the stars, passing through the dust and gas of the interstellar medium, until at last it arrived in our solar system and was detected by human instruments. Stephenson 2 to 18 has a radius that is estimated to be approximately 2,150 times the radius of our Sun. To express this in more concrete terms, if the Sun were the size of a grain of sand, Stephenson 2 to 18 would be a sphere approximately 4.3 meters, about 14 feet, in diameter. If we place Stephenson 2 to 18 at the center of our solar system, its surface would extend well past the orbit of Jupiter, far beyond the realm of the terrestrial planets, beyond the asteroid belt, and into the region of the gas giants. In fact, it would extend so far that if we could somehow shrink Stephenson 2 to 18 slightly and position it in our solar system, it would engulf not only Jupiter but also Saturn. The volume of such an object is almost incomprehensibly vast. The mass of Stephenson 2 to 18 is estimated to be approximately 19 times the mass of the Sun. This seems contradictory at first. How can something be so much larger in size, and yet not be proportionally larger in mass? The answer lies in the fact that Stephenson 2 to 18, as a red supergiant in the advanced stages of its evolution, has become extremely diffuse. Its density is extraordinarily low. The outer layers of the star are composed of gas that is far less dense than the air we breathe. If one were somehow able to move through this stellar atmosphere, which would be impossible as the temperatures are still immensely high, thousands of degrees, one would not feel any significant resistance from the gas, because the density is so low. The star has expanded so much that all of its material has been spread over an enormous volume, resulting in an average density that is minuscule by terrestrial standards. The luminosity of Stephenson 2 to 18 is astonishing. The star shines with a brightness that is approximately 440,000 times greater than the Sun. This means that although Stephenson 2 to 18 is much cooler than the Sun on its surface, a red supergiant has a surface temperature of only about 3,200 Kelvin, compared to the Sun's 5,800 Kelvin. It is so much larger that the total amount of light energy it radiates is far greater. The star is burning through its fuel at a prodigious rate. If the Sun were replaced by Stephenson 2 to 18, even at its distance, Earth would be burned to a cinder immediately. The equilibrium of our planetary system, maintained by the particular characteristics of our Sun's light and heat, would be utterly destroyed. Stephenson 2 to 18 is nearing the end of its life. Stars of this character, massive, extended red supergiants, are not stable in the long term. Within a cosmically short time, perhaps within the next million years or so, the processes occurring in the core of Stephenson 2 to 18 will reach a point of no return. The iron core will become destabilized. The nuclear burning will accelerate toward a critical point. And then, in a moment of cosmic drama that will outshine entire galaxies for a brief period of time, Stephenson 2 to 18 will explode as a supernova. This explosion will scatter the elements synthesized in the star's core throughout the surrounding space. New stars may eventually form from this material. Planets may orbit those new stars. Life may emerge. And thus does the cycle of stellar creation and destruction continue, turning stars into dust, and dust into stars again. But Stephenson 2 to 18 is not, in fact, the only contender for the title of largest star. In the years since its discovery, other candidates have emerged. The universe seems to contain a population of extraordinarily large red supergiant stars, each pushing the boundaries of what our current theories of stellar evolution predict should be possible. Understanding these objects, and understanding why they are as large as they are, represents a frontier in modern astrophysics. One of the most famous and well-studied of these giant stars is Betelgeuse, the red supergiant that marks the shoulder of the constellation Orion. Betelgeuse is close enough, at a distance of about 700 light-years, and large enough that it has been the subject of intense observational scrutiny. It has a radius of approximately 700 times the Sun's radius, making it substantially smaller than Stephenson 2 to 18, but still an object of tremendous size and astronomical significance. Betelgeuse is so large that it would engulf the orbit of Mars if it were placed at the center of our solar system. It is also one of the brightest stars visible to the naked eye in the Earth's night sky, which speaks to its tremendous luminosity. Betelgeuse is famous among astronomers as a star in the final stages of its evolution, one that is expected to explode as a supernova at any time in cosmological terms, within the next 1,000 years, or the next 100,000 years, or perhaps even sooner. Another notable contender is Antares, which is also a red supergiant, located in the constellation Scorpius. Antares has a radius estimated to be between 700 and 900 solar radii, again placing it in the same general class of objects as Stephenson 2-18, but considerably smaller. Like Betelgeuse, Antares is a bright naked-eye star and has been known to human observers since antiquity. The ancients did not understand, of course, that they were looking at a star of such tremendous proportions. To them, it was simply a star in the sky, perhaps remarkable for its reddish color, but otherwise just one point of light among countless others. Moving further up the size hierarchy, we encounter stars like Mu Cephei, a red supergiant with a radius approximately 1,650 times that of the Sun. This star is quite distant and cannot be seen with the naked eye, but through telescopes it can be observed. Its size places it among the largest stars known, though not quite at the extreme end of the distribution. There is also Canis Majoris, another red supergiant with a radius estimated to be around 1,420 solar radii. The measurements of these stars are somewhat uncertain. The exact size depends on how the boundary of the star is defined and on the precision of the distance measurements, but they are certainly among the most enormous objects in the universe. But Stephenson 2-18 surpasses all of these. With its estimated radius of approximately 2,150 solar radii, it occupies a place of apparent supremacy in the current census of known stellar sizes. There have been other candidates proposed over the years. Stephenson 2-18 itself was not always recognized as the largest, and there have been debate and discussion within the astronomical community about which stars deserve the title. Some of these debates hinge on the precision of measurements, on the methods used to determine distance, and on the definition of the stellar radius itself. But at this moment in time, by the most careful measurements available, Stephenson 2-18 appears to be the champion. It is worth noting, however, that the title of and #X201c, largest star, and #X201d is somewhat contested and continually subject to revision. As our measuring instruments improve, as our understanding of stellar physics deepens, and as we discover more stars, the rankings can change. A star discovered tomorrow might prove to be larger than Stephenson 2-18. Or, with better measurements, we might revise our understanding of Stephenson 2-18 itself downward. The universe, it seems, is always willing to surprise us, to exceed our expectations and challenge our assumptions. In this sense, the title of and #X201c, largest star, and #X201d is not a permanent crown, but rather a crown that sits uneasily on the head of whichever star currently holds the distinction, always subject to be taken away. At this point, it is worthwhile to pause and consider a deeper question. Why do stars like Stephenson 2-18 exist at all? Why should there be such a thing as a star with a radius of 2,150 solar radii? Our current models of stellar evolution predict the existence of red supergiants, stars in late stages of stellar evolution, having exhausted the hydrogen in their cores and progressed through phases of helium, carbon, and other element fusion. These models predict that such stars should be quite large, perhaps 500 to 1,000 times the size of the Sun. But do they predict that they should be as large as Stephenson 2-18 appears to be? This is, in fact, an active area of research in stellar astrophysics. The existence of ultragiant stars, like Stephenson 2-18, challenges the existing models of stellar evolution in certain respects. The stars appear to be significantly larger than the current models predict they should be. There are several possible explanations for this discrepancy. One possibility is that the measurements are somehow off, that our estimates of the stellar radii are too large. Another possibility is that our models are incomplete, that we are missing some physical process or phenomenon that would allow stars to grow even larger than we have previously suspected. A third possibility is that these ultra-giant stars are somewhat unusual in their properties, perhaps in their mass loss rates or their composition, in ways that cause them to expand more than typical red supergiants. The key to understanding how a red supergiant can become so large lies in understanding the nature of stellar structure and the balance of forces within a star. At every point within a star, the outward pressure of the gas, created by thermal motion and radiation pressure, must balance the inward crush of gravity. If the outward pressure is greater than the inward gravitational force, the star will expand. If the inward gravitational force is greater, the star will contract. In equilibrium, these forces balance. In the envelope of a red supergiant like Stephenson 2-18, the temperature is relatively cool compared to the core, several thousand Kelvin rather than millions, but the pressure is still substantial. The star's structure in these outer regions is supported by radiation pressure, created by the flood of radiation flowing outward from the hot core. The atmosphere of the star is quite extended, expanding over enormous distances. A critical factor in determining how large a red supergiant can become is the rate at which it loses mass. All stars lose mass to some degree. The Sun, for instance, loses approximately 1 million tons of material per second in the form of the solar wind, though this is merely a whisper compared to the Sun's total mass. But massive stars, and particularly red supergiants, can lose mass at truly prodigious rates. A red supergiant might lose many times the mass of Earth every year. This mass loss occurs in the form of a strong stellar wind, driven by radiation pressure in the star's atmosphere. The radiation from the star is so intense that it pushes against the material in the star's outer layers, accelerating it outward. As a star loses mass, the gravitational force that holds its outer layers becomes weaker. A star with less mass has less gravity, so it is harder to hold material in as tightly. This means that the star can become even more extended. The extended atmosphere becomes more tenuous, and the star swells further. There is a feedback mechanism here. As the star expands, its surface gravity decreases, the outer layers become more susceptible to being blown away by the stellar wind, more mass is lost, the gravitational hold is weakened further, and the star expands even more. This process cannot continue indefinitely. At some point, the star will lose so much mass that it will transition from a red supergiant to a different type of object. Eventually, a star in this phase will undergo core collapse and explode as a supernova, destroying itself in a cataclysmic explosion. The end point of this process marks the end of the star's life as a distinct object. But before that end point is reached, the star can spend a relatively brief period as an ultragiant, as a star of almost incomprehensible proportions, before it passes away. There is also the possibility that some of the largest stars we observe are in binary systems, that they are not single stars, but rather part of a pair of stars orbiting one another. If one star in a binary system is a red supergiant, and the two stars are close enough, material can flow from the red supergiant to its companion. This mass transfer can affect the evolution of both stars. Some theorists have speculated that certain of the extreme ultragiant stars might be in such configurations, and that the mass transfer and the resulting changes in structure might contribute to their exceptional sizes. However, Stephenson 2-18 appears to be a single star, not a member of a binary system, so this cannot explain its extraordinary dimensions. Understanding the precise mechanisms that allow stars like Stephenson 2 to 18, to reach their enormous sizes remains an open question in stellar astrophysics. The existence of these objects is, in a very real sense, pushing on the boundaries of our knowledge, forcing us to refine our models and deepen our understanding of how matter and energy behave under the most extreme conditions. To truly appreciate the significance of Stephenson 2 to 18, it is important to place it within the larger context of the cosmos, to understand not just what this star is, but what its existence tells us about the universe as a whole. The question of how large a star can grow is intimately connected to the question of what kinds of objects the universe produces, and what the distribution of those objects tells us about the fundamental processes of creation, evolution, and destruction that govern the cosmos. The universe contains an almost incomprehensibly large number of stars. Our Milky Way galaxy alone contains an estimated 200 to 400 billion stars. This is already a staggering number. If you were to count one star per second, it would take you roughly 6 million years to count them all. Yet the Milky Way is not unique. The observable universe contains hundreds of billions of galaxies, each with hundreds of billions of stars. The total number of stars visible to our telescopes is on the order of 10 to the power of 24 or more, a septillion stars, if one prefers the naming convention. This is a number so large that the human mind cannot truly grasp it. It exceeds by many orders of magnitude the number of grains of sand on all the beaches of Earth. Among this staggering multitude of stars, there are representatives of every possible type and class. There are tiny white dwarfs, the remnants of stars that have shed their outer layers and left only their ultra-dense cores. These objects are so compact that a teaspoon of white dwarf material would weigh as much as an elephant. There are neutron stars, the remnants of massive stellar explosions, where matter is compressed to such densities that electrons are forced to merge with protons to form neutrons. A neutron star with a mass of 1 billion tons is compressed to a sphere only about 20 kilometers in diameter. And there are black holes, the ultimate fate of the most massive stars, objects where space and time are so warped that not even light can escape once it crosses the event horizon. But there are also stars like Stephenson 2 to 18, stars at the other extreme of stellar properties. Whereas white dwarfs, neutron stars, and black holes represent the extreme of compactness and density, red supergiants and ultragiant stars represent the extreme of extensiveness and diffuseness. They are so large, so spread out, that they would seem to be almost the opposite of a neutron star or black hole. And yet, both extremes are equally real, equally important to understanding the fullness of what the universe contains. The existence of Stephenson 2 to 18 and stars like it tells us that the universe, in its prodigious fertility, is capable of producing objects that challenge our intuitions and exceed our expectations. We live in a universe that is not content to produce objects of merely reasonable proportions. It produces stars that are thousands of times larger than our own sun, that glow with the light of hundreds of thousands of suns, that will eventually explode and scatter their matter across thousands of light years of space. The universe is, in this sense, profligate. It is generous in the extreme. It does not hesitate to push phenomena to their limits. There is a profound lesson here, one that extends beyond astronomy. The universe, taken as a whole, is a place of extremity and exuberance. It produces not just the ordinary and the typical, but also the extraordinary and the exceptional. Life itself, perhaps, owes its existence to this principle, that the universe is willing to explore, to its vastness and diversity, every possibility that the laws of physics permit. Stars like Stephenson 2 to 18 are not aberrations or anomalies in a cosmos of mediocrity. They are expressions of the universe's fundamental creative power. The discovery of Stephenson 2 to 18 raises an important question. How did we come to identify and measure this star? How did this particular object distinguish itself from the countless other stars in the night sky? The answer involves a combination of systematic survey work, archival analysis, and the application of modern observational techniques. Stephenson 2-18 was not discovered as a new object that had suddenly come into view. Rather, it was identified in existing catalogs, databases of known stars that had been compiled over many years by various astronomical surveys. The star had been observed before by various telescopes and instruments, but had not been systematically analyzed to determine its size and distance. The identification of Stephenson 2-18 as the largest known star involved going through existing data, applying new analysis techniques, and making careful measurements using the best available observational tools. The method used to determine Stephenson 2-18 size involved stellar interferometry combined with spectroscopic analysis and distance measurements. By analyzing the spectrum of the star, astronomers could determine its surface temperature and other properties. By using stellar interferometry, they could measure the angular diameter of the star as seen from Earth, how large an angle the star subtends in the sky from our perspective. And by measuring the parallax of the star, the apparent shift in its position as Earth orbits the Sun, they could determine its distance. Once these three pieces of information are available, the angular diameter of the star, its distance from Earth, and some understanding of how the angular diameter relates to the physical radius, which depends on how we define the stellar surface, it is possible to calculate the actual physical radius of the star. For Stephenson 2-18, these calculations yielded a radius of approximately 2,150 solar radii, placing it at the extreme end of the size distribution for known stars. It is worth noting that this measurement, like all astronomical measurements, comes with uncertainties. The radius of Stephenson 2-18 might be as low as about 2,000 solar radii or as high as about 2,300 solar radii, depending on the particular methods and assumptions used. But even with these uncertainties, the star is clearly exceptional, far larger than the vast majority of known stars. It is in the category of the ultra-giant stars, the most extended objects known to science. The story of Stephenson 2-18 is, in many ways, a representative example of how modern astronomy works. We do not discover the secrets of the universe through sudden, dramatic revelations, but rather through patient, systematic observation combined with careful analysis and the application of mathematical models. We gather data across many wavelengths of light, visible light, infrared, radio waves, using multiple instruments and techniques. We compile this data into catalogs and databases. We apply increasingly sophisticated analysis methods. And gradually, the universe reveals its secrets. The discovery of Stephenson 2-18 and the careful measurement of its properties represents not a sudden breakthrough but rather a culmination of many decades of work by many astronomers and many institutions, all contributing to the gradual expansion of human knowledge about the cosmos. It represents, in a sense, the triumph of the scientific method, the idea that by careful observation, by precise measurement, by honest evaluation of evidence and honest acknowledgement of uncertainty, we can come to understand even the most distant and exotic objects in the universe. Stephenson 2-18 is not an eternal object. Stars do not endure forever. They are born from clouds of gas and dust. They live their lives in various configurations and stages of evolution, and ultimately they die. For a star like Stephenson 2-18, the end is not far away by cosmic standards. The star is in the final chapter of its existence, racing through the last phases of nuclear fusion in its core. The nuclear processes occurring in the core of Stephenson 2-18 are in their final stages. The star has already burned through hydrogen and helium, and is now fusing heavier elements, carbon, oxygen, silicon, and others. Each stage of fusion proceeds at an accelerating pace. The helium in the core of a red supergiant like Stephenson 2-18 is burned up in a few million years, whereas the hydrogen in the core of a main sequence star like our Sun lasts for billions of years. The later stages of fusion occur even more rapidly. Eventually, the core of Stephenson 2 to 18 will become largely composed of iron. Iron is the endpoint of nuclear fusion that releases energy. Fusing iron requires energy rather than releasing it. At this point, the core can no longer be supported by radiation pressure from nuclear burning. The core becomes unstable. It collapses catastrophically. In a fraction of a second, the entire core of the star, containing the mass of roughly 20 suns, is compressed from a size comparable to that of Earth to a size smaller than a mountain, and then smaller still. The collapse is halted only when the density becomes so extreme that the pressure of degenerate matter compressed beyond the point where further compression is possible, can provide support. A core bounce occurs, and a shockwave propagates outward through the star. This shockwave will blow the star apart. The outer layers of Stephenson 2 to 18, which encompass so much space and contain so much material, will be accelerated outward at speeds of 30,000 kilometers per second or more. The explosion will be almost incomprehensibly violent. For a period of weeks or months, Stephenson 2 to 18 will outshine entire galaxies. The light from the supernova explosion will travel outward in all directions, including toward Earth, and when it arrives, thousands of years from now, it will be visible from Earth, even in the presence of sunlight, as a bright point of light in the daytime sky. The material ejected from the supernova explosion of Stephenson 2 to 18 will eventually slow down and cool. The hot gas and plasma will gradually merge with the interstellar medium, the gas and dust between the stars. Over thousands and millions of years, this material will mix with the surrounding gas and dust, enriching it with the heavy elements synthesized in the star's core. New clouds of gas will form from this enriched material. New stars will be born. Some of these new stars will have planetary systems. And perhaps, on some of those planets, life will emerge. And thus the cycle continues. Stars are born from the ashes of their predecessors, living their lives and eventually returning their matter to the cosmos, to be recycled into new stars and new worlds. This is the ultimate fate that awaits Stephenson 2 to 18, not in the near future, perhaps not for another 100,000 years or more, but inevitably. The extraordinary star that holds the title of the largest known star in the universe is in the process of transforming, undergoing the final chapters of its existence. And when it does transform, when it does explode, the universe will witness a cataclysm, a spectacular exhibition of the awesome power of stellar death. The existence of Stephenson 2 to 18 and of other ultra-giant stars raises a question that extends beyond astronomy into theoretical physics. Is there an upper limit to how large a star can grow? Is there some physical principle that sets a maximum size? Or can stars, in principle, grow indefinitely, limited only by the amount of material available to them? The current understanding is that there are indeed limits, though these limits are not as strict as one might initially expect. One major constraint is that a star must have sufficient mass to support itself against gravitational collapse. A star must be massive enough that the temperature and pressure in its interior are high enough to sustain nuclear fusion, at least at some point in its life. Stars with masses less than about 0.08 solar masses will never reach the temperature required for hydrogen fusion, and will instead become brown dwarfs, objects that are somewhat star-like, but do not qualify as true stars because they never undergo nuclear burning. However, for stars above this minimum mass, there is no corresponding maximum. There is no hard ceiling above which stars cannot exist. Very massive stars, those with masses of 100, 200, or even 300 solar masses, appear to exist in nature, though they are rare. Such massive stars burn their fuel rapidly, live short lives measured in millions of years rather than billions, and end their existences in cataclysmic supernovae. At the high mass end, there are theoretical limits imposed by the extreme radiation pressure in the stellar interior. If a star becomes too massive, the radiation pressure in its core becomes so extreme that it can overcome the binding effect of gravity, and the star simply blows itself apart in what is sometimes called a parinstability supernova or photodisintegration supernova. This process is thought to occur in stars above about 140 solar masses, or perhaps higher, depending on the star's composition and other factors. Thus, there is an upper limit on stellar mass, though the exact location of this limit is an active area of theoretical research. But the limits on stellar size are somewhat different from the limits on stellar mass. A star's size depends not just on its mass, but also on its evolutionary state. A star with a given mass will be relatively compact while bearing hydrogen in its core, larger as it becomes a red giant, and even larger if it becomes a red supergiant. The size is determined by the balance between the outward pressure from nuclear burning and radiation, and the inward crush of gravity. As a star loses mass through stellar winds, its surface gravity decreases, and it can expand even further. For red supergiants, there appear to be practical, though not absolute, limits on size. The most massive red supergiants, with initial masses above about 40 solar masses, will undergo core collapse and explode as supernovae before they can expand to the most extreme sizes. Red supergiants with slightly lower initial masses can grow larger, because they have more time in the red supergiant phase before they explode. But eventually, all red supergiants will reach a point where the balance of forces in their interiors becomes unstable, and they will undergo core collapse and supernova explosion. Stephenson 2-18, with its radius of 2,150 solar radii, represents the current observational record for stellar size. But it is likely not the absolute limit. Theoretical models suggest that stars could potentially grow somewhat larger, perhaps to radii of 2,500 or 3,000 solar radii, if conditions were right. But such extreme sizes are probably rare, because they require a particular combination of mass, composition, and evolutionary timing to achieve. Most red supergiants remain somewhat smaller. The question of stellar size limits is not merely an abstract theoretical question. It connects to fundamental issues in stellar astrophysics. What determines the structure of a star? How do radiation and gravity interact to shape stellar configurations? What happens at the extremes of the parameter space that nature explores? By studying objects like Stephenson 2-18, objects that push on the boundaries of what we thought was possible, we improve our understanding of these fundamental questions. To stand before the facts of Stephenson 2-18 and contemplate them seriously is to encounter, in a very visceral way, the strangeness of our universe. We live on a small planet orbiting an ordinary star. Our star is one of hundreds of billions in our galaxy. Our galaxy is one of hundreds of billions in the universe. And within this almost incomprehensibly vast cosmos, there exist objects like Stephenson 2-18, stars so enormously large that the human mind struggles to process what is being claimed about them. What does it mean to say that Stephenson 2-18 has a radius of 2,150 solar radii? We have offered some comparisons. If the Sun were a grain of sand, Stephenson 2-18 would be a sphere about 14 feet in diameter. If Stephenson 2-18 were placed at the center of our solar system, its surface would extend far beyond Jupiter. These comparisons are useful, but they do not quite convey the full strangeness of what we are discussing. There is something about the sheer numerical scale of these objects that exceeds our normal capacity for geometric visualization. The volume of Stephenson 2-18 is so vast that it is difficult to express in familiar terms. The volume of a sphere is proportional to the cube of its radius. If Stephenson 2-18 has a radius 2,150 times that of the Sun, then its volume is roughly 2,150 cubed, That is, roughly 10 billion times the volume of the Sun. To put this in perspective, if you could somehow hollow out Stephenson 2 to 18 and fill it with Earths, you could fit roughly 5 billion Earths inside. If you line up Earths along the diameter of Stephenson 2 to 18, you would need about 4,300 Earths to stretch across. And yet, despite this enormous volume, Stephenson 2 to 18 is not particularly massive. It contains only about 19 solar masses of material. This means that the average density of Stephenson 2 to 18 is extraordinarily low. The density is roughly 10 billion times lower than the density of water. In fact, Stephenson 2 to 18 is so diffuse that it is less dense than many gases at Earth's surface. If you were somehow able to exist in the outer layers of Stephenson 2 to 18 without being destroyed by the intense heat, you would not encounter the resistance of a dense solid or even a dense gas. You would move through a medium so rarefied that it would be difficult to perceive as anything but nearly empty space. This combination of enormous size with relatively low mass and density is one of the most striking features of stars, like Stephenson 2 to 18. It reveals something profound about the nature of gravity and structure. The gravity holding Stephenson 2 to 18 together is quite weak. A spacecraft could, in principle, escape from the surface of such a star with a speed slower than a jet airplane. And yet, gravity still holds the star together. Gravity, the weakest of all fundamental forces on atomic scales, nonetheless holds sway over objects of such tremendous size that they dwarf our imagination. In a sense, Stephenson 2 to 18 is an illustration of gravity's dominion. No matter how large an object becomes, gravity continues to shape its structure. To contemplate Stephenson 2 to 18 is also to contemplate the nature of light and energy. This star, despite its low density and low surface temperature, shines with a brightness 440,000 times greater than the Sun. It does so because of its enormous size. Every square meter of the star's surface, though cooler than the Sun's surface, radiates energy. And because the star has such an enormous surface area, the total energy radiated is tremendous. If this star were placed at the distance of the Sun, it would deliver about 440,000 times as much energy to Earth as the actual Sun does. Life as we know it could not exist in such a world. In all of these ways, Stephenson 2 to 18 is a challenge to our understanding, a limit case that tests the boundaries of what we thought was possible. It is also a source of profound wonder. When we look upon the facts of this star, its size, its brightness, its position in our galaxy, we are confronted with the grandeur and exuberance of the physical universe. We are reminded that we live in a cosmos that is not merely large but truly immense, not merely diverse but genuinely alien to our everyday experience. The discovery and careful measurement of Stephenson 2 to 18 represents not a conclusion, but a step on a longer journey of discovery. The future of stellar astronomy holds the promise of identifying even more extreme objects, of refining our measurements of existing objects, and of deepening our theoretical understanding of how stars work. New technologies and observational techniques are being developed that will allow astronomers to see further into space and to measure stellar properties with greater precision than ever before. One particularly promising approach involves the use of space-based interferometry. Currently, the most powerful stellar interferometric facilities are based on Earth, limited by the Earth's atmosphere and the need to use Earth-based observing locations. But future space-based observatories, with multiple instruments flying in formation in space and communicating with each other, could achieve angular resolution far superior to anything available today. These facilities would be able to measure the diameters of distant stars with unprecedented precision, and to study the structure and evolution of stellar atmospheres in detail that is simply not possible today. Improvements in our theoretical understanding of stellar evolution are also anticipated. Current models of stellar evolution, while quite sophisticated, have limitations. They do not always perfectly predict the observed properties of stars. By comparing detailed observations of real stars with theoretical models, and by iteratively refining the models to better match the observations, astrophysicists hope to arrive at increasingly accurate descriptions of how stars work. This process is expected to continue for many years. There is also the possibility that new statistical techniques and machine learning algorithms could be applied to the enormous catalogs of stellar data that modern surveys have generated. These techniques might reveal patterns in the data that human analysis has missed, or might identify peculiar objects worthy of follow-up observation. The automated survey facilities that are continuously scanning the sky could potentially discover new stellar giants. It is entirely possible that a star larger than Stephenson 2-18 will be discovered and properly measured in the coming years or decades. The title of an #X201c, largest known star, and #X201d, is not a permanent crown, but rather a prize that goes to whichever star currently holds the distinction. The universe may well have other surprises in store. But whether or not Stephenson 2-18 retains its title, the significance of this star is not diminished. It remains one of the most remarkable stellar objects known, a limit case that illuminates the extremes of stellar existence. In a broader sense, the study of extreme objects like Stephenson 2-18 is valuable not just for its own sake, but because it challenges our theoretical frameworks and forces us to think more carefully about the principles that govern stellar structure and evolution. Science advances not just through the steady accumulation of observations, but through encounters with phenomena that surprise us, that do not fit our expectations, that push us to revise our understanding. Stephenson 2-18 is precisely such an object. It is a gift to science, a puzzle to be solved, a window into the deepest workings of the cosmos. We began this inquiry with a question: how can something become so large? How can a single object, held together by nothing more than its own gravity, expand to the proportions of Stephenson 2-18? Through the course of our exploration, we have traced the path by which stars grow and evolve, by which they progress through stages of increasing size and luminosity, by which they approach the limits of what gravity and nuclear burning can maintain. Stephenson 2-18 is the largest star known. At the present moment, in the early decades of the 21st century, after centuries of astronomy and decades of detailed modern study, this is the object that holds that distinction. Its radius is approximately 2,150 times the radius of the Sun. Its luminosity is approximately 440,000 times the luminosity of the Sun. It is composed primarily of hydrogen and helium, with smaller quantities of heavier elements. It is located approximately 19,000 light-years away, in a region of the Milky Way that is rich in young, massive stars, and the remnants of stellar explosions. To know about Stephenson 2-18 is to know something profound about the nature of our universe. It is to understand that the cosmos is not a place of modest proportions and quiet stability, but rather a place of extremity and exuberance. It is to recognize that the universe, given the freedom that the laws of physics permit, will explore possibilities that exceed our imagination. In the existence of Stephenson 2-18, we see evidence of this creative power of nature, this willingness to produce objects that are genuinely, almost bewilderingly extreme. When we look up at the night sky, our eyes receive light that has traveled across vast distances of space and time. Most of what we see are ordinary stars, like our own Sun, stars that have passed through their main sequence phase, and are either now in that phase, or are yet to be born. But some of the light we receive comes from more distant regions, from stars that are intrinsically far brighter than those nearby, and thus remain visible despite their distance. And among these distant stars, burning with tremendous luminosity, are objects like Stephenson 2-18, stars in the final stages of their existence, stars that will not endure for billions of years as our sun will, but rather will burn themselves out in a few million years and end their lives in spectacular supernovae. The light from Stephenson 2-18 that we observe today began its journey toward Earth 19,000 years ago. It has traveled across the interstellar medium, passing through clouds of dust and gas, navigating around massive structures in the galaxy before arriving at our planet and being detected by human instruments. The same light might be seen by future generations, by observers far more sophisticated than we are, who will have measured even more accurately the properties of this remarkable star, and who will understand its significance even more deeply than we do. And in the end, when Stephenson 2-18 finally explodes, whether that occurs 10,000 years from now or 100,000 years hence, the universe will witness a moment of terrible beauty, a moment when the accumulated matter and energy of this enormous star is released in a blast of radiation and particles that will outshine galaxies. The elements synthesized in the core of Stephenson 2-18 will be scattered to the winds, enriching the interstellar medium, seeding the formation of new stars and new worlds. And the cycle will continue. Stars will be born from the remnants of Stephenson 2-18. Some of those stars will have planetary systems. And perhaps on some of those planets, life will emerge, and beings will look up at their night sky and wonder at the stars they see. This is the legacy of Stephenson 2-18, and the legacy of all the stellar giants. They are not isolated phenomena, but rather part of the great cycle of creation and destruction that gives meaning and form to the universe. To study the stars is to participate in the oldest of human endeavors. The ancients looked up at the sky and saw patterns, saw stories written in light. Modern astronomy has transformed those ancient observations into rigorous science, has revealed the profound physical principles governing stellar behavior, has shown us that the cosmos is far stranger and more wondrous than the ancients could have imagined. Stephenson 2-18 is one expression of this cosmic wonder. It is a star that deserves our contemplation, our study, and our awe. In the presence of such cosmic extremity, we are reminded of our own smallness, our own brief moment in the vast span of cosmic time. The Earth, that small blue world orbiting a yellow dwarf star, is a universe unto itself to those who inhabit it. But placed in the context of the true cosmic landscape, in which giants like Stephenson 2-18 roam the darkness between the stars, our world becomes infinitesimally small. And yet, this smallness is not something to be dispirited. Rather, it is a source of wonder, a reminder that we are part of something vastly larger than ourselves, something that we can strive to understand, something that inspires us to look upward and ask the eternal questions. What is out there? How does it all work? What does it all mean? Stephenson 2-18 has no answers to these questions. It is simply a star, burning, radiating, nearing the end of its existence. But in its very existence, in its magnitude and majesty, it points towards something beyond itself. It reminds us that we live in a universe governed by natural law, a universe that is noble, a universe that is willing to reveal its secrets to those patient and diligent enough to ask the right questions. This is the greatest gift that the study of the cosmos can offer, not just knowledge about what exists out there, but a sense of participation in something larger than ourselves, something worth dedicating our lives to understanding. There is something out there, between the stars, in the immeasurable dark that stretches beyond every horizon we have ever known. Something has been waiting, not with intention, not with awareness, but with the patient, mindless persistence of chemistry and time. It is not a nebula, not a black hole, not a pulse of radiation from some dying giant. It is a world, a planet, spherical and warm, wrapped in an atmosphere so chemically peculiar that when the first measurements reached the scientists, who had spent careers preparing to receive exactly this kind of data, the hallways of their institutions fell briefly silent, and then erupted, not in chaos, but in something rarer, in the trembling, uncertain, almost fearful recognition that they might be holding the answer to the oldest question our species has ever asked. Before we descend into the details of what was found, and how, and what it might mean, we must pause at the beginning. Not at the beginning of this particular discovery, nor even at the beginning of astronomy as a science, but at the beginning of the question itself. Because the question preceded the science by a very long time. Long before anyone knew what a star truly was, before anyone understood that those points of cold fire overhead were not ornaments hung in some divine ceiling, but were themselves suns, vast and burning, separated from us by distances that make all human geography seem laughably intimate. Long before all of that, people looked up and wondered whether the darkness between the lights was empty or inhabited, wondered whether the feeling of smallness that comes with stargazing was the whole story, or whether it was merely the prelude to something grander, a cosmos not lonely, but teeming. That wondering has a name now. We call it the search for extraterrestrial life. We have institutions devoted to it, careers built upon it, instruments constructed at extraordinary expense specifically to pursue it. And yet for most of its history, the search has returned nothing definitive. Not because we were looking in the wrong places, though sometimes we were, but because we lacked the tools. The question was always larger than the technology available to answer it. Until now. Until a golden mirror, folded like origami and sent adrift in the cold dark a million miles from Earth, opened its eyes and looked at a planet 120 light-years away, and saw something that should not be there, unless something is alive. The universe is approximately 13,800,000,000 years old. This number is not emotionally accessible to us. We can write it, we can say it, we can use it in calculations, but we cannot feel it the way we feel the passage of a single afternoon or a difficult year. And yet, this incomprehensible span of time is perhaps the most important fact about the universe from the perspective of anyone asking about life. Because time is the currency of complexity. Given enough time, hydrogen, the simplest element, the original substance from which everything else derives, can become stars, and stars can become supernovae, and supernovae can scatter carbon and oxygen and nitrogen and sulfur across the void, and from those scattered ashes new stars can form with planets circling them, and on those planets, in the right conditions, chemistry can become biology. The universe has had nearly 14 billion years to practice this transformation. In that light, in that context, the question is not whether life exists elsewhere. The question is how we could ever have imagined it does not. But science does not traffic in inevitabilities. Science demands evidence. And evidence, in the case of life beyond Earth, has been stubbornly absent, not because we believe life was absent, but because we could not reach far enough, look precisely enough, hear subtly enough to detect it. The history of the search for extraterrestrial life is, in many ways, a history of instruments catching up to ambitions. And in the third decade of the 21st century, the instrument finally caught up. It arrived, as the most transformative instruments do, in the form of a telescope. Not a telescope in the ordinary sense, not a tube you peer through on a hilltop, but a machine of extraordinary complexity and precision, a machine that took 2 decades and $10 billion to build and launch, a machine that orbits the sun 1.5 million kilometers from Earth and collects light that our eyes will never see, and turns it into data that our mathematics can read like a letter from the cosmos. The James Webb Space Telescope is named for a NASA administrator, who oversaw the Apollo program in the 1960s. It carries, in one sense, the ambitions of an era that first sent human beings beyond the atmosphere. But its scientific purpose is far more ancient. Webb was built to do many things: to study the first stars that formed after the Big Bang, to peer into star-forming nebulae where new suns ignite in clouds of gas and dust, to trace the evolution of galaxies across billions of years. But among its primary missions is one that previous generations could scarcely have imagined as feasible: to analyze the chemical composition of the atmospheres of planets orbiting other stars, and to search in those atmospheres for the signatures of life. The technique Webb uses for this is called transmission spectroscopy. When a planet passes in front of its star, when it transits, in the language of astronomy, a small fraction of the star's light passes through the planet's atmosphere rather than around it. That atmosphere acts as a filter, absorbing certain wavelengths of light with particular efficiency. Different molecules absorb different wavelengths, each leaving its own distinctive pattern in the transmitted spectrum, a chemical fingerprint, a molecular signature, as unique and readable as a barcode. By collecting enough photons during enough transits and analyzing the resulting spectrum with sufficient precision, it is possible to determine which molecules are present in an alien atmosphere, and in what proportions. Webb does this better than any instrument before it by a factor that is difficult to overstate. Its mirror, composed of 18 hexagonal segments of beryllium coated in a microscopically thin layer of gold, spans 6.5 meters in diameter. Compared to the Hubble Space Telescope, which served astronomy brilliantly for more than 30 years, Webb collects roughly 6 times more light. But the deeper advantage is in wavelength range. Hubble works primarily in visible and ultraviolet light. Webb operates in the infrared, the domain of heat, of molecular vibration, of the specific frequencies at which organic molecules absorb and emit radiation. It is in the infrared that the chemical signatures of complex molecules are written most clearly. And it is in the infrared that Webb reads the atmospheres of distant worlds. The planet it was reading, on the day this story turns upon, is designated K2-18b. The designation is unglamorous, a catalog number assigned by the Kepler Space Telescope's second extended mission when it detected the planet transiting its star in 2015. The star itself, K2-18, is a red dwarf, smaller, cooler, and older than our Sun, burning its hydrogen so parsimoniously that it will outlive our Sun by tens of billions of years. It sits in the constellation Leo, 120 light-years from Earth. That distance sounds enormous, and in human terms it is incomprehensible. But in the context of the Milky Way galaxy, which spans 100,000 light-years from edge to edge, 120 light-years is a whisper, a few steps in a vast cathedral. K2-18b is not a small world. It has approximately 8 times the mass of Earth, and roughly 2.5 times Earth's diameter. This places it in a category that astronomers call mini-Neptunes or super-Earths, a range of planetary sizes that, curiously, does not exist in our own solar system. Between Earth and Neptune, with their vast difference in size, there is nothing orbiting our Sun. But surveys of other star systems have revealed that this intermediate size range is in fact the most common type of planet in the galaxy. Our solar system, with its stark gap between the terrestrial and gas giant planets, appears to be the exception. The cosmos, it seems, favors precisely the kind of world that K2-18b represents. What makes K2-18b particularly compelling is its location. It orbits within the habitable zone of its star, the range of distances at which a planet's surface temperature, under the right atmospheric conditions, could permit liquid water. Its year is 33 Earth days. It receives somewhat less stellar energy than Earth receives from the Sun, but because red dwarf stars emit most of their radiation in wavelengths that heat planetary surfaces efficiently, the temperature at the planet's surface, or rather, at the boundary between its ocean and its atmosphere, is estimated to fall somewhere between 10 and 50 degrees Celsius. Not the scorching inferno of Venus or the freezing desolation of Mars. The temperature of habitability. The best current model for what K2-18b actually is, physically, structurally, in terms of its bulk composition, is something called a Hycean world. The name is a portmanteau, hydrogen in ocean. A Hycean world, as theorized by researchers including Mika Madhusudhan at the University of Cambridge's Institute of Astronomy, is a planet whose interior is dominated by a deep global ocean of liquid water, covered by a hydrogen-rich atmosphere. Not a thin atmosphere like Earth's, but a thick, reducing atmosphere in which hydrogen is the dominant gas, with methane and carbon dioxide mixed in. Above the ocean, which may extend hundreds of kilometers in depth, this atmosphere presses down at pressures that, near the ocean surface, may resemble those in Earth's upper ocean layers. The temperatures are moderate. The water is liquid. And the chemistry, if Hycean world theory is correct, could support life, specifically, the kind of anaerobic microbial life that dominated Earth for the first 2 billion years of biological history, before oxygen became a significant component of our atmosphere. This is the world that James Webb was studying when it found something unexpected. During multiple transits of K2-18b across the face of its star, Webb's near-infrared spectrograph collected the transmission spectrum of the planet's atmosphere with extraordinary precision. The spectrograph recorded the brightness of starlight at thousands of different wavelengths simultaneously, tracking how the spectrum changed as the planet moved across the stellar disk. The resulting data required months of careful analysis, removing instrumental signatures, accounting for the star's own spectral variability, building atmospheric models, and comparing them against the observations, searching for the combination of molecules that best explained what was seen. What they found included carbon dioxide. They found methane. They found water vapor. These detections were themselves scientifically significant, a confirmation that K2-18b has a rich, complex atmosphere quite unlike anything in our solar system. But then the analysis revealed something else, something that caused scientists at Cambridge and at collaborating institutions to pause and look again, and then look again once more. Something that sent a tremor through the field that is still being felt. They found, at a statistical confidence of greater than 3 sigma, corresponding to a probability of 99.7%, the spectral signature of dimethyl sulfide. Dimethyl sulfide. 2 carbon atoms, 6 hydrogen atoms, 1 sulfur atom, bonded into a structure with the chemical formula CH3SH3. On Earth, this molecule is produced almost exclusively by living organisms. It is the chemical that gives the ocean its distinctive smell, that salt-edged, mineral, alive scent that reaches you on a coastal breeze. It is produced by marine phytoplankton, microscopic photosynthetic organisms, as a metabolic byproduct when they break down a compound called dimethylsulfonylpropionate. It is produced by marine bacteria that process the remains of dying algae. It enters the atmosphere in vast quantities, where it plays a role in cloud formation and climate regulation. Every molecule of dimethyl sulfide in Earth's atmosphere was made inside a living cell. No known geological process produces dimethyl sulfide in detectable quantities. No known abiotic photochemical reaction generates it efficiently under conditions thought to exist on Hycean worlds. No volcanic emission contains it. No comet could deliver it in sufficient quantities to maintain an atmospheric abundance detectable by a telescope at interstellar distances. On Earth, dimethyl sulfide is as close as chemistry comes to a signature of life, not a signature of complex or intelligent life, not a signature of civilization, but a signature of biology, of metabolism, of organisms transforming matter and releasing chemical traces of their existence into the air. And Webb found its signature on K2-18b. The significance of this finding demands that we slow down and resist the natural human impulse toward easy conclusions. 99.7% is a very high probability. In statistics, it corresponds to what physicists call 3 sigma, a level at which the probability of the result being a chance fluctuation in the data, rather than a real signal, is approximately 3 in 1,000. In many scientific fields, 3 sigma is the threshold at which a result is taken seriously enough to publish, to build upon, to investigate further. It is the level at which a casino begins to suspect the dice are loaded. It is the level at which a pharmaceutical trial begins to suggest that a drug is genuinely working. It is not, in the language of particle physics, where 5 sigma is required before an announcement of discovery, an absolute certainty. But it is a very long way from coincidence. The researchers, led by Professor Nikumadhu-Sudhan, were careful in their language. They are scientists, trained by years of professional culture to resist premature certainty, to hedge, to qualify, to acknowledge alternative explanations. Their published paper, which appeared in the Astrophysical Journal Letters following peer review, describes the detection of a spectral feature consistent with the presence of dimethyl sulfide, acknowledges the statistical confidence of that detection, explores possible non-biological explanations, and concludes that the biological interpretation is the most parsimonious. The simplest explanation consisted with all available evidence. The language is measured. The emotion in the room when those numbers first appeared was not. Because this is what 99.7% means in the context of the search for extraterrestrial life. It means, for the first time in the entire history of science, that a specific chemical compound, one produced on Earth exclusively by living organisms, has been tentatively detected in the atmosphere of another world, at a statistical confidence level that places the result squarely within the territory of publishable, peer-reviewed, scientifically defensible findings. This is not a blip in the data. This is not wishful thinking. This is the cosmos whispering something through the light, and for the first time in all of human history, we have an instrument sensitive enough to hear it. Let us now look more closely at what kind of life could be producing this signal, if indeed something is alive on K2-18b. The molecule dimethyl sulfide is not an indicator of intelligent life. It is not a radio signal, not an artifact, not a sign that someone out there has built something. It is a metabolic signature, the chemical exhaust of biology at its most fundamental level. On Earth, the organisms that produce it in the largest quantities are single-celled. Marine phytoplankton are eukaryotic cells. They have a nucleus, a cell membrane, organelles, but they are not, by any stretch, complex. They have no nervous system, no experience, no awareness. They are extraordinarily efficient metabolic machines, globally important, climatologically influential, ecologically indispensable, but they are not thinking. If organisms on K2-18b are producing dimethyl sulfide, then, by analogy, they would be somewhere in the range of microbial to single-cell complexity. Not whales, not trees, not minds, but life, the fundamental, tenacious, chemically inventive process by which matter organizes itself into structures that metabolize, replicate, and evolve. The distinction matters enormously, because it tells us what kind of discovery this may be. It is not the discovery of intelligence. It is not the discovery of civilization. It is, if confirmed, the discovery that the chemistry of life, that elegant, improbable, astonishing transformation of simple molecules into self-replicating metabolic systems, is not unique to Earth, that it has happened somewhere else, that the universe is, in a meaningful and measurable sense, biologically inhabited, and that, even in the absence of any mind to reflect upon it, would be one of the most profound discoveries in the history of our species. To understand why, consider what it would mean for the statistics of life in the universe. The Milky Way galaxy contains somewhere between 200 and 400 billion stars. The vast majority of these stars, particularly the red dwarfs, which are by far the most common stellar type, are now known to host planets. Statistical analysis of Kepler mission data suggests that on average, every star in the galaxy has at least one planet. If we accept the lower bound of 200 billion stars, and apply the estimate that something like 1 in 5 rocky or ocean-world planets and habitable zones could support life, we arrive at numbers of potential inhabited worlds that are staggering in their implications. And those are just the planets we can see. Beyond our galaxy, across the observable universe, there are more than 2 trillion galaxies, each containing billions of stars. If life exists independently on even 2 planets in the same galaxy, if K2-18b's biosphere is genuinely independent of Earth's, then the probability that life is cosmically common becomes, in statistical terms, overwhelming. This is the intellectual earthquake that a confirmed detection of life on K2-18b would trigger. Not just the specific finding about that specific planet, but the seismic implication for our understanding of what kind of universe we live in. We would learn, definitively, that the emergence of life from chemistry is not a miracle, not a once-in-the-history-of-the-cosmos fluke, but a process that chemistry performs wherever it finds the right conditions. Water, carbon, energy, time, and given enough of all 4, life follows. Not always. Not immediately. But with a regularity that the universe, in its 14-billion-year history, has had ample time to demonstrate. The history of astronomy is, in one reading, a history of scale, of the progressive expansion of the known cosmos, and with it, the progressive diminishment of human centrality. The ancient model placed Earth at the center of a finite, geocentric universe, with the stars as lights fixed to a rotating sphere. Copernicus displaced Earth from the center, and showed it to be one of several planets orbiting the Sun. Galileo confirmed this with observations. Newton showed that the same laws of gravity that govern falling apples also govern planetary orbits, that the cosmos is not a realm of divine exception, but a vast, law-abiding mechanism. Herschel began to map the stars of the Milky Way, and showed them to be a disc-shaped community of suns. Hubble showed that the Milky Way is one of billions of galaxies, each containing billions of stars, that our island of stars is just that, an island in an ocean of islands that stretches in all directions without apparent end. Each of these expansions was accompanied by disorientation, by resistance, by the need to revise fundamental assumptions about our place and significance. And each time, the new picture turned out to be not less wonderful than the old, but more, not less full of meaning, but differently full of meaning. A universe in which we are not at the geometric center is, it turns out, just as capable of being the stage for human experience, human love, human discovery. The loss of centrality was never a loss of significance. It was a gain of perspective. What the detection of life on K2-18b, if confirmed, would represent is the next expansion in this sequence. Not a spatial expansion this time, but a biological one. The discovery that life is not centralized in one world, just as the cosmos is not centered on one planet, or one star, or one galaxy. The discovery that biology, like gravity and electromagnetism and thermodynamics, is a feature of the universe, not an accident that happened once on a small rocky world near an average star, but a consequence of chemistry operating under the laws of physics in conditions that the universe provides in abundance. This is not a diminishment of Earth. It is an enlargement of life. The discovery that life exists elsewhere does not make Earth less precious any more than the discovery of other galaxies made the Milky Way less beautiful. If anything, it reveals what the emergence of life means more clearly, not a cosmic miracle reserved for one special place, but a cosmic tendency expressing itself wherever it can. Let us dwell for a moment on the planet itself, on what K2-18b might look like to a hypothetical observer in orbit above it, because that exercise and imagination, constrained by what science has told us, is illuminating. There would be no shoreline, no continental shelf, no mountain range breaking the surface. If K2-18b is the Hycean world that models suggest it may be, then its surface, the boundary between solid and liquid, between rock and water, lies beneath hundreds of kilometers of ocean, under pressures that dwarf anything experienced in Earth's deepest trenches. What floats above that oceanic abyss would be a global sea, perhaps turbulent, perhaps calm in its upper layers depending on the dynamics of the atmosphere pressing down upon it, lit by the deep red light of the star K2-18, which would appear in the sky larger than our sun, but far less bright, casting its ruddy illumination across water that has never known a coastline. The atmosphere above that ocean would be thick, not the delicate shell of gas that wraps Earth, easily lost to space over geological time and constantly replenished by biological activity, but a substantial hydrogen-dominated envelope mixed with methane, carbon dioxide, and, according to Webb's most recent measurements, trace quantities of dimethyl sulfide. The clouds in that atmosphere would be different from Earth's, composed perhaps of hydrocarbon aerosols, perhaps of water droplets formed at different temperatures and pressures than their terrestrial counterparts. The light reaching the ocean surface would be filtered through this complex atmospheric chemistry, shifted in color toward the infrared, dimmer than what we experience on a clear day, but perhaps sufficient for photosynthesis, or for whatever biochemical process serves the equivalent function in K2-18b's biosphere, if it has one. Below the surface of that global ocean, in the darkness lit only by whatever bioluminescence might exist, the conditions for microbial life, if current models are correct, would be favorable by any terrestrial standard. The temperature would be moderate. Water would be liquid. Simple organic compounds would be dissolved in the ocean, cycling through chemical reactions driven by the energy of the star above and perhaps by geothermal heat from below. And if the analogy with Earth holds, if the fundamental chemistry of life is as universal as its basic ingredients suggest, then in that warm, dark, chemically complex ocean, something might be using that chemistry, metabolizing, reproducing, evolving, exhaling, in the chemical sense, dimethyl sulfide into the waters above, where it rises through the ocean column and diffuses into the atmosphere, where it floats in concentrations of parts per billion, where it absorbs a particular wavelength of infrared light passing through during a transit, and where, 120 years later, that pattern of absorption arrives at the gold mirror of an instrument built by the descendants of the first living things that ever developed curiosity about the sky. The timeline of this photon journey is one of the details of this story that most rewards slow contemplation. The light that Webb collected to identify the signature of dimethyl sulfide on K2-18 be left that planet's atmosphere approximately 120 years ago. It departed during the last years of the 19th century, during the age of Edison and Pasteur and the early Curie, during a time when the Wright brothers had not yet flown, when Einstein was a 20-year-old student, when the idea that stars were other suns with their own planetary systems was still debated rather than established. Those photons traveled through the void at the only speed nature allows for light, indifferent to centuries and civilizations, arriving at the position of our solar system just as humanity had built something capable of receiving them with sufficient precision to read their message. There is a kind of cosmic patience in this, a message dispatched before the receiver existed, arriving precisely when the receiver was finally ready. If there is life on K2-18b, it knew nothing of what it was doing. It was simply metabolizing, simply releasing a chemical byproduct into the atmosphere as billions of Earth organisms do every day without the slightest awareness of the consequences. But those consequences traveled 120 light years and arrived in a scientific instrument that told us something we have wanted to know for longer than science itself has existed. The science of how we know what Webb found requires a moment of explanation, because the beauty of the method is inseparable from the beauty of the discovery. Transmission spectroscopy works because molecules interact with light in specific ways. Each molecule, depending on its structure, the arrangement and masses of its atoms, the nature of its chemical bonds, absorbs photons at specific energies, which correspond to specific wavelengths of light. For dimethyl sulfide, the relevant absorption features lie in the near-infrared, associated with the stretching and bending vibrations of the molecules carbon-hydrogen and carbon-sulfur bonds. When a beam of starlight passes through an atmosphere containing dimethyl sulfide, those specific wavelengths are absorbed more strongly than others. The molecule reaches up, in a sense, and plucks those particular photons from the stream. Webb's near-infrared spectrograph, NIR-SPEC, records the brightness of starlight across thousands of wavelength channels simultaneously, with a precision that previous instruments could not approach. By comparing the spectrum observed during a transit, when light is passing through the planet's atmosphere, with the spectrum observed outside a transit, when no atmospheric filtering is occurring, astronomers can isolate the atmospheric contribution, the chemical fingerprint left by the molecules in the air. What they found when they applied this method to K2-18b and searched the resulting spectrum for the signatures of known molecules was a pattern that included features consistent with dimethyl sulfide at wavelengths predicted by laboratory measurements of that molecule's spectral properties. The analysis required extensive modeling. The team had to construct atmospheric models, computational simulations of the planet's atmosphere with various assumed compositions, and compare those models against the observed data, using statistical methods to determine which compositions best explained what was seen. They tested models with dimethyl sulfide and models without it. They tested models with alternative molecules that might produce similar spectral features. They propagated their uncertainties carefully, accounting for the limited precision of the wavelength calibration, for possible stellar contamination of the spectrum, for the finite number of photons collected across the observed transits. And when all of that was done, the result remained: the presence of dimethyl sulfide in K2-18b's atmosphere was the most probable explanation for the observed spectral features, at a confidence level of greater than 3 sigma. That confidence level, and what it does and does not mean, deserves emphasis. In particle physics, the standard for claiming a discovery is 5 sigma, which corresponds to a probability of roughly 1 in 3.5 million that the result is a statistical fluctuation. This higher bar exists because particle physics experiments generate vast quantities of data and test enormous numbers of hypotheses, creating many opportunities for false positives to arise by chance. Atmospheric spectroscopy of exoplanets operates in a different statistical regime. Fewer observations, cleaner hypotheses, more direct comparison of model and measurement. In this context, 3 sigma is a genuinely strong result. It is not proof. It is not certainty. It is a compelling, data-grounded, peer-reviewed reason to take the hypothesis seriously and pursue the next test. The next test is already underway. Webb continues to observe K2-18b. Each additional transit adds more photons to the dataset, reduces uncertainties, strengthens or weakens the signal. Independent research groups around the world are analyzing the same data with their own methods, their own models, their own assumptions, checking whether Madhusudan's team's findings survive scrutiny from different analytical perspectives. Theorists are working to determine whether any abiotic mechanism, any non-biological chemical reaction, could produce dimethyl sulfide at the detected abundance under Hisian world conditions. Experimentalists are measuring the spectral properties of dimethyl sulfide under pressures and temperatures relevant to K2-18b's atmosphere, checking whether the theoretical absorption features match the observed ones with the precision the detection requires. This is how science works. Not through the pronouncements of authorities, but through the convergence of independent lines of evidence, through the slow, sometimes tedious, always essential process of checking and rechecking and checking again, of asking whether the result holds when someone else looks at it from a different angle. The finding about K2-18b has not yet completed this process. It may yet be overturned. The history of science contains examples of 3 sigma results that vanished when more data arrived, and they serve as important reminders of the need for continued rigor. But it also contains examples of 3 sigma results that strengthened with time, that survived every attempted refutation, that eventually entered the canon of established science. Only continued observation will tell us which category K2-18b's dimethyl sulfide belongs to. What we can say now, in this moment before that verdict is delivered, is that we live in a time unlike any that has preceded it in the history of the search for extraterrestrial life. Previous generations of searchers could look at distant stars and imagine that planets orbited them, but had no way to confirm it. The generation after them confirmed the planets, but could not examine their atmospheres. The generation after them began the first tentative atmospheric analyses, detecting water vapor and simple molecules in the envelopes of hot giant planets, worlds utterly unlike anything capable of supporting biology. And now we have Webb, an instrument so sensitive that it can detect the trace chemicals in the atmosphere of a world the size of a mini-Neptune, 120 light-years away, with enough precision to distinguish between dozens of candidate molecules and identify the one most consistent with the data. We have crossed a threshold. Whatever the final verdict on K2-18b proves to be, the threshold has been crossed. The question of whether life exists beyond Earth is no longer purely philosophical, purely speculative, purely the domain of imagination. It is now an empirical question, a question that can be asked and, in principle, answered through observation. The instruments now exist. The methods now exist. The understanding of what to look for now exists. All that remains is more data, more patience, more careful analysis, and time. Carl Sagan spent much of his life arguing for this moment. Not necessarily for this specific planet or this specific molecule, but for the moment when the search for extraterrestrial life would become a mature, rigorous, data-driven science rather than the fringe enthusiasm that institutional astronomy sometimes treated it as. He argued, eloquently and persistently, and with that particular gift he had for making the cosmic field personal, that the question of whether we are alone is one of the most important questions a conscious species can ask, not merely for what the answer might tell us about the universe, but for what the act of asking it tells us about ourselves. That we look up, that we wonder, that we build instruments to test our wondering against reality, that we are, in whatever sense matters most, a species that refuses to accept the limits of its own immediate experience. Sagan died in 1996, the year before the first confirmed detection of water vapor in an exoplanet's atmosphere. He never lived to see the Kepler mission catalog thousands of worlds. He never saw Webb launch. But the intellectual tradition he represented, the insistence that the cosmos is worth studying with rigor and with wonder simultaneously, that science and poetry are not enemies, but companions in the project of understanding, that tradition lives in every researcher who sat with Madhusudhan's data and felt, beneath the professional caution, something that had no technical name. David Attenborough has spent decades witnessing and documenting the inventiveness of life on Earth, the astonishing diversity of forms that natural selection has produced from the same basic chemistry, given different environments and different spans of time. He has described the courtship of birds of paradise, the collective intelligence of ant colonies, the navigation of migratory butterflies, the chemical communication of orchids and their pollinators. In all of that witnessing, a consistent theme emerges, that life fills every available space, exploits every available energy source, evolves every possible strategy for survival and reproduction. That given appropriate conditions, life does not merely persist, it proliferates, diversifies, elaborates itself into forms of staggering variety and sophistication. If that pattern holds beyond Earth, if life's tendency to fill available niches is not a local peculiarity of our biosphere, but a universal property of chemistry under favorable conditions, then an ocean world like K2-18b, with its global ocean and its moderate temperatures and its billions of years of chemical complexity, is precisely the kind of environment we should expect to be inhabited, not by whales or forests or any of the complex multicellular structures that life on Earth eventually produced, but by the microbial ancestors of complexity, by organisms that do what the first life on Earth did for the first 2 billion years, metabolize, divide, evolve, and in doing so, leave their chemical traces in the atmosphere above them. Dimethyl sulfide is such a trace. It is the smell of living oceans. And Webb may have smelled it on another world. The concept of the Hycean world, the theoretical framework within which K2-18b is best understood, was developed in large part by Madhusudhan's own research group at Cambridge, published in a landmark 2021 paper that proposed this class of planets as potentially habitable environments that had been underappreciated in the search for life. The argument was straightforward but important. Existing habitability criteria focused almost exclusively on rocky planets in the terrestrial size range. But if life can begin and sustain itself in a global ocean covered by a hydrogen-rich atmosphere, as Hycean world models suggest is chemically and thermodynamically plausible, then the number of potentially inhabited worlds in the galaxy expands dramatically. Hycean worlds may be far more common than Earth-like rocky planets in the classical habitable zone. If they can host life, then habitable real estate in the universe is far more abundant than we had imagined. This is the intellectual context in which the K2-18b detection lands. Not just as an isolated finding about one planet, but as the first potential empirical confirmation of a theoretical framework that, if correct, would redraw our map of where to look for life and what to look for when we look. If dimethyl sulfide on K2-18b is biological, then Hycean worlds are genuine life-hosting environments. And if Hycean worlds are genuine life-hosting environments, then the habitable zone of the galaxy is far larger than the narrow ring of rocky planets that most habitability models have historically emphasized. What are the alternative explanations? The non-biological scenarios that scientists must rigorously consider before accepting the biological interpretation. The principle is simply this: in science, extraordinary claims require extraordinary evidence, and the claim that an atmospheric chemical is produced by living organisms on another planet is about as extraordinary as claims get. Every abiotic pathway to dimethyl sulfide must be examined and, if possible, ruled out. Photochemical production. Could ultraviolet radiation from the star K2-18 catalyze the synthesis of dimethyl sulfide from simpler sulfur-containing molecules in the hydrogen-rich atmosphere? Theorists have modeled this carefully. The answer appears to be that photochemical production is possible in principle, but grossly inefficient under the conditions modeled for K2-18b. Several orders of magnitude less efficient than would be required to maintain the atmospheric abundance inferred from Webb's data. Not ruled out with certainty, but not a satisfying explanation. Hydrothermal production. Could geologically heated vents on the ocean floor produce dimethyl sulfide? The problem here is thermochemistry. Dimethyl sulfide is thermally unstable at the temperatures associated with hydrothermal activity. It decomposes faster than it forms under those conditions. It would not survive long enough to reach the atmosphere in significant quantities. Not a compelling explanation. Cometary delivery. Could a sustained bombardment of comets carrying organic compounds, including dimethyl sulfide or its precursors, maintain atmospheric levels detectable by Webb? The math does not support it. The flux of cometary material required to explain the inferred abundance would be many orders of magnitude greater than anything astronomically plausible for a mature planetary system. Instrumental artifact. Could the spectral feature attributed to dimethyl sulfide be an artifact of the telescope's calibration, or a misidentification of some other molecule? The team checked this extensively. The feature appears at the expected wavelengths, with the expected width and shape. It is reproduced across multiple independent transits. Alternative molecules that could produce similar features were tested and found to fit the data less well. The community of atmospheric spectroscopists who reviewed the paper before publication is not easily fooled by calibration artifacts, and none identified a compelling instrumental explanation. What remains, after each of these alternatives is examined and found wanting, is the biological explanation that something in K2-18b's ocean is metabolizing sulfur-containing compounds and releasing dimethyl sulfide as a byproduct, just as marine phytoplankton does in Earth's oceans every day. Not proven. But the most parsimonious explanation for the data that exists. The philosopher of science Karl Popper argued that scientific theories advance not by proof, but by falsification, by the failure of all attempts to disprove them. The hypothesis that dimethyl sulfide on K2-18b is biological has so far survived the attempts to disprove it through abiotic alternatives. That is not the same as saying it is confirmed. But it is the right kind of scientific situation, a hypothesis that makes testable predictions, that has survived initial testing, and that calls for further tests. More observations. More modeling. More independent analysis. Science doing what it does. We should also think carefully about what the detection of microbial life on K2-18b would mean for the search more broadly. The most philosophically significant implication is a statistical one. If life arose independently on two planets in the same galaxy, even microbial life, even single-celled life far simpler than anything with a nervous system, then the probability that life is a common feature of the cosmos becomes, in statistical terms, essentially a certainty, because two data points, even if imprecise, allow the construction of a probability distribution. Two origins of life in one galaxy implies that life is not astronomically rare, that the conditions required for it are not exquisitely narrow, that wherever suitable chemistry and energy and time converge, life tends to follow. The Fermi paradox, the question, attributed to physicist Enrico Fermi, of why we have not detected signs of extraterrestrial civilization given the apparent probability of its existence, takes on a different character in this light. If life is common but intelligent, technological, communicating civilization is rare, if microbial life is the universe's typical biological output, with complex, brain-having, civilization, there is a moment in the life of every civilization that has ever dared to look upward, when the sky ceases to be a ceiling and becomes a door. That moment arrived for our species not with a bang but with a whisper, a quiet mechanical unfolding in the cold silence beyond the atmosphere, a gold-plated mirror slowly spreading its 18 hexagonal petals, like some impossible flower blooming in the dark. The James Webb Space Telescope, humankind's most ambitious act of curiosity, had awakened. And what it would see, in the months and years that followed, would shake the very foundations of what we thought we knew about the universe, not because the universe was behaving strangely, but because it was behaving in ways that suggested we had been wrong, profoundly and perhaps systematically wrong, about almost everything. To understand why what Webb found disturbed the scientific community so deeply, you must first understand what scientists expected to find. Not as a dry inventory of predictions, but as something more intimate, as a statement of faith. Because that is what a cosmological model truly is. It is an act of faith, disciplined and mathematical, yes, constrained by observation and logic, and the hard-won lessons of centuries of inquiry, but faith nonetheless. Faith that the universe is knowable. Faith that the patterns we have detected close to home extend outward, faithfully, to the farthest shores of space and time. Faith that the story we have pieced together from starlight and radio waves and gravitational whispers is the true story, or close enough to true that the difference barely matters. Webb did not merely outdate that story. It threatened to rewrite it from the opening line. The model we had constructed was called the lambda-CDM model, cold dark matter, seasoned with the cosmological constant, a mathematical term Einstein had once inserted into his equations and then famously regretted, a kind of fudge factor that turned out not to be a fudge at all, but a description of something real and deeply strange, a repulsive energy woven into the fabric of space itself, pushing everything apart, accelerating the expansion of the universe at a rate that defies intuitive comprehension. This model, this lambda-CDM, had been one of the great triumphs of late 20th and early 21st century physics. It described the large-scale structure of the cosmos with extraordinary precision. It predicted the patterns in the cosmic microwave background radiation, the faint afterglow of the Big Bang, still detectable today as a kind of thermal hum pervading all of space, with a fidelity that was almost uncanny. It told us when the first stars should have formed, how they should have clustered into galaxies, how those galaxies should have grown and merged and evolved over the 13.8 billion years since the universe began its great expansion. It was beautiful. It was elegant. And if Webb's early findings are to be believed, it may be incomplete in ways that will take decades to fully understand. What Webb found, staring into the ancient light of the universe's first billion years, were galaxies. That sounds unremarkable until you understand what kind of galaxies they were. They were large. They were massive. They were structured and mature and luminous in ways that the standard model said they simply should not yet be. Galaxies of that size, with that many stars, arranged with that degree of order, they require time to build. They require the slow gravitational accumulation of matter, the collapse of clouds of hydrogen and helium into the first stellar nurseries, the birth and death of generations of stars, the progressive enrichment of the interstellar medium with heavier elements forged in stellar cores and scattered by supernovae, the mergers of smaller galaxies into larger ones, the patient, unhurried process of cosmic construction that unfolds over hundreds of millions and then billions of years. Or so we thought. Webb looked back to within the first few 100 million years after the Big Bang and found galaxies that looked like they had already been through all of that. Galaxies that looked old when the universe was still an infant. And that contradiction, that impossible, haunting contradiction, is what scientists had feared they might find but hoped they wouldn't. In the first year of Webb's scientific operations, a series of papers appeared in the astronomical literature that caused something close to a collective intake of breath among cosmologists. Researchers analyzing Webb's deep field images that captured thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length, found objects at redshifts of 8, 10, 12, 14, and beyond. A redshift is a measure of how much the universe has stretched the light from a distant object during the billions of years that light has spent traveling toward us. A redshift of 8 corresponds to a time when the universe was only about 650 million years old. A redshift of 14 corresponds to a time when the universe was barely 230 million years old, a sliver of cosmic time, a geological moment compared to the full sweep of cosmic history. And at these redshifts, Webb found galaxies, bright, massive, seemingly well-formed galaxies, that the standard model had not predicted. The discrepancy was not small. Some of the objects Webb detected appeared to be 10 to 100 times more massive than models allowed for that epoch. The question then immediately arose, the question that made careful scientists pause and less careful ones reach immediately for revolutionary proclamations, was not whether these objects were real. They were real. Webb's instruments are not in the business of manufacturing phantoms. The question was what their existence meant. It is worth pausing here to consider the nature of scientific fear. When a scientist says they feared a result, they do not mean it in the ordinary emotional sense, the quickening of the pulse, the cold sweat, the impulse to look away. Scientific fear is more nuanced than that. It is the anxiety that comes from having built something beautiful and then discovering evidence that it might need to be torn apart. It is the recognition that a beloved model, tested and refined over decades, might be insufficient. But it is also, if you listen carefully, tinged with something else, with excitement, because a result that breaks a model is not a defeat. It is an invitation. It is the universe whispering, patiently and without judgment, that there is more to understand. The scientists who built the standard cosmological model did not build it in the hope that it would be the last word. They built it in the hope that it would be a good enough word to get them to the next question. And Webb, it seems, has delivered the next question with extraordinary clarity. The machinery of Webb's vision is worth understanding, because it is extraordinary in itself, a feat of engineering so ambitious, so technically demanding that its successful deployment was, to those who had spent their careers waiting for it, something close to a miracle. The telescope had been in development for over 20 years, the subject of budget overruns and schedule delays and political battles that threatened more than once to kill it entirely. It had been launched on Christmas morning of 2021, carried into space by an Ariane 5 rocket from the Guiana Space Center on the northeastern coast of South America, and then had spent nearly 6 months unfolding itself, cooling itself, aligning itself, calibrating its instruments in the cold dark of the second Lagrange point, a gravitational equilibrium located 1.5 million kilometers from Earth on the side opposite the Sun. And then, in July of 2022, it began to see. What Webb can see that Hubble could not is, in the most literal sense, time itself. Because Webb observes primarily in the infrared, in wavelengths of light longer than what the human eye can detect, longer than the red end of the visible spectrum, it can see through the dust that obscures so many of the universe's most interesting regions. Stellar nurseries hidden behind vast clouds of interstellar gas and dust reveal themselves to Webb's instruments in stunning detail. But more than that, Webb can detect the infrared light that carries the signature of the universe's most ancient objects. When light travels through an expanding universe, it stretches. The expansion of space itself tugs at the wavelengths of light, pulling them apart, shifting them toward longer and longer wavelengths. By the time light from a galaxy at redshift 14 reaches us, it has been shifted so far toward the infrared that Hubble, a primarily optical telescope, could barely detect it. For Webb, it is, if not exactly visible, then at least accessible. And in that accessibility lies the ability to see things that have never before been seen by human eyes or human instruments. The mirror at Webb's heart is a marvel. 18 hexagonal segments of beryllium coated with a thin layer of gold. Gold, because gold is an extraordinary reflector of infrared light, each one adjustable to nanometer precision by tiny actuators that bend the mirror surface to the exact curvature needed to bring distant starlight to a perfect focus. The total mirror area is 6.5 square meters, more than 6 times the light-collecting area of Hubble. Behind the mirror sits the sun shield, a 5-layered structure the size of a tennis court, each layer coated with a reflective material that bounces sunlight away from the telescope. The sun shield reduces the temperature on the sun-facing side from roughly 85 degrees Celsius to minus 233 degrees Celsius on the telescope side, cold enough that the instruments can detect the faint infrared glow of objects billions of light years away without being blinded by the warmth of their own surroundings. Every aspect of Webb's design is a response to the extraordinary difficulty of seeing ancient, cold, redshifted light across unimaginable distances. And when you understand how hard it was to build, you begin to understand why what it found was so unexpected and so confronting. Let us speak of what the universe was expected to look like in those first few 100 million years. In the beginning, and that phrase carries a weight that no amount of scientific familiarity can entirely strip from it, the universe was an almost featureless sea of matter and energy, hot and dense and nearly uniform. Nearly, but not quite. There were tiny fluctuations in density, regions where the matter was infinitesimally more concentrated than elsewhere, seeds of future structure planted by the quantum fluctuations of the inflationary epoch that preceded the conventional Big Bang, stretched to cosmological scales by the explosive expansion of spacetime. Over the first few 100 million years, gravity amplified these fluctuations. Matter fell into the denser regions. The denser regions grew denser still. Eventually, in pockets of accumulating hydrogen and helium, the first stars were born, massive, violet, short-lived objects very different from our own sun, burning hot and bright and dying young, seeding the universe with the first heavy elements and the first photons energetic enough to ionize the surrounding intergalactic medium in a process called reionization, which gradually transformed the early universe from a fog of neutral hydrogen into the transparent, structured cosmos we inhabit today. In this picture, the first galaxies were expected to be small. They were expected to be irregular, lumpy, chaotic, the raw material of structure rather than structure itself. They were expected to be deficient in heavy elements, because heavy elements require generations of stellar evolution to produce, and the first generation of stars had barely begun its work. They were not expected to be the kinds of massive, luminous, chemically enriched objects that Webb was finding. They were not expected to look, in some cases, almost like the galaxies we see in the local universe today, the grand spirals and ellipticals that took billions of years to assemble. And yet there they were, bright and massive and seemingly composed, hanging in the oldest light Webb could reach, like a quiet challenge to everything the models had predicted. The reaction of the scientific community to Webb's early galaxy findings was fascinating to observe, because it illustrates something important about how science actually works, not the sanitized, linear narrative of textbooks, but the messy, contentious, exhilarating process of real inquiry. There were those who immediately reached for the most dramatic interpretation. The Standard Model is broken. Lambda CDM is wrong. The Big Bang is in question. This interpretation made excellent headlines, but was immediately disputed by the majority of working cosmologists, who pointed out, quite correctly, that extraordinary claims require extraordinary evidence, and that there were several possible explanations for Webb's findings that did not require abandoning the entire edifice of modern cosmology. One possibility was that the galaxies Webb was seeing were intrinsically brighter than average, not necessarily more massive than models predicted, by containing more luminous objects per unit of mass, perhaps because star formation in the early universe was more efficient than assumed, concentrated into brief intense bursts that produced enormous amounts of light in short periods. Star formation efficiency, the fraction of a gas cloud's mass that actually ends up in stars before stellar feedback disperses the remaining gas, is one of the parameters in galaxy formation models that is most uncertain, because it depends on complex, small-scale physics that is difficult to simulate accurately. If early galaxies formed stars more efficiently than assumed, they would be brighter than models predicted without necessarily being more massive. This explanation is plausible. It is also, crucially, testable. Another possibility was that the mass estimates themselves were uncertain. Estimating the stellar mass of a distant galaxy from its observed light is not a simple calculation. It requires assumptions about the age distribution of the stars in the galaxy, the initial mass function, the statistical distribution of star masses, and the history of star formation, all of which affect how much light a given mass of stars produces. These assumptions introduce uncertainties that could, in principle, lead to overestimates of mass. Some researchers argued that the most extreme of Webb's early candidates, the objects that seemed most flagrantly at odds with the Standard Model, might upon closer inspection prove to be less anomalous than they first appeared. And in some cases, they were right. Follow-up spectroscopic observations, which measure the actual redshift of a galaxy by analyzing the precise wavelengths of its emission and absorption lines, rather than inferring it from the shape of its light curve, confirmed that some of the most dramatic candidates were indeed at the distances suggested by photometric estimates. Others were at lower redshifts than initially thought, which made them more consistent with standard predictions, but also less dramatic, and therefore less likely to appear in popular accounts of Webb's discoveries. But not all of Webb's early findings could be explained away. There remained a core of observations, a population of massive, luminous galaxies at high redshift, that even the most conservative analysis found difficult to fully accommodate within the standard picture. Not impossible, not definitively model-breaking, but difficult. Uncomfortable in the way that only genuinely anomalous data can be. And it was this discomfort, not the headlines about the Big Bang being wrong, which were always overblown, but the quieter, more persistent discomfort of working scientists confronting data that didn't quite fit, that represented the true significance of what Webb had found. There is something deeply human about the discomfort of a challenged model. We build our understanding of the world by constructing frameworks, mental architectures that organize our observations, connect our facts, give shape to our knowledge. And when new observations arrive that do not fit cleanly into those frameworks, we face a choice. We can modify the framework, add epicycles, adjust parameters, extend the model in ways that accommodate the new data while preserving the core structure. Or, if the modifications become sufficiently numerous and sufficiently awkward, we can abandon the framework entirely and begin the difficult, exhilarating work of constructing a new one. The history of science is full of both kinds of responses, and it is not always obvious in real time which kind of response is appropriate. Sometimes the anomaly is a signal that something deep is wrong. Sometimes it is a reminder that our models are always simplifications of a richer reality. The art of science is in learning to tell the difference, and in having the honesty to admit when you cannot. The Hubble tension is one of the places where the discomfort of challenged models had already been accumulating long before Webb arrived. The tension refers to a discrepancy between two independent measurements of the Hubble constant, the parameter that describes the current rate of expansion of the universe. Measured from the cosmic microwave background using the Planck satellite, the Hubble constant comes out to roughly 67 kilometers per second per megaparsec. Measured from the local universe using Cepheid variable stars and type Ia supernovae as distance indicators, the so-called cosmic distance ladder, it comes out to around 73 kilometers per second per megaparsec. These two numbers are not merely different. They are different in a way that cannot be accounted for by the known uncertainties in either measurement. The discrepancy is statistically significant at the level of phi sigma, meaning there is roughly 1 chance in 3.5 million that it could be explained by random measurement error. Either one of the measurements is systematically wrong in a way that has not yet been identified, or the standard model is missing something. And one of the things Webb was expected to do was help resolve this tension by providing an independent check on the cosmic distance ladder using its superior ability to detect and characterize Cepheid variables in distant galaxies. What Webb found, when it turned its gaze to the distance ladder, was both reassuring and troubling. It confirmed that the local measurements were not suffering from the specific systematic errors that some had hoped would explain the tension. The Cepheid distances Webb measured were consistent with those measured by Hubble, which meant the local value of the Hubble constant was robust, and therefore that the tension with the Planck value was real and not going away. The universe, it seemed, was expanding faster in the local measurements than in the global ones, and no one could fully explain why. Some cosmologists began to seriously entertain the possibility that something was genuinely wrong with the standard model at a fundamental level. Perhaps dark energy was not a constant, but a dynamical field that has evolved over time. Perhaps there was new physics in the early universe, an early dark energy component, perhaps, that slightly modified the expansion history in ways that affected the inferred value of the Hubble constant from the microwave background. Perhaps the equation of state of dark energy was not exactly -1, as the cosmological constant requires, but something slightly different that could produce the observed discrepancy. These were not crackpot ideas. They were serious proposals from serious scientists, published in peer-reviewed journals, seriously debated at conferences. The Hubble tension had elevated from an annoying discrepancy to a potential crack in the foundation of modern cosmology. And then Webb, while helping to characterize the distance ladder with unprecedented precision, also began to deliver its own set of uncomfortable findings about the nature of early galaxies, adding another layer of tension, another set of observations that were difficult but not impossible to explain, to an already complicated picture. The combination of the Hubble tension and the early galaxy problem began to feel, to some cosmologists, like the accumulation of small clues that something larger was being missed, like the way, in detective fiction, a series of seemingly unrelated anomalies gradually resolves into the recognition of a pattern, a deeper logic that was always present but invisible until the right perspective was found. One of the specific findings that generated the most intense discussion was what some researchers began calling the problem of the cosmic titans. These were galaxies, several of them confirmed at high redshift by Webb spectroscopic instruments, that appeared to contain stellar masses comparable to or exceeding those of large present-day galaxies, at epochs when the universe was less than 1 billion years old. In the standard picture of hierarchical structure formation, galaxies grow primarily through mergers. Small galaxies merge to form larger ones, which merge again to form still larger ones, in a bottom-up process driven by the gravitational collapse of dark matter halos. This process takes time. There is a limit to how large a galaxy can grow by a given cosmic age, because there has been only so much time for mergers to occur, only so much time for dark matter halos to collapse and accrete matter. The cosmic titans seemed to be too large too soon. Not impossibly so, not in a way that definitively violated the mathematics of structure formation, but uncomfortably so. Enough to make careful scientists ask whether the assumptions built into their simulations were correct. Those simulations, vast computational endeavors that attempt to model the formation of cosmic structure from first principles, running on some of the world's most powerful supercomputers, have been refined and validated over decades to produce results consistent with the observed universe. But they have been calibrated and tested primarily against observations of the local universe and the moderately distant universe, the universe as it was when it was a few billion years old. Webb was probing territory that had never before been accessible to observation, and the simulations had never been tested against data from those earliest epochs. It was entirely possible that the simulations were wrong in their early universe behavior not because of any fundamental flaw in the underlying physics, but because of simplifying assumptions and numerical approximations that were acceptable for later epochs, but inadequate for the extreme conditions of the early universe. The question of whether early star formation was more efficient than assumed was one such assumption. The treatment of stellar feedback, the way radiation, stellar winds, and supernova explosions affect the surrounding gas and regulate or suppress star formation, was another. Small changes in these parameters could, in principle, produce significant changes in the predicted population of early massive galaxies. The theorists went to work. At the same time that astronomers were grappling with the early galaxy problem, Webb was delivering equally startling results on the question of the nature of the universe's first stars, the so-called population 3 stars, hypothetical objects whose existence was predicted by theory, but which had never been directly observed. Population 3 stars were expected to form from clouds of primordial gas containing only hydrogen, helium, and trace amounts of lithium, the elements produced in the first few minutes after the Big Bang, before any stellar nucleosynthesis had occurred. Without the heavier elements that serve as coolants in present-day star-forming regions, these primordial clouds would have been less efficient at radiating away the heat generated by gravitational collapse, which meant they would have fragmented less effectively and formed stars with much higher masses than typical present-day stars. The first stars may have been hundreds or even thousands of times more massive than the Sun, immensely luminous, burning hot and blue and ferociously, and dying young in cataclysmic explosions that enriched the surrounding gas with the first heavy elements and planted the seeds of future chemical complexity. Webb had not directly detected individual population 3 stars, They would be far too faint and far too distant for even Webb's extraordinary sensitivity. But it had detected what appeared to be their signatures, chemical fingerprints in the spectra of high redshift galaxies suggesting regions of extremely low metallicity, and in some cases, candidate objects whose spectral properties were consistent with the presence of very massive, hot stars of a type not seen in the local universe. The detection was not definitive. Interpreting spectra at these distances involves uncertainties and ambiguities that require careful analysis and often multiple observations. But the hints were there, tantalizing whispers of the universe's first luminous objects, dimly perceived through the noise of cosmic distance. What made these hints particularly interesting was their potential connection to another of Webb's major early findings, the unexpected prevalence of active galactic nuclei, supermassive black holes, in the act of consuming matter and radiating enormous amounts of energy in the early universe. In the Standard Model, supermassive black holes grow over cosmic time by the accretion of gas and by the mergers of smaller black holes. The black holes found at the centers of galaxies today, including the 4 million solar mass beast at the center of our own Milky Way, are the end products of billions of years of growth. Finding supermassive black holes in the early universe, when there had been little time for growth to occur, was therefore unexpected. And yet Webb found them, actively accreting black holes with masses of hundreds of millions, or even billions of solar masses at redshifts of 6, 7, 8, and beyond. Some of these objects, called quasars, had been detected before by earlier observatories, though typically only the most luminous, most extreme examples could be seen at such distances. Webb's greater sensitivity allowed it to detect less extreme examples, a more typical population of early black holes, and what it found was that these objects were more common, and had grown to larger sizes more quickly than the Standard Model comfortably predicted. The connection between population 3 stars and early supermassive black holes was speculative but intriguing. One hypothesis suggested that the most massive population 3 stars might have ended their lives not in conventional supernova explosions, but in a direct collapse to a black hole, bypassing the supernova phase entirely and producing relatively massive black hole seeds, a few hundred to a few thousand solar masses, that could then serve as the starting points for the rapid growth to supermassive scales. Another hypothesis invoked the direct collapse of massive primordial gas clouds, not mediated by stars at all, into so-called direct collapse black holes, which would begin their lives already at the 100,000 solar mass scale, and would have a significant head start in the race to become supermassive. These scenarios were already under consideration before Webb launched, and Webb's observations were beginning to provide data that could, in principle, distinguish between them, though definitively doing so would require many more observations over many more years. There is something almost vertiginous about contemplating these objects. Black holes contain billions of times the mass of our Sun, already assembled less than 1 billion years after the universe began. A black hole is not a thing in any ordinary sense. It is a region of space-time where gravity has become so intense that nothing, not matter, not light, not information, not time as we ordinarily experience it, can escape. The boundary of a black hole, the event horizon, is a surface of no return, a geometric feature of space-time rather than a physical surface, indivisible itself but detectable by its effects on nearby matter. Matter falling toward a black hole is compressed and heated to extreme temperatures, radiating light across the full electromagnetic spectrum before crossing the horizon and disappearing from the observable universe forever. The most massive black holes, surrounded by the richest accretion flows, outshine entire galaxies. That is what a quasar is, a black hole engine so powerful that its radiation overwhelms the combined light of hundreds of billions of stars. And Webb was finding these engines already running at full power in the universe's first few 100 million years. The question of how they got there so quickly is one of the most compelling open problems in modern astrophysics, and Webb's observations are both deepening the mystery and, slowly, beginning to illuminate its edges. The universe is under no obligation to be simple. This is one of the lessons that the history of science teaches, though it is a lesson that each generation of scientists must relearn for itself. Time after time, what has seemed like a complete and satisfying picture of reality has turned out to be an approximation, accurate within a certain domain, useful for a certain set of purposes, but ultimately insufficient for the deeper questions that always lurk beneath. Newtonian mechanics was not wrong. It remains extraordinarily useful for describing the motion of objects at everyday speeds and sizes. But it was incomplete, and Einstein's relativity revealed the incompleteness in a way that simultaneously resolved existing anomalies and opened new territories of understanding that Newton could not have imagined. Quantum mechanics was not wrong. It is the most precisely tested theory in the history of physics. But it is in tension with general relativity in ways that suggest both are approximations to a deeper theory that has not yet been found. The history of physics is a history of successive approximations, each one more accurate and more comprehensive than the last, each one revealing new depths of complexity that the previous picture had not even been able to frame as a question. There is no reason to think this process is complete. There is, in fact, every reason to think it is very far from complete. Webb's findings about the early universe can be seen in this light, not as evidence that modern cosmology is wrong, but as evidence that it is, as all good scientific theories eventually prove to be, incomplete. The Lambda-CDM model has been an extraordinary achievement. It successfully describes the large-scale structure of the universe, the temperature fluctuations of the cosmic microwave background, the abundances of light elements produced by Big Bang nucleosynthesis, the dynamics of galaxy clusters, the statistics of the galaxy distribution, a vast array of observational facts that no previous model had been able to account for. That is not nothing. That is, in fact, a very great deal. But if Webb is telling us that the model's predictions for the early universe are systematically off in certain respects, that massive galaxies assembled too quickly, that black holes grew too fast, that star formation was more efficient than assumed, then the model is incomplete, and the incompleteness is an opportunity. The nature of dark matter is one candidate source of that incompleteness. Dark matter, the invisible, non-luminous substance that constitutes about 27% of the total energy density of the universe, compared to the mere 5% contributed by ordinary visible matter, is one of the most important and least understood components of the cosmos. It was inferred from its gravitational effects, the rotation curves of galaxies, the velocities of galaxies and clusters, the gravitational lensing of background light, all point to the presence of far more mass than is visible. But despite decades of searching, no one has detected a dark matter particle in the laboratory. The most favored candidate, weakly interacting massive particles, or WIMPs, has evaded detection in increasingly sensitive experiments. Other candidates, axions, sterile neutrinos, primordial black holes, remain unconfirmed. The properties of dark matter that are built into the Standard Model, how it interacts with itself, how it clusters on small scales, how it influences the formation of the first structures, are assumed rather than measured, and different assumptions lead to different predictions about the early universe. If dark matter has properties that differ from the simplest assumptions, if it has some degree of self-interaction, for example, or if some fraction of it is warm rather than cold, meaning that it has a non-negligible velocity dispersion that prevents it from clustering on the smallest scales, then galaxy formation in the early universe could proceed differently than current models predict. The cosmic Titan's Webb is finding could, in principle, be a clue about the nature of dark matter as much as about the physics of star formation. Dark energy is another candidate source of incompleteness. The cosmological constant, the simplest form of dark energy, a fixed energy density associated with empty space, is in deep tension with fundamental physics. If you try to calculate the value of the cosmological constant from quantum field theory, you get a number that is either zero or enormous, depending on what assumptions you make, and neither of those numbers matches the observed value, which is tiny but non-zero. The cosmological constant problem is one of the deepest unsolved problems in theoretical physics, a gap between our two great theories, quantum mechanics and general relativity, that we do not know how to bridge. If dark energy is not a constant, but a dynamical field, an entity that evolves over time, perhaps approaching the cosmological constant value today, but having had a different value in the early universe, then the expansion history of the universe would be different from the Landau-CDM prediction, and the growth of structure could proceed at a different rate, potentially explaining some of what Webb is seeing. New observations from a different space mission, the Euclid satellite, launched in 2023, are expected to provide constraints on the evolution of dark energy over cosmic time. But Webb's data on high redshift galaxies is already beginning to place limits on some models. There is a quality to the light from a very distant galaxy that is almost impossible to fully capture in words, but worth attempting. That light left its source billions of years ago, in some cases, more than 13 billion years ago, when the universe was young and different, and full of processes that no longer operate in the same way. For billions of years it traveled across expanding space, its wavelength stretching as the universe itself stretched, carrying information